Hello, my name is Dan Bonet, and I'd like to welcome you to my course on cryptography that I'll be teaching at Stanford University this quarter. This quarter I'm experimenting with recording the lectures and having the students watch the lectures online. In fact, anyone is welcome to watch the lectures and join the course. This is an experiment, so we'll see how it goes. My goals for this course are basically to teach you how cryptographic primitives work. But more importantly, I'd like to teach you how to use cryptographic primitives correctly and reason about the security of your constructions. We will see various abstractions of cryptographic primitives, and we'll do some security proofs. My goal is that by the end of the course, you'll be able to reason about the security of cryptographic constructions and be able to break ones that are not secure. Now, I'd like to say a few words on how I would like you to take the class. First of all, I'm a big believer in taking notes as you listen to the lectures, so I would really encourage you to summarize and take notes in your own words of the material that's being presented. Also, I should mention that on the videos, I'm able to go much faster than I would go in a normal classroom, and so I would encourage you to periodically pause the video and think about the material that's being covered and not move forward until the material is clear in your mind. Also, from time to time, the video will pause and pop-up questions will come up. These are intended to kind of help you along with the material, and I would really encourage you to answer those questions by yourselves rather than skip them. Usually the questions are about the material that has just been covered, and so it shouldn't be too difficult to answer the questions. So I would really encourage you to do them rather than skip them. Now, by now, I'm sure everybody taking the class knows that cryptography is used everywhere computers are. It's a very common tool that's used to protect data. For example, web traffic is protected using a protocol called HTTPS. Wireless traffic, for example, Wi-Fi traffic is protected using the WPA2 protocol that's part of 802.11i. Cell phone traffic is protected using an encryption mechanism in GSM. Bluetooth traffic is protected using cryptography, and so on. We're going to see how these various systems work. In fact, we're going to cover SSL and, in fact, even 802.11i in quite a bit of detail, and you'll see how these systems work in practice. Cryptography is also used for protecting files that are stored on disk by encrypting them, so that if the disk is stolen, the files are not compromised. It's also used for content protection. For example, when you buy DVDs and Blu-ray discs, the movies on these discs are encrypted. In particular, DVD uses a system called CSS, the Content Scrambling System, CSS, and Blu-ray uses a system called AACS. We'll talk about how CSS and AACS work. It turns out that CSS is a fairly easy system to break, and we'll talk about how we'll do some cryptanalysis and actually show how to break encryption that's used in CSS. Cryptography is also used for user authentication and many other applications that we'll talk about in the next segment. Now, I want to go back to secure communication and talk about the case where here we have a laptop trying to communicate with a web server. This is a good time to also introduce our friends Alice and Bob, who are going to be with us throughout the quarter. Essentially, Alice is trying to communicate securely with Bob. Here, Alice is on the laptop and Bob is on the server. The protocol that's used to do that is called HTTPS, but in fact, the actual protocol is called SSL. Sometimes it's called TLS. And the goals of these protocols is basically to make sure that as data travels across the network, an attacker, first of all, can't eavesdrop on this data, and second of all, an attacker can't modify the data while it's in the network. So no eavesdropping and no tampering. Now, as I said, the protocol that's used to secure web traffic, called TLS, actually consists of two parts. The first part is called this handshake protocol, where Alice and Bob talk with one another, and at the end of the handshake, basically a shared secret key appears between the two of them. So both Alice and Bob know this secret key, but an attacker looking at the conversation has no idea what the key K is. Now, the way you establish this secret key, the way you do the handshake, is using public key cryptography techniques, which we're going to talk about in the second part of the course. Now, once Alice and Bob have the shared key, we can use this key to communicate securely by properly encrypting data between them. And in fact, this is going to be the first part of the course, which is essentially once the two sides have a shared secret key, how do they use that secret key to encrypt and protect data that goes back and forth between them. Now, as I said, another application of cryptography is to protect files on disk. So here you have a file that happens to be encrypted, so that even if the disk is stolen, an attacker can't actually read the contents in the file. And if an attacker tries to modify the data on disk, the data in the file while it's on disk, when Alice tries to decrypt this file, that will be detected, and she'll then basically ignore the contents of the file. So we have both confidentiality and integrity for files stored on disk. Now, I want to make a minor philosophical point that in fact storing encrypted files on disk is very much the same as protecting communication between Alice and Bob. In particular, when you store files on disk, it's basically Alice who stores a file today wants to read the file tomorrow. So rather than communicating between two parties, Alice and Bob, in the case of stored disk encryption, it's Alice today who's communicating with Alice tomorrow. But really the two scenarios, secure communications and secure files, are kind of philosophically the same. Now, the building block for securing traffic is what's called symmetric encryption systems. And we're going to talk in the first half of the course extensively about symmetric encryption systems. So in a symmetric encryption system, basically the two parties, Alice and Bob, share a secret key K, which the attacker does not know. Only they know the secret key K. Now they're going to use a cipher which consists of these two algorithms, E and D. E is called an encryption algorithm, and D is called a decryption algorithm. The encryption algorithm takes the message and the key as input and produces a corresponding ciphertext. And the decryption algorithm does the opposite. It takes the ciphertext as input along with the key and produces the corresponding message. Now, a very important point that I'd like to stress, I'm only going to say this once now and never again, but it is an extremely important point, and that is that the algorithms E and D, the actual encryption algorithms, are publicly known. Adversary knows exactly how they work. The only thing that's kept secret is the secret key K. Other than that, everything else is completely public. And it's really important to realize that you should only use algorithms that are public, because those algorithms have been peer-reviewed by a very large community of hundreds of people for many, many, many years, and these algorithms only begin to be used once this community has shown that they cannot be broken, essentially. So in fact, if someone comes to you and says, hey, I have a proprietary cipher that you might want to use, the answer usually should be that you stick to standards, to standard algorithms, and not use a proprietary cipher. In fact, there are many examples of proprietary ciphers that as soon as they were reverse engineered, they were easily broken by simple analysis. Now, even in the simple case of symmetric encryption, which we're going to discuss in the first half of the course, there are actually two cases that we're going to discuss in turn. The first is when every key is only used to encrypt a single message. We call these one-time keys. Okay, so for example, when you encrypt email messages, it's very common that every single email is encrypted using a different symmetric key. Yeah, different symmetric cipher key. Because the key is used to only encrypt one message, there are actually fairly efficient and simple ways of encrypting messages using these one-time keys, and we'll discuss those actually in the next module. Now, there are many cases, in fact, where keys need to be used to encrypt multiple messages. We call these many-time keys. For example, when you encrypt files in a file system, the same key is used to encrypt many, many different files. And it turns out if the key is now going to be used to encrypt multiple messages, we need a little bit of more machinery to make sure that the encryption system is secure. In fact, after we talk about one-time keys, we'll move over and talk about encryption modes that are specifically designed for many-time keys, and we'll see that there are a couple more steps that need to be taken to ensure security in those cases. Okay, the last point I want to make is that there are a couple of important things to remember about cryptography. First of all, cryptography, of course, is a fantastic tool for protecting information in computer systems. However, it's also very important that cryptography has its limitations. First of all, cryptography is really not the solution to all security problems. For example, if you have software bugs, then very often cryptography is not going to be able to help you. Similarly, if you're worried about social engineering attacks, where the attacker tries to fool the user into taking actions that are going to hurt the user, then cryptography is very often actually not going to help you. So it's very important that although it's a fabulous tool, it's not the solution to all security problems. Now, another very important point is that cryptography essentially becomes useless if it's implemented incorrectly. So for example, there are a number of systems that work perfectly fine, and we'll see examples of those systems that in fact allow Alice and Bob to communicate, and in fact messages that Alice sent to Bob, Bob can receive and decrypt. However, because cryptography is implemented incorrectly, the systems are completely insecure. And actually, I should say that I like to mention an old encryption standard called WEP, WEP, that's used for encrypting Wi-Fi traffic. WEP contains many mistakes in it, and often when I want to show you how not to do things in cryptography, I will point to how things were done in WEP as an example. So for me, it's very fortunate to have an example protocol I can point to for how not to do things. And finally, a very important point that I'd like you to remember is that cryptography is not something you should try to invent and design yourself. As I said, there are standards in cryptography, standard cryptographic primitives, which we're going to discuss at length during this course. And primarily, you're supposed to use these standard cryptographic primitives and not invent these primitives yourself. The standards have all gone through many years of review by hundreds of people, and that's not something that's going to happen to an ad hoc design. And as I said, over the years, there are many examples of ad hoc designs that were immediately broken as soon as they were analyzed. Before we start with the technical material, I want to give you a quick overview of what cryptography is about and the different areas of cryptography. So the core of cryptography, of course, is secure communication that essentially consists of two parts. The first is secure key establishment, and then how do we communicate securely once we have a shared key. We already said that secure key establishment essentially amounts to Alice and Bob sending messages to one another, such that at the end of this protocol, there's a shared key that they both agree on, shared key K. And beyond that, beyond just a shared key, in fact, Alice would know that she's talking to Bob, and Bob would know that he's talking to Alice. But a poor attacker who listens in on this conversation has no idea what the shared key is. And we'll see how to do that later on in the course. Now, once they have a shared key, they want to exchange messages securely using this key, and we'll talk about encryption schemes that allow them to do that in such a way that an attacker can't figure out what messages are being sent back and forth, and furthermore, an attacker cannot even tamper with this traffic without being detected. In other words, these encryption schemes provide both confidentiality and integrity. But cryptography does much, much, much more than just these two things, and I want to give you a few examples of that. So the first example I want to give you is what's called a digital signature. So a digital signature basically is the analog of a signature in the physical world. In the physical world, remember, when you sign a document, essentially you write your signature on that document, and your signature is always the same. You always write the same signature on all documents that you want to sign. In the digital world, this can't possibly work, because if the attacker just obtained one signed document for me, he can cut and paste my signature onto some other document that I might not have wanted to sign. And so it's simply not possible in the digital world that my signature is the same for all documents that I want to sign. So we're going to talk about how to construct digital signatures in the second half of the course. It's really quite an interesting primitive, and we'll see exactly how to do it. Just to give you a hint, the way digital signatures work is basically by making the digital signature be a function of the content being signed. So an attacker who tries to copy my signature from one document to another is not going to succeed, because the signature on the new document is not going to be the proper function of the data in the new document. And as a result, the signature won't verify. And as I said, we're going to see exactly how to construct digital signatures later on, and then we'll prove that those constructions are secure. Another application of cryptography that I wanted to mention is anonymous communication. So here, imagine user Alice wants to talk to some chat server Bob. And perhaps she wants to talk about a medical condition, and so she wants to do that anonymously so that the chat server doesn't actually know who she is. Well, there's a standard method called a mixnet that allows Alice to communicate over the public internet with Bob through a sequence of proxies, such that at the end of the communication, Bob has no idea who it just talked to. The way mixnets work is basically as Alice sends her messages to Bob through a sequence of proxies, these messages get encrypted and decrypted appropriately so that Bob has no idea who it talked to, and the proxies themselves don't even know that Alice is talking to Bob, or that actually who's talking to who more generally. One interesting thing about this anonymous communication channel is it's bidirectional. In other words, even though Bob has no idea who it's talking to, he can still respond to Alice, and Alice will get those messages. Once we have anonymous communication, we can build other privacy mechanisms. And I want to give you one example, which is called anonymous digital cash. Remember that in the physical world, if I have a physical dollar, I can walk into a bookstore and buy a book, and the merchant would have no idea who I am. The question is whether we can do the exact same thing in the digital world. In the digital world, basically, Alice might have a digital dollar coin, and she might want to spend that digital dollar at some online merchant, perhaps some online bookstore. Now, what we'd like to do is make it so that when Alice spends her coin at the bookstore would have no idea who Alice is. So we provide the same anonymity that we get from physical cash. Now the problem is that in the digital world, Alice can take the coin that she had, this $1 coin, and before she spent it, she can actually make copies of it. And then all of a sudden, instead of having just $1 coin, now all of a sudden she has $3 coins, and they're all the same, of course. And there's nothing preventing her from taking those replicas of the dollar coin and spending it at other merchants. And so the question is, how do we provide anonymous digital cash, but at the same time also prevent Alice from double spending the dollar coin at different merchants? In some sense, there's a paradox here where anonymity is in conflict with security, because if we have anonymous cash, there's nothing to prevent Alice from double spending the coin, and because the coin is anonymous, we have no way of telling who committed this fraud. And so the question is, how do we resolve this tension? And it turns out it's completely doable, and we'll talk about anonymous digital cash later on. Just to give you a hint, I'll say that the way we do it is basically by making sure that if Alice spends the coin once, then no one knows who she is. But if she spends the coin more than once, all of a sudden her identity is completely exposed, and then she could be subject to all sorts of legal problems. And so that's how anonymous digital cash would work at a high level, and we'll see how to implement it later on in the course. Another application of cryptography has to do with more abstract protocols. But before I state the general results, I want to give you two examples. So the first example has to do with election systems. So here's the election problem. Suppose we have two parties, Party 0 and Party 1, and voters vote for these parties. So for example, this voter could have voted for Party 0, this voter voted for Party 1, and so on. So in this election, Party 0 got 3 votes, and Party 2 got 2 votes. So the winner of the election, of course, is Party 0, but more generally, the winner of the election is the party who receives the majority of the votes. Now, the voting problem is the following. The voters would somehow like to compute the majority of the votes, but do it in such a way such that nothing else is revealed about their individual votes. Okay, so the question is how to do that. And to do so, we're going to introduce an election center who's going to help us compute the majority, but keep the votes otherwise secret. And what the parties will do is they will each send a funny encryption of their votes to the election center in such a way that at the end of the election center is able to compute and output the winner of the election. However, other than the winner of the election, nothing else is revealed about the individual votes. The individual votes otherwise remain completely private. Of course, the election center is also going to verify that this voter, for example, is allowed to vote and that the voter has only voted once. But other than that information, the election center and the rest of the world learn nothing else about that voter's vote other than the result of the election. So this is an example of a protocol that involves 6 parties. In this case, there are 5 voters and 1 election center. These parties compute amongst themselves, and at the end of the computation, the result of the election is known, but nothing else is revealed about the individual inputs. Now, a similar problem comes up in the context of private auctions. So in a private auction, every bidder has his own bid that he wants to bid. And now suppose the auction mechanism that's being used is what's called a victory auction, where the definition of a victory auction is that the winner is the highest bidder, but the amount that the winner pays is actually the second highest bid. So he pays the second highest bid. Okay, so this is a standard auction mechanism called the victory auction. And now what we'd like to do is basically enable the participants to compute, to figure out who the highest bidder is and how much he's supposed to pay. But other than that, all other information about the individual bids should remain secret. So for example, the actual amount that the highest bidder bid should remain secret. The only thing that should become public is the second highest bid and the identity of the highest bidder. So again, now the way we will do that is we'll introduce an auction center, and in a similar way, essentially everybody will send their encrypted bids to the auction center. The auction center will compute the identity of the winner, and in fact, he will also compute the second highest bid. But other than these 2 values, nothing else is revealed about the individual bids. Now, this is actually an example of a much more general problem called secure multi-party computation, and let me explain what secure multi-party computation is about. So here, basically, abstractly, the participants have a secret input to themselves. So in the case of an election, the inputs would be the votes. In the case of an auction, the inputs would be the secret bids. And then what they'd like to do is compute some sort of a function of their inputs. Again, in the case of an election, the function is the majority. In the case of auction, the function happens to be the second highest largest number among x1 to x4. And the question is, how can they do that such that the value of the function is revealed, but nothing else is revealed about the individual votes? So let me show you kind of a dumb, insecure way of doing it. What we do is we introduce a trusted party. And then this trusted authority basically collects individual inputs, and it kind of promises to keep the individual inputs secret so that only it would know what they are, and then it publishes the value of the function to the world. So the idea is now that the value of the function became public, but nothing else is revealed about the individual inputs. But of course, you got this trusted authority that you got to trust, and if for some reason it's not trustworthy, then you have a problem. And so there's a very central theorem in crypto. It really is quite a surprising fact that says that any computation you'd like to do, any function f you'd like to compute, that you can compute with a trusted authority, you can also do without a trusted authority. Let me at a high level explain what this means. Basically what we're going to do is we're going to get rid of the authority, so the parties are actually not going to send their inputs to the authority, and in fact there's no longer going to be an authority in the system. Instead, what the parties are going to do is they're going to talk to one another using some protocol, such that at the end of the protocol, all of a sudden the value of the function becomes known to everybody, and yet nothing other than the value of the function is revealed. In other words, the individual inputs is still kept secret. But again, there is no authority. There's just a way for them to talk to one another such that the final output is revealed. So this is a fairly general result. It's kind of a surprising fact that this is at all doable, and in fact it is, and towards the end of the class we'll actually see how to make this happen. Now, there are some applications of cryptography that I can't classify in any other way other than to say that they're purely magical. Now, let me give you two examples of that. So the first is what's called privately outsourcing computation. So I'll give you an example of a Google search just to illustrate the point. So imagine Alice has a search query that she wants to issue. It turns out that there are very special encryption schemes such that Alice can send an encryption of her query to Google, and then because of the property of the encryption scheme, Google can actually compute on the encrypted values without knowing what the plaintext are. So Google can actually run its massive search algorithm on the encrypted query and recover an encrypted results. Okay? Google would send the encrypted results back to Alice, Alice would decrypt, and then she would receive the results. But the magic here is all Google saw was just encryptions of her queries and nothing else. And so Google, as a result, has no idea what Alice just searched for, and nevertheless, Alice actually learned exactly what she wanted to learn. Okay, so these are magical kind of encryption schemes. They're fairly recent. This is only a new development from about 2 or 3 years ago that allows us to compute on encrypted data, even though we don't really know what's inside the encryption. Now, before you rush off and think about implementing this, I should warn you that this is really, at this point, just theoretical in the sense that running a Google search on encrypted data probably would take 1 billion years. But nevertheless, just the fact that this is doable is already really surprising and is already quite useful for relatively simple computations. So in fact, we'll see some applications of this out later on. The other magical application I want to show you is what's called zero knowledge. And in particular, I'll tell you about something called the zero knowledge proof of knowledge. So here, what happens is there's a certain number n which Alice knows, and the way the number n was constructed is as a product of two large primes. So imagine here we have two primes, p and q. Each one you can think of it as like 1,000 digits. And you probably know that multiplying 2,000 digit numbers is fairly easy. But if I just give you their product, figuring out their factorization into primes is actually quite difficult. And in fact, we're going to use the fact that factoring is difficult to build public key crypto systems in the second half of the course. Okay, so Alice happens to have this number n, and she also knows the factorization of n. Now Bob just has the number n. He doesn't actually know the factorization. Now the magical fact about the zero knowledge proof of knowledge is that Alice can prove to Bob that she knows the factorization of n. Yeah, she can actually give this proof to Bob that Bob can check and become convinced that Alice knows the factorization of n. However, Bob learns nothing at all about the factors p and q. And this is provable. Bob absolutely learns nothing at all about the factors p and q. And this statement actually is very, very general. This is not just about proving the factorization of n. In fact, almost any puzzle that you want to prove that you know an answer to, you can prove it in zero knowledge. So if you have a crossword puzzle that you've solved, well, maybe crosswords is not the best example, but if you have like a Sudoku puzzle, for example, that you want to prove that you've solved, you can prove it to Bob in a way that Bob would learn nothing at all about the solution, and yet Bob would be convinced that you really do have a solution to this puzzle. Okay, so those are kind of magical applications. And so the last thing I want to say is that modern cryptography is a very rigorous science, and in fact, every concept we're going to describe is going to follow 3 very rigorous steps. Okay, and we're going to see these 3 steps again and again and again, so I want to explain what they are. So the first thing we're going to do when we introduce a new primitive, like a digital signature, is we're going to specify precisely what the threat model is. That is, what can an attacker do to attack a digital signature, and what is his goal in forging signatures. Okay, so we're going to define exactly what does it mean for a signature, for example, to be unforgeable. Unforgeable. Okay, and I'm giving digital signatures just as an example. For every primitive we describe, we're going to precisely define what the threat model is. Then we're going to propose a construction, and then we're going to give a proof that any attacker that's able to attack the construction under this threat model, that attacker can also be used to solve some underlying hard problem. And as a result, if the problem really is hard, that actually proves that no attacker can break the construction under the threat model. Okay, but these 3 steps are actually quite important. In the case of signatures, we'll define what it means for a signature to be unforgeable, then we'll give a construction, and then, for example, we'll say that anyone who can break our construction can then be used to, say, factor integers, which is believed to be a hard problem. Okay, so we're going to follow these 3 steps throughout, and you'll see how this actually comes about. Okay, so this is the end of the segment, and then in the next segment we'll talk a little bit about the history of cryptography. Before we start with the technical material, I want to tell you a little bit about the history of cryptography. There's a beautiful book on this topic by David Kahn called The Codebreakers that covers the history of cryptography all the way from the Babylonian era to the present. Here I'm just going to give you a few examples of historical ciphers, all of which are badly broken. So to talk about ciphers, the first thing I'm going to do is introduce our friends Alice and Bob, who are going to be with us for the rest of the quarter. So Alice and Bob are trying to communicate securely, and there is an attacker who's trying to eavesdrop on their conversation. So to communicate securely, they're going to share a secret key, which I'll denote by K. They both know this secret key, but the attacker does not know anything about this key K. So now they're going to use a cipher, which is a pair of algorithms, an encryption algorithm denoted by E and a decryption algorithm D. These algorithms work as follows. The encryption algorithm E takes the message M as inputs, and it takes as inputs the key K. I'm going to put a wedge above the key input just to denote the fact that this input is really the key input. And then it outputs a ciphertext, which is the encryption of the message M using the key K. I'm always going to write the key first, and when I write colon equals, what I mean is that the expression defines what the variable C stands for. Now the ciphertext is transmitted over the internet to Bob somehow. Actually, it could be transmitted over the internet, could be transmitted using an encrypted file system. It doesn't really matter. But when the ciphertext reaches Bob, he can plug it into the decryption algorithm and give the decryption algorithm the same key K. Again, I'm going to put a wedge here as well to denote the key input. And the decryption algorithm outputs the original plaintext message. Now, the reason we say that these are symmetric ciphers is that both the encryptor and decryptor actually use the same key K. As we'll see later in the course, there are ciphers where the encryptor uses one key and the decryptor uses a different key. But here we're just going to focus on symmetric ciphers where both sides use the same key. Okay, so let me give you a few historic examples of ciphers. The first example, the simplest one, is called a substitution cipher. I'm sure all of you played with substitution ciphers when you were in kindergarten. Basically, a key for a substitution cipher is a substitution table that basically says how to map letters. So here, for example, the letter A would be mapped to C, the letter B would be mapped to W, the letter C would be mapped to N, so on and so forth, and then the letter Z would be mapped, say, to A. So this is one example of a key for a substitution cipher. So just to practice the notation we introduced before, the encryption of a certain message using this key, let's say the message is B, C, Z, A, the encryption of this message using this key here would be, is done by substituting one letter at a time. So B becomes W, C becomes N, Z becomes A, and A becomes C. So the encryption of BCZA is WNAC, and this defines the ciphertext. Similarly, we can decrypt the ciphertext using the same key, and of course we'll get back the original message. Okay, so just for historical reasons, there's one example of something that's related to the substitution cipher called the Caesar cipher. The Caesar cipher actually is not really a cipher at all, and the reason is that it doesn't have a key. What a Caesar cipher is basically a substitution cipher where the substitution is fixed, namely it's a shift by 3. So A becomes D, B becomes E, C becomes F, and so on and so forth. What is it? Y becomes B, and Z becomes C. It's a fixed substitution that's applied to all plaintext messages. So again, this is not a cipher because there is no key. The key is fixed. So if an attacker knows how our encryption scheme works, he can easily decrypt the message. The key is not random, and therefore decryption is very easy once you understand how the scheme actually works. Okay, so now let's go back to the substitution cipher where the keys really are chosen at random. These substitution tables are chosen at random. And let's see how we break this substitution cipher. Turns out to be very easy to break. The first question is, how big is the key space? How many different keys are there, assuming we have 26 letters? So I hope all of you said that the number of keys is 26 factorial because a substitution key is simply a table, a permutation of all 26 letters. The number of permutations of 26 letters is 26 factorial. If you calculate this out, 26 factorial is about 2 to the 88, which means that describing a key in a substitution cipher takes about 88 bits. So each key is represented by about 88 bits. Now, this is a perfectly fine size for a key space. In fact, we're going to be seeing ciphers that are perfectly secure that are adequately secure with key spaces that are roughly of this size. However, even though the substitution cipher has a large key space of size 2 to the 88, it's still terribly insecure. So let's see how to break it. And to break it, we're going to be using letter frequencies. So the first question is, what is the most frequent letter in English text? So I imagine all of you know that, in fact, E is the most common letter. And that is going to, if we make that quantitative, that's going to help us break a substitution cipher. So just given the ciphertext, we can already recover the plaintext. So the way we do that is, first of all, using frequencies of English letters. So here's how this works. So you give me an encrypted message using a substitution cipher. All I know is that the message is in English, the plaintext is in English. And I know that the letter E is the most frequent letter in English, and in fact it appears 12.7% of the time in standard English text. So what I'll do is I'll look at the ciphertext you gave me, and I'm going to count how many times every letter appears. Now, the most common letter in the ciphertext is going to be the encryption of the letter E with very high probability. So now I'm able to recover one entry in the key table, namely now I know what the letter E maps to. The next most common letter in English is the letter T, that appears about 9.1% of the time. So now again, I count how many times each letter appears in the ciphertext, and the second most frequent letter is very likely to be the encryption of the letter T. So now I've recovered the second entry in the key table. And I can continue this way. In fact, the letter A is the next most common letter. It appears 8.1% of the time. So now I can guess that the third most common letter in the ciphertext is the encryption of the letter A, and now I've recovered 3 entries in the key table. Well, so now what do? The remaining letters in English appear roughly the same amount of time, other than some rare letters like Q and X. But we're kind of stuck at this point. We figured out 3 entries in the key table, but what do we do next? So the next idea is to use frequencies of pairs of letters. Sometimes these are called digrams. So what I'll do is I'll count how many times each pair of letters appears in the ciphertext. And I know that in English, the most common pairs of letters are things like HE, AN, IN, I guess TH is another common pair of letters. And so I know that the most common pair of letters in the ciphertext is likely to be the encryption of one of these 4 pairs. And so by trial and error, I can sort of figure out more elements in the key table. And again, by more trial and error, this way, by looking at trigrams, I can actually figure out the entire key table. So the bottom line here is that in fact this substitution cipher is vulnerable to the worst possible type of attack, namely a ciphertext only attack. Just given the ciphertext, the attacker can recover the decryption key and therefore recover the original plaintext. So there's really no point in encrypting anything using a substitution cipher because the attacker can easily decrypt it all. You might as well send your plaintext completely in the clear. So now we're going to fast forward to the Renaissance, and I guess we're moving from the Roman era to the Renaissance, and look at a cipher designed by a fellow named Vigenère who lived in the 16th century. He designed a couple of ciphers. Here I'm going to show you a variant of one of his ciphers. This is called a Vigenère cipher. So in a Vigenère cipher, the key is a word. In this case, the word is crypto. It's got 6 letters in it. And then to encrypt the message, what you do is you write the message under the key. So in this case, the message is, "What a nice day today." And then you replicate the key as many times as needed to cover the message. And then the way you encrypt is basically you add the key letters to the message letters modulo 26. So just to give you an example here, for example, if you add Y and A, you get Z. If you add T and A, you get U. And you do this for all the letters. And remember, whenever you add modulo 26. So if you go past Z, you go back to A. So that's the Vigenère cipher. And in fact, decryption is just as easy as encryption. Basically, the way you would decrypt is, again, you would write the ciphertext under the key, you would replicate the key, and then you would subtract the key from the ciphertext to get the original plaintext message. So breaking a Vigenère cipher is actually quite easy. Let me show you how you do it. The first thing we need to do is we need to assume that we know the length of the key. So let's just assume we know that. In this case, the length of the key is 6. And then what we do is we break the ciphertext into groups of 6 letters each. Okay, so we're going to get a bunch of groups like this. Each one contains 6 letters. And then we're going to look at the first letter in each group. Okay, so in this case, yes, we're looking at the first letter every 6 characters. Now, what do we know about these 6 letters? We know that, in fact, they're all encrypted using the same letter in the ciphertext. All of these are encrypted using the letter C. In other words, ZLW is a shift by 3 of the plaintext letters. So if we collect all these letters, then the most common letter among the set is likely to be the encryption of E. Right? E is the most common letter in English. Therefore, if I look at every 6th letter, the most common letter in that set is likely to be the encryption of the letter E. Aha! So let's just suppose that, in fact, the most common letter every 6th letter happens to be the letter H. Then we know that E plus the first letter of the key is equal to H. That says that the first letter of the key is equal to H minus E. And in fact, that is the letter C. So now we've recovered the first letter of the key. And now we can continue doing this with the second letter. So we look at the second letter in every group of 6 characters. And again, we repeat the same exercise. We find the most common letter among this set. And we know that this most common letter is likely the encryption of E. And therefore, whatever this most common letter is, if we subtract E from it, we're going to get the second letter of the key. And so on and so forth with the third letter every 6 characters. And this way we recover the entire key, and that allows us to decrypt the message. Now, the only caveat is that I had to assume ahead of time that I know the length of the key, which in this case is 6. But if I don't know the length of the key ahead of time, that's not a problem either. What I would do is I would run this decryption procedure assuming the key length is 1. Then I'd run it assuming the key length is 2. Then I would run it assuming the key length is 3. And so on and so on and so on until finally I get a message, I get a decryption that makes sense, that's sensical. And once I do that, I know that I've kind of recovered the right length of the key. And I know that I've also recovered the right key and therefore the right message. Okay, so very, very quickly you can recover, you can decrypt Vigenère ciphers. Again, this is a ciphertext only attack. The interesting thing is that Vigenère had a good idea here. This addition mod 26
is actually a good idea, and we'll see that later, except it's executed very poorly here. And so we'll correct that a little bit later. Okay, we're going to fast forward now from the Renaissance to the 19th century, where everything became electric. And so people wanted to design ciphers that use electric motors. In particular, these ciphers are called rotor machines because they use rotors. So an early example is called a Hebron machine, which uses a single rotor. Here you have a picture of this machine. The motor, I guess the rotor is over here, and the secret key is captured by this disk here. It's embedded inside of this disk, which rotate by 1 notch every time you press a key on the typewriter. Okay, so every time you hit a key, the disk rotates by 1 notch. Now, what does this key do? Well, the key actually encodes a substitution table. So, and therefore the disk actually is the secret key. And as I said, this disk encodes a substitution table. In this case, if you happen to press C as the first letter, output would be the letter T. And then the disk would rotate by 1 notch. After rotating by 1 notch, the new substitution table becomes the one shown here. You see that E basically moves up, and then the remaining letters moves down. So imagine this is basically a 2-dimensional rendering of the disk rotating by 1 notch. Then you press the next letter, and the disk rotates again. You notice again N moved up, and the remaining letters moved down. So in particular, if we hit the letter C 3 times, the first time the output would be T. The second time the output would be S, and the third time the output would be K. So this is how this single rotor machine works. And as it turned out, very quickly after it was advertised, it was again broken basically using letter frequencies, digram frequencies, and trigram frequencies. It's not that hard, given enough ciphertext, to directly recover the secret key and then the message. Again, a ciphertext only attack. So to kind of work against these frequency attacks, these statistical attacks, these rotor machines became more and more complicated over time, until finally, I'm sure you've all heard of the Enigma. The Enigma is kind of a complicated rotor machine. It uses 3, 4, or 5 rotors. There are different versions of the Enigma machine. Here you see an example of the Enigma machine with 3 rotors. The secret key in the Enigma machine is the initial setting of the rotors. Okay, so in the case of 3 rotors, there would be 26 cube possible different keys. When you type on the typewriter, basically these rotors here rotate at different rates. Oh, I forgot to say, this is a diagram of an Enigma machine using 4 rotors. As you type on the typewriter, the rotors rotate and output the appropriate letters of the ciphertext. So in this case, the number of keys is 26 to the 4th, which is 2 to the 18, which is actually relatively a small key space. Today you can kind of brute force search using a computer through 2 to the 18 different keys very, very quickly. You know, my wristwatch can do it in just a few seconds, I guess. And so this Enigma machine was using relatively small key spaces, but I'm sure you've all heard that the British cryptographers at Bletchley Park were able to mount ciphertext-only attacks on the Enigma machine. They were able to decrypt German ciphers back in World War II, and that played an important role in many different battles during the war. After the war, I guess that was the end kind of the mechanical age, and started the digital age, where folks were using computers. And as the world kind of migrated to using computers, the government realized that it's buying a lot of digital equipment from industry. And so it wanted industry to use a good cipher, so that when it buys equipment from industry, it would be getting equipment with a decent cipher. And so the government put out this request for proposal for a data encryption standard, a federal data encryption standard. And we're going to talk about this effort in more detail later on in the course. But in 1974, a group at IBM put together a cipher that became known as DES, the Data Encryption Standard, which became a federal standard for encrypting data. The key space for DES is 2 to the 56, which is relatively small these days, but was large enough back in 1974. And another interesting thing about DES is, rather than, unlike rotor machines, which encrypt 1 character at a time, the data encryption standard encrypts 64 bits at a time, namely 8 characters at a time. And we'll see the significance of this later on in the course. Because DES uses such a small key space, these days it can be broken by a brute force search. And so these days, DES is considered insecure and should not be used in projects. Unfortunately, it is used in some legacy systems, but it definitely is on its way out and definitely should not be used in new projects. Today, there are new ciphers, things like the Advanced Encryption Standard, which uses 128-bit keys. Again, we'll talk about the Advanced Encryption Standard in much more detail later on in the course. There are many, many other types of ciphers. I mentioned Salsa 20 here. We'll see why in just a minute. But this is all for the quick historical survey, and now we can get into the more technical material.
Over the years, many natural cryptographic constructions were found to be insecure. In response, modern cryptography was developed as a rigorous science where constructions are always accompanied by a proof of security. The language used to describe security relies on discrete probability. In this segment and the next, I'll give a quick overview of discrete probability, and I point to this Wikibooks article over here for a longer introduction. Discrete probability is always defined over a universe, which I'll denote by U, and this universe in our case is always going to be a finite set. In fact, very commonly, our universe is going to be simply the set of all n-bit strings, which here is denoted by 0, 1 to the n. So for example, the set 0, 1 squared is the set of all 2-bit strings, which happens to be the string 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 elements in this set, and more generally, in the set 0, 1 to the n, there are 2 to the n elements. Now, a probability distribution over this universe U is simply a function which I'll denote by P, and this function, what it does is it assigns to every element in the universe a number between 0 and 1. And this number is what I'll call the weight or the probability of that particular element in the universe. Now, there's only one requirement on this function P, and that is that the sum of all the weights sum up to 1. That is, if I sum the probability of all elements x in the universe, what I end up with is the number 1. So let's look at a very simple example, looking back to our 2-bit universe, so 0, 0, 0, 1, 1, 0, and 1, 1, and you can consider the following probability distribution, which, for example, assigns to the element 0, 0 the probability 1/2, the element 0, 1, we assign the probability 1/8, to 1, 0, we assign the probability 1/4, and to 1, 1, we assign the probability 1/8. Okay, and you can see that if we sum up these numbers, in fact, we get 1, which means that this probability P is, in fact, the probability distribution. Now, what these numbers mean is if I sample from this probability distribution, I'll get the string 0, 0 with probability 1/2, I'll get the string 0, 1 with probability 1/8, and so on and so forth. So now that we understand what a probability distribution is, let's look at 2 classic examples of probability distributions. The first one is what's called the uniform distribution. The uniform distribution assigns to every element in the universe exactly the same weight. I'm going to use U between 2 bars to denote the size of the universe U, that is the number of elements in the universe. And since we want the sum of all the weights to sum up to 1, and we want all these weights to be equal, what this means is that for every element x in the universe, we assign a probability of 1 over U. So in particular, if we look at our example, the uniform distribution on the set of 2-bit strings would simply assign 1/4, the weight 1/4 to each one of these strings. And clearly, the sum of all the weights sums up to 1. What this means is that if I sample at random from this distribution, I'll get a uniform sample across all 2-bit strings. So all of these 4-bit strings are equally likely to be sampled by this distribution. Another distribution that's very common is what's called the point distribution at the point x0. And what this point distribution does is basically it puts all the weights on a single point, namely x0. So here we assign to the point x0 all the weight, 1, and then to all other points in the universe, we assign the weight 0. And by the way, I want to point out that this inverted A here should be read as for all. So all this says is that for all x that are not equal to x0, the probability of that x is equal to 0. So again, going back to our example, a point distribution, for example, that would put all its mass on the string 1, 0 would assign the probability 1 to the string 1, 0 and 0 to all other strings. So now if I sample from this distribution, pretty much I'm always guaranteed to always sample the string 1, 0 and never sample any of the other strings. So now we know what a distribution is, and I just want to make one last point, and that is that because this universe U is always going to be a finite set for us, we can actually write down the weights that the distribution assigns to every element in U and represent the entire distribution as a vector. So here, for example, if we look at the universe of all 3-bit strings, we can literally write down the weight that the distribution assigns to the string 0, 0, 0, then the weight that the distribution assigns to the string 0, 0, 1, and so on and so forth. And you can see that we can write this as a vector. In this case, it'll be a vector of dimension 8. There are 8 strings of 3 bits. And as a result, basically, the entire distribution is captured by this vector of 8 real numbers in the interval 0 to 1. The next thing I want to do is define the concept of an event. So consider a subset A of our universe, and I'll define the probability of this subset to be simply the sum of the weights of all the elements in the set A. In other words, I'm summing over all x in A the weight of these elements x in the set A. Now, because the sum over the entire universe of all weights needs to be 1, this means that if we look at the probability of the entire universe, basically we get 1. And if we look at the probability of a subset of the universe, we're going to get some number in the interval 0 to 1. And we say that the probability of this set A is the sum, which is a number between 0 and 1. And I'll tell you that a subset A of the universe is called an event, and the probability of the set A is called the probability of that event. So let's look at a simple example. So suppose we look at the universe U, which consists of all 8-bit strings, right? So the size of this universe U is 256 because there are 256 8-bit strings. Essentially, we're looking at all byte values, all 256 possible byte values. Now, let's define the following event. Basically, the event is going to contain all bytes, so all 8-bit strings in our universe, such that the 2 least significant bits of the byte happens to be 1, 1. So for example, if we look at 0, 1, 0, 1, 1, 0, 1, 0, that's an element in the universe that's not in the set A. But if we change this 0 to a 1, then that's an element in the universe which is in our set A. And now let's look at the uniform distribution over the universe U. And let me ask you, what is the probability of the event A? So what is the probability that when we choose a random byte, the 2 least significant bits of that byte happens to be 1, 1? Well, the answer is 1/4. And the reason that's true is because it's not too difficult to convince yourself that of the 256 8-bit strings, exactly 64 of them, 1/4 of them, end in 1, 1. And the probability of each string, since we're looking at the uniform distribution, the probability of each string is exactly 1 over the size of the universe, namely 1 over 256. And the product of these 64 elements, each one has weight 1 over 256, is exactly 1/4, which is the probability of the event A that we were looking at. So a very simple bound on the probability of events is called the union bound. So imagine we have 2 events, A1 and A2. So these are both subsets of some universe U. And we want to know what is the probability that either A1 occurs or A2 occurs. In other words, what is the probability of the union of these 2 events? This little U here denotes the union of the 2 sets. So the union bound tells us that the probability that either A1 occurs or A2 occurs is basically less than the sum of the 2 probabilities. And that's actually quite easy to see. So simply look at this picture here. You can see that when we look at the sum of the 2 probabilities, we're basically summing the probability of all the elements in A1, all the elements in A2, and you realized we kind of double summed these elements in the intersection. They get summed twice here on the right-hand side. And as a result, the sum of the 2 probabilities is actually going to be larger than or equal to the actual probability of the union of A1 and A2. So that's the classic union bound. And in fact, I'll tell you that if the 2 events are disjoint, in other words, their intersection is empty, in that case, if we look at the sum, at the probability that either A1 happens or A2 happens, that's exactly equal to the sum of the 2 probabilities. Okay, so we'll use these facts here and there throughout the course. So just to be clear, the inequality holds always, but when the two events are disjoint, then in fact we get an equality over here. So let's look at a simple example. Suppose our event A1 is the set of all n-bit strings that happen to end in 1, 1. And suppose A2 is the set of all n-bit strings that happen to begin with 1, 1. Okay, so n, think of it as 8 or some large number. And I'm asking now, what is the probability that either A1 happens or A2 happens? In other words, if I sample uniformly from the universe U, what is the probability that either the least significant bits are 1, 1 or the most significant bits are 1, 1? Well, as we said, that's basically the probability of the union of A1 and A2. We know that the probability of each one of these events is 1/4 by what we just did on the previous slide. And therefore, by the union bound, the probability of the OR is, 1/4, the probability of A1 plus the probability of A2, which is 1/4 plus 1/4. And we just proved that the probability of seeing 1, 1 in the most significant bit or 1, 1 in the least significant bit is less than 1/2. So that's a simple example of how we might go about using the union bound to bound the probability that one of two events might happen. The next concept we need to define is what's called a random variable. Now, random variables are fairly intuitive objects, but unfortunately the formal definition of a random variable can be a little confusing. So what I'll do is I'll give an example, and hopefully that will be clear enough. So formally, a random variable, denoted say by x, is a function from the universe into some set v. And we say that this set v is where the random variable takes its values. So let's look at a particular example. So suppose we have a random variable x, and this random variable maps into the set 0, 1. So the values of this random variable are going to be either 0 or 1, so 1 bit basically. Now this random variable maps our universe, which is the set of all n-bit binary strings, 0, 1 to the n. And how does it do it? Well, given a particular sample in the universe, a particular n-bit string y, what the random variable will do is simply output the least significant bit of y. And that's it. That's the whole random variable. So now let me ask you, suppose we look at the uniform distribution on the set 0, 1 to the n. Let me ask you, what is the probability that this random variable outputs 0, and what is the probability that the random variable outputs 1? Well, you can see the answers are half and half, but let's just reason through why that's the case. So here we have a picture showing the universe and the possible output space. And so in this case, the variable can output either 0 or 1. Well, when does the variable output 0? The variable outputs 0 when the sample in the universe happens to have its least significant bits be set to 0. And the variable 1 outputs 1 when the sample in the universe happens to have its least significant bit set to 1. Well, if we choose strings uniformly at random, the probability that we choose a string that has its least significant bit set to 0 is exactly 1/2, which is why the random variable outputs 0 with probability exactly 1/2. Similarly, if we choose a random n-bit string, the probability that the least significant bit is equal to 1 is also 1/2, and so we say that the random variable outputs 1 also with exactly probability 1/2. Now, more generally, if we have a random variable taking values in a certain set v, then this random variable actually induces a distribution on the set v. And here I just wrote in symbols what this distribution means, but it's actually very easy to explain. Essentially what it says is that the variable outputs v basically with the same probability that if we sample a random element in the universe and then we apply the function x, we ask how likely is it that the output is actually equal to v. So formally we say that the probability that x outputs v is the same as the probability of the event that when we sample a random element in the universe, we fall into the pre-image of v under the function x. And again, if this wasn't clear, it's not that important. All you need to know is that a random variable takes values in a particular set v and it induces a distribution on that set v. Now, there's a particularly important random variable called a uniform random variable, and it's basically defined as you would expect. So let's say that U is some finite set, for example, the set of all n-bit binary strings, and we're going to denote a random variable R that's basically samples uniformly from the set U by this little funny arrow with a little R on top of it. And this, again, denotes that the random variable R is literally a uniform random variable sampled over the set U. So in symbols, what this means is that for all elements A in the universe, the probability that R is equal to A is simply 1 over U. And if you want to stick to the formal definition of a uniform variable, it's actually not that important. But I'll just say that formally the uniform random variable is just an identity function, namely Rx is equal to x for all x in the universe. So just to see that this is clear, let me ask you a simple puzzle. Suppose we have a uniform random variable over 2-bit strings, so over the sets 0, 0, 0, 1, 1, 0, and 1, 1. And now let's define a new random variable x to basically sum the first and second bits of R. That is, x simply is the sum of R1 and R2, the first and second bits of R, treating those bits as integers. So for example, if R happens to be 0, 0, then x will be 0 plus 0, which is 0. So let me ask you, what is the probability that x is equal to 2? So it's not difficult to see that the answer is exactly 1/4, because basically the only way that x is equal to 2 is if R happens to be 1, 1, but the probability that R is equal to 1, 1 is basically 1/4, because R is uniform over the set of all 2-bit strings. The last concept I want to define in this segment is what's called a randomized algorithm. So I'm sure you're all familiar with deterministic algorithms. These are algorithms that basically take a particular input data as input, and they always produce the same output, say y. So if we run the algorithm 100 times on the same input, we'll always get the same output. So you can think of a deterministic algorithm as a function that, given a particular input data m, will always produce exactly the same output, a of m. A randomized algorithm is a little different in that it, as before, it takes the input data m as input, but it also has an implicit argument called r, where this r is sampled anew every time the algorithm is run. And in particular, this r is sampled uniformly at random from the set of all n-bit strings for some arbitrary n. Now what happens is every time we run the algorithm on a particular input m, we're going to get a different output because a different r is generated every time. So the first time we run the algorithm, we get one output. The second time we run the algorithm, a new r is generated and we get a different output. The third time we run the algorithm, a new r is generated and we get a third output, and so on. So really the way to think about a randomized algorithm is it's actually defining a random variable, right? So given a particular input message m, it's defining a random variable which is defining a distribution over the set of all possible outputs of this algorithm given the input m. So the thing to remember is that the output of a randomized algorithm changes every time you run it, and in fact the algorithm defines a distribution and the set of all possible outputs. So let's look at a particular example. So suppose we have a randomized algorithm that takes as input a message m, and of course it also takes an implicit input, which is this random string that is used to randomize its operation. So now what the algorithm will do is simply will encrypt the message m using the random string as input. So this basically defines a random variable. This random variable takes values that are encryptions of the message m, and really what this random variable is, it's a distribution over the set of all possible encryptions of the message m under a uniform key. So the main point to remember is that even though the input to a randomized algorithm might always be the same, every time you run the randomized algorithm, you're going to get a different output. Okay, so that concludes this segment, and we'll see a bit more discrete probability in the next segment. In this segment, we're going to continue with a few more tools from discrete probability, and I want to remind everyone that if you want to read more about this, there's more information in this Wikibooks article that is linked over here. So first, let's do a quick recap of where we are. We said that discrete probability is always defined over a finite set, which we're going to denote by u, and typically for us, u is going to be the set of all n-bit binary strings, which we denote by 0, 1 to the n. Now a probability distribution p over this universe u is basically a function that assigns to every element in the universe a weight in the interval 0 to 1, such that if we sum the weight of all these elements, the sum basically sums up to 1. Now we said that a subset of the universe is what's called an event, and we said that the probability of an event is basically the sum of all the weights of the elements in the event. And we said that the probability of an event is some real number in the interval 0 to 1. And I want to remind everyone that basically the probability of the entire universe is basically 1 by the fact that the sum of all the weights sums up to 1. Then we define what a random variable is. Formally, a random variable is a function from the universe to some other set. But the thing that I want you to remember is that the random variable takes values in some set V, and in fact, a random variable defines a distribution on this set V. So the next concept we need is what's called independence, and I'm going to very briefly define this. If you want to read more about independence, please go ahead and look at the Wikibooks article. But essentially, we say that two events A and B are independent of one another if, when you know that event A happens, that tells you nothing about whether event B actually happened or not. Formally, the way we define independence is to say that the probability of A and B, namely that both events happen, is actually equal to the probability of event A times the probability of event B. So multiplication, in some sense, the fact that probabilities multiply under conjunction, captures the fact that these events are independent. And as I said, if you want to read more about that, please take a look at the background material. Now, the same thing can be said for random variables. So suppose we have two random variables, x and y, they take values in some set V. Then we say that these random variables are independent if the probability that x is equal to A and y is equal to B is equal to the product of these two probabilities. Basically, what this means is even if you know that x is equal to A, that tells you nothing about the value of y. Okay, that's what this multiplication means. And again, this needs to hold for all A and B in the space of values of these random variables. So just again, to jog your memory, if you've seen this before, a very quick example. Suppose we look at the set of 2-bit strings, so 0, 0, 0, 1, 1, 0, and 1, 1. And suppose we choose a random element from this set. Okay, so we randomly choose one of these four elements with equal probability. Now let's define two random variables. X is going to be the least significant bit that was generated, and y is going to be the most significant bit that's generated. So I claim that these random variables, x and y, are independent of one another. And the way to see that intuitively is to realize that choosing R uniformly from the set of four elements is basically the same as flipping a coin, an unbiased coin, twice. The first bit corresponds to the outcome of the first flip, and the second bit corresponds to the outcome of the second flip. And of course, there are four possible outcomes. All four outcomes are equally likely, which is why we get the uniform distribution over 2-bit strings. Now, variables x and y, why are they independent? Basically, if I tell you the result of the first flip, namely I tell you the least significant bit of R, so I tell you how the first coin, whether it fell on its head or fell on its tail, that tells you nothing about the result of the second flip. Which is why intuitively you might expect these random variables to be independent of one another. But formally, we would have to prove that for all 0, 1 pairs, the probability of x equals 0 and y equals 0, x equals 1, y equals 1, and so on, these probabilities multiply. Let's just do it for one of these pairs. So let's look at the probability that x is equal to 0 and y is equal to 0. Well, you see that the probability that x is equal to 0 and y is equal to 0 is basically the probability that R is equal to 0, 0. And what's the probability that R is equal to 0, 0? Well, by the uniform distribution, that's basically equal to 1/4. That's 1 over the size of the set, which is 1/4 in this case. And well, lo and behold, that's in fact these probabilities multiply because, again, the probability that x is equal to 0, the probability that the least significant bit of R is equal to 0, this probability is exactly 1/2, because there are exactly two elements that have their least significant bit equal to 0. 2 out of 4 elements gives you a probability of 1/2. And similarly, the probability that y is equal to 0 is also 1/2, so in fact the probabilities multiply. Okay, so that's this concept of independence. And the reason I wanted to show you that is because we're going to look at an important property of XOR that we're going to use again and again. So before we talk about XOR, let me just do a very quick review of what XOR is. So of course, XOR of 2 bits means the addition of those bits modulo 2. So just to kind of make sure everybody's on the same page, if we have 2 bits, so 0, 0, 0, 1, 1, 0, and 1, 1, their XOR, the truth table of the XOR, is basically just the addition modulo 2. You can see 1 plus 1 is equal to 2, modulo 2, that's equal to 0. So this is the truth table for the XOR, and I'm always going to denote XOR by this circle with a plus inside. And then when I want to apply XOR to bit strings, I apply the addition modulo 2 operation bitwise. So for example, the XOR of these two strings would be 1, 1, 0, and I guess I'll let you fill out the rest of the XORs just to make sure we're all on the same page. So of course it comes out to 1, 1, 0, 1. Now we're going to be doing a lot of XORing in this class. In fact, there's a classical joke that the only thing cryptographers know how to do is just XOR things together. But I want to explain to you why we see XOR so frequently in cryptography. Basically, XOR has a very important property, and the property is the following. Suppose we have a random variable y that's distributed arbitrarily over 0, 1 to the n. So we know nothing about the distribution of y. But now suppose we have an independent random variable that happens to be uniformly distributed also over 0, 1 to the n. So it's very important that x is uniform and that it's independent of y. So now let's define the random variable, which is the XOR of x and y. Then I claim that no matter what distribution y started with, this z is always going to be a uniform random variable. So in other words, if I take an arbitrarily malicious distribution and I XOR it with an independent uniform random variable, what I end up with is a uniform random variable. Okay, and this is again kind of a key property that makes XOR very useful for crypto. So this is actually a very simple fact to prove. Let's just go ahead and do it. Let's just prove it for 1 bit, so for n equals 1. Okay, so the way we'll do it is we'll basically write out the probability distributions for the various random variables. So let's see, for the random variable y, well, the random variable can be either 0 or 1. And let's say that P0 is the probability that it's equal to 0, and P1 is the probability that it's equal to 1. Okay, so that's one of our tables. Similarly, we're going to have a table for the variable x. Well, the variable x is much easier. That's a uniform random variable, so the probability that it's equal to 0 is exactly 1/2. Probability that it's equal to 1 is also exactly 1/2. Now let's write out the probabilities for the joint distribution. In other words, let's see what the probability is for the various joint values of y and x. In other words, how likely is it that y is 0 and x is 0, y is 0 and x is 1, y is 1 and x is 0, and 1, 1. Well, so what we do is basically, because we assume the variables are independent, all we have to do is multiply the probabilities. So the probability that y is equal to 0 is P0, probability that x is equal to 0 is 1/2, so the probability that we get 0, 0 is exactly P0 over 2. Similarly, for 0, 1, we'll get P0 over 2. For 1, 0, we'll get P1 over 2. And for 1, 1, again, the probability that y is equal to 1 and x is equal to 1, well, that's P1 times the probability that x is equal to 1, which is 1/2, so it's P1 over 2. Okay, so those are the 4 probabilities for the various options for x and y. So now let's analyze what is the probability that z is equal to 0. Well, the probability that z is equal to 0 is basically the same as the probability that, let's write it this way, xy is equal to 0, 0, or xy is equal to 1, 1. Those are the 2 possible cases that z is equal to 0 because z is the XOR of x and y. Now these events are disjoint, so this expression can simply be written as the sum of the 2 expressions given above. So basically it's the probability that xy is equal to 0, 0 plus the probability that xy is equal to 1, 1. So now we can simply look up these probabilities in our table. So the probability that xy is equal to 0, 0 is simply P0 over 2. And the probability that xy is equal to 1, 1 is simply P1 over 2. So we get P0 over 2 plus P1 over 2. But what do we know about P0 and P1? Well, it's a probability distribution. Therefore, P0 plus P1 must equal 1. And therefore, this fraction here must equal to 1/2. P0 plus P1 is equal to 1. So therefore, the sum of these 2 terms must equal 1/2. And we're done. Basically, we proved that the probability that z is equal to 0 is 1/2. Therefore, the probability that z is equal to 1 is also 1/2. Therefore, z is a uniform random variable. So this simple theorem is the main reason why XOR is so useful in cryptography. The last thing I want to show you about discrete probability is what's called the birthday paradox. And I'm going to do it really fast here because we're going to come back later on and talk about this in more detail. So the birthday paradox says the following. Suppose I choose n random variables in our universe U. Okay, and it just so happens that these variables are independent of one another. They actually don't have to be uniform. All we need to assume is that they're distributed in the same way. The most important property, though, is that they're independent of one another. So the theorem says that if you choose roughly the square root of the size of u elements, we're kind of ignoring this 1.2 here, it doesn't really matter, but if you choose square root of the size of u elements, then basically there's a good chance that there are two elements that are the same. In other words, if you sample about square root of u times, then it's likely that two of your samples will be equal to one another. And by the way, I should point out that this inverted e just means exists. So there exists indices I and j such that Ri is equal to Rj. So here's a concrete example that we'll actually see many, many times. So suppose our universe consists of all strings of length 128 bits. So the size of u is gigantic. It's actually 2 to the 128. It's a very, very large set. But it so happens that if you sample, say, around 2 to the 64 times from the set, this is about the square root of u, then it's very likely that two of your sample messages will actually be the same. So why is this called the birthday paradox? Well, traditionally it's described in terms of people's birthdays, so you would think that each one of these samples would be someone's birthday. And so the question is, how many people need to get together so that there are two people that have the same birthday? So just as a simple calculation, you can see there are 365 days in the year, so you would need about 1.2 times the square root of 365 people until the probability that two of them have the same birthday is more than a half. This, if I'm not mistaken, is about 24, which means that if 24 random people get together in a room, it's very likely that two of them will actually have the same birthday. This is why it's called a paradox, because 24 supposedly is a smaller number than you would expect. Interestingly, people's birthdays are not actually uniform across all 365 days in the year. There's actually a bias towards September, but I guess that's not relevant to the discussion here. The last thing I wanted to do is just show you the birthday paradox a bit more concretely. So suppose we have a universe of about 1 million samples. Then you can see that when we sample roughly 1,200 times, the probability that we sample the same element twice is roughly a half. But the probability of sampling the same number twice actually converges very quickly to 1. You can see that if we sample about 2,200 items, then the probability that two of those items are the same already is 90%. And at 3,000, it's basically 1. So this converges very quickly to 1 as soon as you go beyond the square root of the size of the universe. So we're going to come back and study the birthday paradox in more detail later on, but I just for now wanted you to know what it is. So that's the end of this segment, and then in the next segment we'll start with our first example encryption systems.
Now that we've seen a few examples of historic ciphers, all of which are badly broken, we're going to switch gears and talk about ciphers that are much better designed. But before we do that, I want to first of all define more precisely what a cipher is. So first of all, a cipher is actually, remember, a cipher is made up of two algorithms. There's an encryption algorithm and a decryption algorithm. But in fact, a cipher is defined over a triple. So there's the set of all possible keys, which I'm going to denote by script k. This sometimes I'll call this the key space, the set of all possible keys. There's the set of all possible messages, and the set of all possible ciphertexts. Okay, so this triple, in some sense, defines the environment over which the cipher is defined. And then the cipher itself is a pair of efficient algorithms, E and D. E is the encryption algorithm, D is the decryption algorithm. Of course, E takes keys and messages and outputs ciphertexts. And the decryption algorithm takes keys and ciphertexts and outputs messages. And the only requirement is that these algorithms are consistent. They satisfy what's called a correctness property. So for every message in the message space and every key in the key space, it had better be the case that if I encrypt the message with the key k, and then I decrypt using the same key k, I had better get back the original message that I started with. So this equation here is what's called the consistency equation, and every cipher has to satisfy it in order to be a cipher. Otherwise, it's not possible to decrypt. One thing I wanted to point out is that I put the word efficient here in quotes, and the reason I do that is because efficient means different things to different people. If you're more inclined towards theory, efficient means runs in polynomial time. So algorithms E and D have to run in polynomial time in the size of their inputs. If you're more practically inclined, efficient means runs within a certain time period. So for example, algorithm E might be required to take under a minute to encrypt a gigabyte of data. Either way, the word efficient kind of captures both notions, and you can interpret it in your head whichever way you like. I'm just going to keep referring to it as efficient and put quotes in it. As I said, if you're theory inclined, think of it as polynomial time, and otherwise think of it as concrete time constraints. Another comment I want to make is that in fact algorithm E is often a randomized algorithm. What that means is that as you're encrypting messages, algorithm E is going to generate random bits for itself, and it's going to use those random bits to actually encrypt the messages that are given to it. On the other hand, the decryption algorithm is always deterministic. In other words, given the key and the ciphertext, output is always the same. Doesn't depend on any randomness that's used by the algorithm. Okay, so now that we understand what a cipher is better, I want to kind of show you the first example of a secure cipher. It's called the one-time pad. It was designed by Vernam back at the beginning of the 20th century. Before I actually explain what the cipher is, let's just state it in the terminology that we've just seen. So the message space for the Vernam cipher for the one-time pad is the same as the ciphertext space, which is just the set of all n-bit binary strings. So this just means all sequences of bits of 0, 1 characters. The key space is basically the same as the message space, which is again simply the set of all n-bit binary strings. So a key in the one-time pad is simply a random bit string, so it's a random sequence of bits that's as long as the message to be encrypted, as long as the message. Okay, now that we specified kind of what the cipher is defined over, we can actually specify how the cipher works, and it's actually really simple. So essentially, the ciphertext, which is the result of encrypting a message with a particular key, is simply the XOR of the two, simply K XOR M. So see a quick example of this. Remember that XOR, this plus with a circle, XOR means addition modulo 2. So if I take a particular message, say 0, 1, 1, 0, 1, 1, 1, and I take a particular key, say 1, 0, 1, 1, 0, 0, 1, when I compute the encryption of the message using this key, all I do is I compute the XOR of these two strings. In other words, I do addition modulo 2 bit by bit. So I get 1, 1, 0, 1, 1, 1, 0. That's the ciphertext. And then how do I decrypt? I basically kind of do the same thing. So to decrypt a ciphertext using a particular key, what I do is I XOR the key and the ciphertext again. And so all we have to verify is that it satisfies the consistency requirements. And I'm going to do this slowly once, and then from now on I'm going to assume this is all simple to you. So we're going to have to make sure that if I decrypt a ciphertext that was encrypted using a particular key, I had better get back the message M. So what happens here? Well, let's see. So if I look at the encryption of K and M, this is just K XOR M by definition. What's the decryption of K XOR M using K? That's just K XOR M. And so since I said that XOR is addition modulo 2, addition is associative, so this is the same as K XOR K XOR M, which is simply, as you know, K XOR K is just 0, and 0 XOR anything is simply M. Okay, so this actually shows that the one-time pad is in fact a cipher, but it doesn't say anything about the security of the cipher. And we'll talk about security of the cipher in just a minute. First of all, let me quickly ask you a question just to make sure we're all in sync. Suppose you're given a message M and the encryption of that message using the one-time pad. So all you're given is the message and the ciphertext. My question to you is, given this pair, M and C, can you actually figure out the one-time pad key that was used in the creation of C from M? So I hope all of you realize that, in fact, given the message and the ciphertext, it's very easy to recover what the key is. In particular, the key is simply M XOR C. And we'll see that if it's not immediately obvious to you, we'll see why that's the case a little later in the lecture. Okay. All right. So the one-time pad is really cool from a performance point of view. All you're doing is you're XORing the key and the message. So it's a super, super fast cipher for encrypting and decrypting very long messages. Unfortunately, it's very difficult to use in practice. The reason it's difficult to use is the keys are essentially as long as the message. So if Alice and Bob want to communicate securely, so Alice wants to send a message M to Bob, before she begins even sending the first bit of the message, she has to transmit a key to Bob that's as long as that message. Well, if she has a way to transmit a secure key to Bob that's as long as the message, she might as well use that same mechanism to also transmit the message itself. So the fact that the key is as long as the message is quite problematic and makes the one-time pad very difficult to use in practice. Although we'll see that the idea behind the one-time pad is actually quite useful. And we'll see that a little bit later. But for now, I want to focus a little bit on security. So the obvious questions are, why is the one-time pad secure? Why is it a good cipher? Then to answer that question, the first thing we have to answer is, what is a secure cipher to begin with? What makes a cipher secure? Okay, so to study security of ciphers, we have to talk a little bit about information theory. And in fact, the first person to study security of ciphers rigorously is a very famous, the father of information theory, Claude Shannon, and he published a famous paper back in 1949 where he analyzes the security of the one-time pad. So the idea behind Shannon's definition of security is the following. Basically, if all you get to see is the ciphertext, then you should learn absolutely nothing about the plaintext. In other words, the ciphertext should reveal no information about the plaintext. And you see why it took someone who invented information theory to come up with this notion, because he had to formally explain what does information about the plaintext actually mean. Okay? So that's what Shannon did. And so let me show you Shannon's definition. I'll write it out slowly first. So what Shannon said is, suppose we have a cipher ED that's defined over a triple KMNC just as before. So KMNC define the key space, the message space, and the ciphertext space. And we say that the cipher has perfect secrecy if the following condition holds. It so happens that for every two messages, M0 and M1 in the message space, for every two messages, the only requirement I'm going to put on these messages is they have the same length. So we'll see why this requirement is necessary in just a minute. And for every ciphertext in the ciphertext space, okay, so for every pair of messages and for every ciphertext, it had better be the case that if I ask, what is the probability that encrypting M0 with K, encrypting M0 with K gives C, okay, so how likely is it, if we pick a random key, how likely is it that when we encrypt M0 we get C? That probability should be the same as when we encrypt M1. Okay, so the probability of encrypting M1 and getting C is exactly the same as the probability of encrypting M0 and getting C. And this is, as I said, where the key, the distribution, is over the distribution on the key. So the key is uniform in the key space. So K is uniform in K. And I'm often going to write K arrow with a little r above it to denote the fact that K is a random variable that's uniformly sampled in the key space K. Okay, this is the main part of Shannon's definition. And let's think a little bit about what this definition actually says. So what does it mean that these two probabilities are the same? Well, what it says is that if I'm an attacker and I intercept a particular ciphertext C, then in reality, the ciphertext, the probability that the ciphertext is the encryption of M0 is exactly the same as the probability that it's the encryption of M1, because those probabilities are equal. So if all I have is the ciphertext C, that's all I've intercepted, I have no idea whether the ciphertext came from M0 or the ciphertext came from M1, because, again, the probability of getting C is equally likely whether M0 is being encrypted or M1 is being encrypted. So here we have the definition stated again, and I just want to write these properties again more precisely. So let's write this again. So what this definition means is that if I'm given a particular ciphertext, I can't tell where it came from. I can't tell if the message that was encrypted is either M0 or M1. And in fact, this property is true for all messages, for all these M0, for all M0 and M1. So not only can I not tell if C came from M0 or M1, I can't tell if it came from M2 or M3 or M4 or M5, because all of them are equally likely to produce the ciphertext C. So what this means really is that if you're encrypting messages with a one-time pad, then in fact the most powerful adversary, I don't really care how smart you are, the most powerful adversary can learn nothing about the plaintext, learns nothing about the plaintext from the ciphertext. So just to say it in one more way, basically what this proves is that there's no ciphertext only attack on a cipher that has perfect secrecy. Now, ciphertext only attacks actually aren't the only attacks possible, and in fact, other attacks may be possible. But other attacks may be possible. Okay. Now that we understand what perfect secrecy means, the question is, can we build ciphers that actually have perfect secrecy? And it turns out we don't have to look very far. The one-time pad, in fact, has perfect secrecy. So I want to prove to you, this is Shannon's first results, and I want to prove this fact to you. It's a very simple proof, so let's go ahead and look at it and just do it. So we need to kind of interpret, what does it mean? What is this probability that ek of m0 is equal to c? So it's actually not that hard to see that for every message in every ciphertext, the probability that the encryption of m under a key k, the probability that that's equal to c, the probability of a random choice of key, by definition, all that is basically the number of keys, k in script k, such that, well, if I encrypt m with k, I get c. So I literally count the number of such keys, and I divide by the total number of keys. Right? That's what it means that if I choose a random key, that key maps m to c. Right? So it's basically the number of keys that map m to c divided by the total number of keys. This is this probability. So now suppose that we had a cipher such that for all messages in all ciphertext, it so happens that if I look at this number, the number of k in k, such that ekm is equal to c. In other words, I'm looking at the number of keys that map m to c. Suppose this number happens to be a constant. So say it happens to be 2, 3, or 10, or 15. It just happens to be an absolute constant. If that's the case, then by definition, for all m0 and m1, and for all c, this probability has to be the same, because the denominator is the same, the numerator is the same, it's just this constant, and therefore this probability is always the same for all m and c. And so if this property is true, then the cipher has perfect secrecy. Okay, so let's see what can we say about this quantity for the one-time pad. So the question to you is, if I have a message in a ciphertext, how many one-time pad keys are there that map this message m to the ciphertext c? In other words, how many keys are there such that m XOR k is equal to c? So I hope you've all answered 1, and let's see why that's the case. For the one-time pad, if we have that the encryption of k of m under k is equal to c, that basically, well, by definition, that implies that k XOR m is equal to c. But that also simply says that k has to be equal to m XOR c. Yes, I just XOR both sides by m, and I get that k must equal to m XOR c. Okay, so what that says is that for the one-time pad, in fact, the number of keys in k such that ekm is equal to c, that simply is 1, and this holds for all messages and ciphertext. And so again, by what we said before, this says that the one-time pad has perfect secrecy. Perfect secrecy, and that completes the proof of this trivial, very, very simple lemma. Now, the funny thing is that even though this lemma is so simple to prove, in fact, it proves a pretty powerful statement again. This basically says, for the one-time pad, there is no ciphertext-only attack. So unlike the substitution cipher, or the Vigenère cipher, or the rotor machines, all those could be broken by ciphertext-only attack, we've just proved that for the one-time pad, that's simply impossible. Given the ciphertext, you simply learn nothing about the plaintext. However, as we'll see, this is not the end of the story. I mean, are we done? I mean, basically, we're done with the course now, because we have a way to encrypt so that an attacker can't recover anything about our message. So maybe we're done with the course. But in fact, as we'll see, there are other attacks. And in fact, the one-time pad is actually not such a secure cipher. In fact, there are other attacks that are possible, and we'll see that shortly. Okay? So I emphasize again, the fact that it has perfect secrecy does not mean that the one-time pad is a secure cipher to use. Okay, but as we said, the problem with the one-time pad is that the secret key is really long. So if you had a way of communicating the secret key over to the other side, you might as well use that exact same method to also communicate the message to the other side, in which case you wouldn't need a cipher to begin with. Okay, so the problem again is the one-time pad has really long keys, and so the obvious question is, are there other ciphers that have perfect secrecy and possibly have much, much shorter keys? Well, so the bad news is that Shannon, after proving that the one-time pad has perfect secrecy, proved another theorem that says that if in fact a cipher has perfect secrecy, the number of keys in a cipher must be at least the number of messages that the cipher can handle. Okay, so in particular what this means is if I have perfect secrecy, then necessarily the number of keys, or rather the length of my key, must be greater than the length of the message. So in fact, since the one-time pad satisfies this with equality, the one-time pad is an optimal cipher that has perfect secrecy. Okay, so basically what this shows is that this is an interesting notion. The one-time pad is an interesting cipher, but in fact, in reality, it's actually quite hard to use. Hard to use in practice, again, because of these long keys. And so this notion of perfect secrecy, even though it's quite interesting, basically says that it doesn't really tell us that practical ciphers are going to be secure. And we're going to see, but as we said, the idea behind the one-time pad is quite good, and we're going to see in the next lecture how to make that into a practical system.
Now that we know about the one-time pad, let's talk about making the one-time pad more practical using something called the stream cipher. But before we do that, let's do a quick review of where we were. So let me just remind you that a cipher is defined over a triple of sets called a key space, a message space, and a ciphertext space. And a cipher is a pair of efficient algorithms called E and D. E stands for encryption and D stands for decryption. And the only property that we need to satisfy is that decryption is the opposite of encryption. In other words, if I encrypt a message M using a particular key and I decrypt using the same key, I get back the original message. Last time we looked at a couple of weak ciphers like the substitution cipher and the Vigenère cipher. We showed that all of them can be easily broken, so you should never, ever, ever use those ciphers. Those were just for historical reference. And then we looked at our first example of a good cipher, namely the one-time pad. Let me just remind you how the one-time pad is defined. Basically, the message space is the set of all n-bit strings. The ciphertext is the set of all n-bit strings, and similarly, the key is the set of all n-bit strings. And the way we encrypt is by a simple XOR. To encrypt the message, we just XOR the message and the key. That gives us the ciphertext. And then to decrypt the ciphertext, we just do this XOR again. And it's easy to show by properties of XOR that, in fact, decryption is the opposite of encryption. And then we talked about this lemma. In fact, we proved it. That says that the one-time pad has perfect secrecy, which means that if you're just an eavesdropper and you just get to see a single ciphertext, you're not going to be able to deduce any information about the encrypted plaintext. Unfortunately, we also said that Shannon proved this lemma. We called it the bad news lemma, that basically says that any cipher that has perfect secrecy must have really long keys. In other words, the key length must be at least as long as the length of the message, which means that the cipher is not particularly useful, because if two parties have a way to agree on really long keys that are as long as the message, they, in some sense, might as well use that mechanism to already transmit the message itself. So in this lecture, we're going to take the idea of the one-time pad and try to make it into a practical encryption scheme. So this is what's called a stream cipher. So the idea in a stream cipher is, rather than using a totally random key, we're actually going to use a pseudo-random key. And to explain how that works, I need to define what is a pseudo-random generator, a PRG. So a PRG, really, all it is just a function, and I'll call it G for generator, that takes a seed. So I'm going to use 0, 1 to the s to denote all strings of length s. So this we'll call the seed space. So it takes an s-bit seed and maps it into a much larger string, which we'll denote by 0, 1 to the n. And the property is that n must be much, much larger than s. So in other words, we take a seed that might be maybe only 128 bits, and we expand it into a much, much larger output string that could be gigabytes long. That's what this pseudo-random generator does. And of course, the goal is that, first of all, the generator is efficiently computable. So the function g, there should be some sort of an efficient algorithm that computes it. So efficiently computable by a deterministic algorithm. It's important to understand that the function g itself has no more randomness in it. It's totally deterministic. The only thing that's random here is the random seed that's given as input to the function g. And the other property, of course, is that the output should look random. And the question is, what does it mean to look random? And that's something that we'll define later on in the lecture. Okay, so suppose we have such a generator. How do we use that to build a stream cipher? Well, the idea is that we're going to use the seed as our key. So our short seed is going to be the secret key. And then we're going to use the generator to basically expand the seed into a much, much larger random-looking sequence, or pseudo-random sequence, as it's known. So this would be g of k. And then we are going to XOR it, just like in the one-time pad. We're going to XOR the pseudo-random sequence with the message, and that's going to give us the ciphertext. Or if we want to write this in math, we'll write C equals the encryption of the message M with a key K, which is simply defined as M XOR G of K. And then when we want to decrypt, basically we do exactly the same thing. It's basically the ciphertext XOR G of K, just like in the one-time pad, except that instead of XORing with K, we XOR with the output of the generator applied to K. So the first question to ask is, why is this secure? So basically, we only have one notion of security so far, which we called perfect secrecy. And so let's just quickly ask, can a stream cipher have perfect secrecy? Remember, in the stream cipher, the key is much, much shorter than the message. And so nevertheless, can it have perfect secrecy? So I hope everybody said the answer is no. The key is much shorter than the message, and we said that in a perfectly secure cipher, the key must be as long as the message, and therefore it's not possible that a stream cipher actually has perfect secrecy. So the question is then, well, why is it secure? First of all, we would need a different definition of security to argue that the stream cipher is secure, and in particular, the security property is going to depend on the specific generator that we used. So in fact, the definition of privacy that we'll need to argue security of stream ciphers we'll see in the next lecture. But for now, let me show you one particular property that a generator must have, a minimal property needed for security. This property is called unpredictability. So let's just suppose for 1 second that in fact a stream cipher is predictable. So what does that mean? Suppose the PRG is predictable. What that means is essentially that there is some I such that if I give you the first I bits of the output, this notation, bar 1 to I, means look at the first I bits of the output of the function. Okay, so I give you the first I bits of the stream. There is some sort of an algorithm, there's an efficient algorithm that will compute the rest of the stream. Okay, so given the first I bits, you can compute the remainder of the bits. I claim that if this is the case, then the stream cipher would not be secure. So let's see why. Well, suppose an attacker actually intercepts a particular ciphertext, let's call it C. Right, if this is the case, then in fact we have a problem. Because suppose that just by some prior knowledge, the attacker actually knows that the initial part of the message happens to be some known value. For example, you know that in the mail protocol, SMTP, the standard send mail protocol used in the internet, you know that every message starts with a word from colon. Well, that would be a prefix that the adversary knows that the message must begin with, from colon. What it could do is it could XOR the ciphertext with the words from colon, with the little prefix of the message that it actually knows, and what that would give it is a prefix of the pseudo-random sequence. So now it would learn as a result of this, it would learn a prefix of the pseudo-random sequence. But then we know that once it has a prefix of the pseudo-random sequence, it can predict the remainder of the pseudo-random sequence, and that would allow it to then predict the rest of the message M. Okay, so for example, if the pseudo-random generator was predictable given 5 bits of the pad, then every email encrypted using the stream cipher would be decryptable because, again, the attacker knows the prefix of the message, from which he deduces a prefix of the pad, which then allows him to compute the rest of the pad, which then allows him to recover the entire plaintext. Okay, so this is an example that shows that in fact if a PRG is predictable, then already there are security problems because a small prefix would reveal the entire message. As it turns out, even if I could just predict one bit of the output, even if given the first I bits, I can predict the next bit, the I plus first bit, already this is a problem, because that would say that given, again, the first couple of letters in a message, I can decrypt essentially and recover the next bit of the message, or the next letter of the message, and so on. So this predictability property shows that, if we use a PRG that's going to be used in a stream cipher, it had better be unpredictable. So what does it mean that a PRG is unpredictable? So let's define more precisely what it means for a PRG to be unpredictable. Well, first we'll define more precisely what it means for a PRG to be predictable. So we say that G is predictable if there exists an efficient algorithm, let's call it A, and there is some position, there's a position I between 1 and n minus 1, such that if we look at the probability over a random key, probability that if I generate a random key, and remember this notation means choose a random key from the set K, so this arrow with R just means choose a random key from the set K. Basically, if I give this algorithm the prefix of the output, so I give it the first I bits of the output, the probability that it's able to predict the next bit of the output, this probability is greater than half plus epsilon for some non-negligible epsilon. And non-negligible, for example, would be epsilon which is greater than 1 over 2 to the 30. 1 over a billion, for example, we would consider non-negligible. So these terms, negligible and non-negligible, we'll come back at the end of the lecture and define them more precisely. But for now, let's just stick with the intuitive notion of what non-negligible means. And so this is what it means for an algorithm, for a generator to be predictable. Basically, there's some algorithm that is able to predict the I plus first bit, even the initial prefix. Okay? And then we say that an algorithm, that a PRG is unpredictable if in fact, if it doesn't satisfy the property that we just defined. In other words, it is not predictable. But what does it mean more precisely for it not to be predictable? It means that in fact for all positions, for all I, there's no efficient adversary, no efficient algorithm A that can predict the I plus first bit with non-negligible probability epsilon. Okay, and this has to be true for all I. So no matter which prefix I give you, you're not going to be able to predict the next bit that follows the prefix. Okay, so let's look at some examples. Here's a silly example. Suppose I give you a generator and I ask you, is it predictable? Well, this generator happens to have the property that if I XOR all the bits of the output, I always happen to get 1. Okay, so I XOR all the bits, bit number 1, XOR bit number 2, XOR bit number 3. If I XOR all those bits, I happen to get 1. The question is that a predictable generator? And again, I hope everybody answered yes, that essentially given the first n minus 1 bits of the output, I can predict the nth bit because it would just be the bit that's needed to make the XOR of all the bits be 1. In other words, if I give you all but one of the bits of the generator, you can actually predict the last bit of the generator. Now that we've seen that PRGs have to be unpredictable, I just want to mention a couple of weak PRGs. This should never ever be used for crypto. This is a very common mistake, and I just want to make sure none of you guys make this mistake. So a very common PRG that should actually never be used for crypto is called a linear congruential generator. So let me explain what a linear congruential generator is. Basically, it has parameters. It has 3 parameters. I'll call them A, B, and P. A and B are just integers, and P is a prime. And the generator is defined as follows. Essentially, I'll say R0 is the seed of the generator. And then the way you generate randomness is basically you iteratively run through the following steps. You compute A times R of I minus 1 plus B modulo P. Then you output a few bits of the current states, output few bits of Ri. then of course you increment I and you iterate this again and again and again. Okay, so you can see how this generator proceeds. It starts with a particular seed. At every step there is this linear transformation that's being applied to the seed, and then you output a few bits of the current state, and then you do that again and again and again and again. Unfortunately, even though this generator has good statistical properties in the sense that, for example, the number of zeros it outputs is likely going to be similar to the number of ones and so on. You can actually argue all sorts of nice statistical properties about this. Nevertheless, it is a very easy generator to predict, and in fact should never ever be used. In fact, just given a few output samples, it's easy to predict the remainder of the sequence. And as a result, this generator should never ever be used. Another example is a random number generator that's very closely related to the linear congruential generator. This is a random number generator implemented in glibc, very common library, that you can see. I just wrote down the definition here. You can see that it basically outputs a few bits at every iteration, and it just does this simple linear transformation at every step. Again, this is a very easy generator to predict and should never ever be used for crypto. And so kind of the lesson I want to just emphasize here is never ever use the function, the built-in glibc function random for crypto, because it doesn't produce cryptographic randomness in the sense that it's easy to predict. And in fact, systems like Kerberos version 4 have used random and have been bitten by that. So please don't make that mistake yourself. We'll talk about how to do secure random number generation actually in the next lecture. Before we conclude this lecture, I just want to give a little bit more detail about these concepts of negligible and non-negligible values. So different communities in crypto actually define these concepts differently. For practitioners, basically the terms negligible and non-negligible are just particular scalars that are used in the definition. So for example, a practitioner would say that if a value is more than 1 over a billion, 1 over 2 to the 30, we say that the value is non-negligible. The reason that's so is because if you happen to use a key, for example, for encrypting a gigabyte of data is about 2 to the 30, or maybe even 2 to the 32 bytes, then an event that happens with probability 1 over 2 to the 30 will likely happen after about a gigabyte of data. So since a gigabyte of data is within reason for a particular key, this event is likely to happen. Therefore, 1 over 2 to the 30 is non-negligible. On the other hand, we'll say that 1 over 2 to the 80, which is much, much, much smaller, is an event that happens with this probability, is an event that's actually not going to happen over the life of the key, and therefore we'll say that that's a negligible event. As it turns out, these practical definitions of negligible and non-negligible are quite problematic, and we'll see examples of why they're problematic later on. So in fact, in the more rigorous theory of cryptography, the definition of negligible and non-negligible are somewhat different. And in fact, when we talk about the probability of events, we don't talk about these probabilities as scalars, but rather we talk about them as functions of a security parameter. So let me explain what that means. So these functions are essentially functions that output positive real values, or non-negative real values that are supposedly probabilities, but they're functions that act on non-negative integers. Okay, so what does it mean for a function to be non-negligible? What it means is that the function is bigger than some polynomial infinitely often. In other words, for infinitely many values, the function is bigger than some 1 over polynomial. Okay, so I wrote the exact definition here, and we'll see an example in just a minute. Okay, so if something is often bigger than 1 over a polynomial, we'll say that it's not negligible. However, if something is smaller than all polynomials, then we'll say that it's negligible. So what this says here is basically for any degree polynomial, for all d, there exists some lower bound lambda d such that for all lambda bigger than this lambda d, the function is smaller than 1 over the polynomial. Okay, so all this says is that the function is negligible if it's less than all polynomial fractions. In other words, it's less than 1 over lambda d for sufficiently large lambda. So let's look at some examples, and we'll see applications of these negligible and non-negligible concepts later on, but I just wanted to make it clear that this is how you would rigorously define these concepts. Basically, either smaller than 1 over poly or bigger than 1 over poly. One would be negligible, the other would be non-negligible. Let's look at some examples. So for example, a function that drops exponentially in lambda clearly would be negligible because for any constant d, there is a sufficiently large lambda such that 1 over 2 to the lambda is less than 1 over lambda to the d. Okay, so this is clearly less than all polynomials. However, the function, say, 1 over lambda to 1,000, right? This is a function that grows very, very, very slowly. It barely ever moves. Nevertheless, this function is non-negligible because if I set d to be 10,000, then clearly this function is bigger than 1 over lambda to the 10,000. And so this function is bigger than some polynomial fraction. Now let's look at a confusing example, just to be tricky. What do you think? If suppose I have a function that for odd lambda happens to be exponentially small, for even lambda happens to be polynomially small, is this a negligible or non-negligible function? Well, by our definition, this would be a non-negligible function. And the intuition is if a function happens to be only polynomially small very often, that actually means that this event, an event that happens with this probability, is already too large to be used in a real crypto system. Okay, so the main points to remember here are that these terms basically correspond to less than polynomial or more than polynomial. But throughout the course, we'll mostly use negligible to mean less than an exponential, and non-negligible to mean less than 1 over polynomial. So now we saw the core idea for converting the one-time pad into a practical cipher, namely a stream cipher. And then in the next lecture, we're going to see how to actually argue that the stream cipher is actually secure. That's going to require a new definition of security, since perfect secrecy is not good enough here. And we will see that in the next lecture. In this segment, we're going to look at attacks on the one-time pad and some things you need to be careful with when you use the stream cipher. But before we do that, let's do a quick review of where we were. So recall that the one-time pad encrypts messages by XORing the message and a secret key, where the secret key is as long as the message. Similarly, decryption is done by similarly XORing the ciphertext and the same secret key. When the key is uniform and random, we prove that the one-time pad has this information theoretic security that Shannon called perfect secrecy. The problem was, of course, the keys are as long as the message, so the one-time pad is very difficult to use. We then talked about a way to make the one-time pad practical by using a pseudo-random generator that expands a short seed into a much larger message. And the way a stream cipher worked, essentially using a pseudo-random generator, was in the same way as the one-time pad, basically, but rather than using a truly random pad, we used the pseudo-random pad that's expanded to be as long as the message from the short key that's given as input to the generator. We said now that security no longer relies on perfect secrecy because stream ciphers cannot be perfectly secure. Instead, security relies on properties of the pseudorandom generator. And we said that the pseudorandom generator essentially needs to be unpredictable. But in fact, it turns out that definition is a little bit hard to work with. And we're going to see a better definition of security for PRGs in about 2 segments. But in this segment, we're going to talk about attacks on the one-time pad. And the first attack I want to talk about is what's called the two-time pad attack. Okay, so remember that the one-time pad is called one-time pad because the pad can only be used to encrypt a single message. I want to show you that if the same pad is used to encrypt more than one message, then security goes out the window and basically an eavesdropper can completely decrypt encrypted messages. So let's look at an example. So here we have 2 messages, M1 and M2, that are encrypted using the same pad. So the resulting ciphertext, C1 and C2, again, basically are encryptions of these messages, M1 and M2, but both are encrypted using the same pad. Now suppose an eavesdropper intercepts C1 and C2, and he basically has both C1 and C2. The natural thing for the eavesdropper to do is actually compute the XOR of C1 and C2, and what does he get when he computes this XOR? So I hope everybody sees that basically once you XOR C1 and C2, the pads cancel out, and essentially what comes out of this is the XOR of the plaintext messages. And it turns out that English basically has enough redundancy such that if I give you the XOR of 2 plaintext messages, you can actually recover those 2 messages completely. More importantly for us, since these messages are encoded using ASCII, in fact, ASCII encoding has enough redundancy such that given the XOR of 2 ASCII encoded messages, you can recover the original messages back. Okay, so essentially given these XORs, you can recover both messages. So the thing to remember here is if you ever use the same pad to encrypt multiple messages, an attacker who intercepts the resulting ciphertexts can basically recover the original plaintexts without too much work. So the stream cipher key or the one-time pad key should never, ever, ever, ever be used more than once. So let's look at some examples where this comes up in practice. It's a very common mistake to use a stream cipher key or a one-time pad key more than once. And let me show you some example where this comes up so you know to avoid these mistakes when you build your own systems. The first example is a historic example at the beginning of the 1940s where the Russians actually used a one-time pad to encrypt various messages. Unfortunately, the pads that they were using were generated by a human by throwing dice. And so, the human would throw these dice and write down the results of these throws, and the collected throws would then form the pads that were used for encryption. Now, because it was kind of laborious for them to generate these pads, it seemed wasteful to use the pad to encrypt just one message, so they ended up using these pads to encrypt multiple messages. And US intelligence was actually able to intercept these two-time pads, these ciphertexts that were encrypted using the same pad applied to different messages. And it turns out over a period of several years, they were able to decrypt something like 3,000 plaintexts just by intercepting these ciphertexts. The project is called Project Venona. It's actually a fascinating story of cryptanalysis just because the two-time pad is insecure. More importantly, I want to talk about more recent examples that come up in networking protocols. So let me give you an example from Windows NT in a protocol called the point-to-point transfer protocol. This is a protocol for a client wishing to communicate securely with a server. The client and the server both share a secret key here, and they both send messages to one another. So here we'll denote the messages from the client by M1. So the client sends a message, the server responds, the client sends a message, the server responds, the client sends a message, the server responds, and so on and so forth. Now, the way PTP works is basically the entire interaction from the client to the server is considered as one stream. In other words, what happens is the messages M1 and M2 and M3 are kind of viewed as one long stream. Here, these two parallel lines means concatenation. So essentially, we're concatenating all the messages from the client to the server into one long stream, and all that stream is encrypted using the stream cipher with key K. So that's perfectly fine. I mean, there's nothing wrong with that. These messages are encrypted, are treated as one long stream, and they're all encrypted using the same key. The problem is the same thing is happening also on the server side. In other words, all the messages from the server are also treated as one long stream. So here, they're all concatenated together and encrypted using, unfortunately, the same pseudo-random seed. In other words, using the same stream cipher key. So basically what's happening here is you see an effect that the two-time pad is taking place where the set of messages from the client is encrypted using the same one-time pad as the set of messages from the server. The lesson here is that you should never use the same key to encrypt traffic in both directions. In fact, what you need to do is to have one key for interaction between the client and the server and one key for interaction between the server and the client. The way I like to write this is really that the shared key K really is a pair of keys. One key is used to encrypt messages from server to client, and one key is used to encrypt messages from client to server. So these are two separate keys that are used, and both sides, of course, know this key. So both sides have this pair of keys. Okay, and they can both encrypt. So one is used to encrypt messages in one direction, and the other is used to encrypt messages in the other direction. So another important example of the two-time pad comes up in Wi-Fi communication, in particular in the 802.11b protocol. So all of you, I'm sure, know that 802.11 contains an encryption layer, and the original encryption layer was called WEP. And WEP, fortunately for us, is actually a very badly designed protocol, so that I can always use it as an example of how not to do things. There are many, many mistakes inside of WEP, and here I want to use it as an example of how the two-time pad came about. So let me explain how WEP works. So in WEP, there's a client and an access point. Here's the client, here's the access point. They both share a secret key K. And then when they want to transmit a message to one another, say these are frames that they transmit to one another. Let's say the client wants to send a frame containing the plaintext M to the access point. What he would do is first of all, he appends some sort of a checksum to this plaintext. The checksum is not important at this point. What is important is that then this concatenation gets encrypted using a stream cipher, where the stream cipher key is this concatenation of a value IV and a long-term key K. So this IV is a 24-bit string. Okay, this IV is a 24-bit string. And you can imagine that it starts from 0, and perhaps it's a counter that counts increments by 1 for every packet. The reason they did this is the designers of WEP realized that in a stream cipher, the key is only supposed to be used to encrypt one message. And so they said, well, let's go ahead and change the key after every frame. And the way they changed the key essentially was by prepending this IV to it. And you notice this IV changes on every packet, so it increments by 1 on every packet. And the IV then is sent in the clear along with the ciphertext. So the recipient knows the key K, he knows what the IV is, he can rederive the PRG of IV concatenated K, and then decrypt the ciphertext to recover the original message M. Now the problem with this, of course, is the IV is only 24 bits long, which means that there are only 2 to the 24 possible IVs, which means that after 16 million frames are transmitted, essentially the IV has to cycle. And once it cycles, after 60 million frames, essentially we get a 2-time pad. The same IV would be used to encrypt 2 different messages. The key K never changes. It's a long-term key. And as a result, the same key, namely IV concatenated K, would be used to encrypt 2 different frames, and the attacker can then figure out plaintext of both frames. So that's one problem. And the worst problem is, in fact, that on many 802.11 cards, if you power cycle the card, the IV will reset back to 0. And as a result, every time you power cycle the card, essentially you'll be encrypting the next payload using 0 concatenated K. So after every power cycle, you'll be using the 0 concatenated K key to encrypt many, many, many times the same packet. So you see how in WEP, the same pad could be used to encrypt many different messages as soon as the IV is repeated. There's nothing to prevent the IV from repeating after a power cycle or from repeating after every 16 million frames, which isn't that many frames in a busy network. So while we're talking about WEP, I want to mention one more mistake that was done in WEP. This is a pretty significant mistake, and let's see how we might design it better. So you notice that the designers of WEP basically wanted to use a different key for every packet. Okay, so every frame is encrypted using a different key, this concatenation of IV and K. Unfortunately, they didn't randomize the keys, and the keys are actually, if you look at the key for frame number 1, well, it'll be this concatenation of 1 and K. This field is 24 bits. And then the key for frame number 2 is the concatenation of 2 and K. The key for frame number 3 is the concatenation of 3 and K. So the keys are very closely related to one another. And I should probably mention also that these keys themselves can be 104 bits, so that the resulting PRG key is actually 104 plus 24 bits, which is 128 bits. Unfortunately, these keys are very much related to one another. These are not random keys. You notice they all have the same suffix of 104 bits. And it turns out the pseudorandom generator used in WEP is not designed to be secure when you use related keys that are so closely related. In other words, the majority of these keys are basically the same. And in fact, for the PRG that's used in WEP, that PRG is called RC4. We'll talk about that more in the next segment. It turns out there's an attack that was discovered by Fleurer, Mantin, and Shamir back in 2001 that shows that after about 10 to the 6, after about 1 million frames, you can recover the secret key. You can recover K. So this is kind of a disastrous attack that says essentially all you have to do is listen to about 1 million frames. These frames basically, as we said, they're all generated from a very common seed, namely 104 bits of these seeds are all the same. The fact that you've used such closely related keys is enough to actually recover the original key. And it turns out even after the 2001 attack, better attacks have come out that show that these related keys are very much disastrous, and in fact these days something like 40,000 frames are sufficient. And so that within a matter of minutes, you can actually recover the secret key in any WEP network. So WEP provides no security at all for 2 reasons. First of all, it can result in a 2-time pad, but more significantly, because these keys are so closely related, it's actually possible to recover the key by watching just a few ciphertexts. And by the way, we'll see that when we do a security analysis of these types of constructions, in a few segments we'll start talking about how to analyze these types of constructions. We'll see that when we have related keys like this, in fact, our security analysis will fail. We won't be able to get the proof to go through. So one could ask, what should the designers of web should have done instead? Well, one approach is to basically treat the frames, M1, M2, M3. Each one is a separate frame transmitted from the client to the server. They could have treated them as one long stream and then XOR them essentially using the pseudo-random generator as one long stream. So the first segment of the pad would have been used to encrypt M1, the second segment of the pad would have been used to encrypt M2, the third segment of the pad would have been used to encrypt M3, and so on and so forth. So they basically would never have had to change the key because the entire interaction is viewed as one long stream. But they chose to have a different key for every frame. So if you want to do that, a better way to do that is rather than slightly modifying this IV that just slightly modifies the prefix of the key, of the PRG key, a better way to do that is to use a PRG again. So essentially what you could do is you would take your long-term key and then feed that directly through a PRG. So now we get a long stream of bits that look essentially random. And then the initial segment could be used, the first segment could be used as the key for frame number 1. And then the second segment would be used as the key for, key from frame number 2, and so on and so forth. The third segment would be used to encrypt frame number 3, and so on and so forth. Okay? So the nice thing about this is now essentially by doing this, each frame has a pseudo-random key. These keys now have no relation to one another. They look like random keys. And as a result, if the PRG is secure for random seeds, it would also be secure on this input because these keys essentially look as though they're independent of one another. We'll see how to do this analysis formally once we talk about these types of constructions. Since this two-time pad attack comes up so often in practice, it's such a common mistake, I want to give one more example where it comes up so you know how to avoid it. And the last example I want to give is in the context of disk encryption. So imagine we have a certain file, and maybe the file begins with, the words to Bob. And then the contents of the file follows. When this is stored on disk, of course, the file is going to get, so here we have our disk here. The file is going to get broken into blocks. And each block will be, when we actually store this on disk, things will be encrypted. And, so maybe to Bob will go into the first block, and then the rest of the content will go into the remaining blocks. But of course, this is all encrypted, so I'll kind of use these lines here to denote the fact that this is encrypted, and an attacker looking at the disk has no idea what the contents of the message is. But now suppose that at a later time, user goes ahead and modifies, basically, fires up the editor and modifies the file. So now instead of saying to Bob, it says to Eve, and nothing else changes in the file. That's the only change that was made. When the user then saves this modified file to disk, basically he's going to re-encrypt it again. And so the same thing is going to happen. The file is going to get broken into blocks. Now the file is going to say to Eve, and everything, of course, is going to be encrypted. So again, I'll put these lines here. Now, an attacker looking at the disk, taking a snapshot of the disk before the edit, and then looking again at the disk after the edit, what he will see is that the only thing that changed is this little segment here that's now different. Everything else looks exactly the same. So the attacker, even though he doesn't know what actually happened to the file, what's in the file, or what changed, he knows exactly the location where the edit took place. And so the fact that the one-time pad or a stream cipher encrypts one bit at a time means that if one change takes place, then it's very easy to tell where that change occurred. And that leaks information that the attacker shouldn't actually learn. Ideally, you'd like to say that even if the file changed just a little bit, the entire contents of the file should change, or maybe at least the entire contents of the blocks should change. Here you can see that the attacker even knows within the block where the change was actually made. Okay, so in fact, because of this, it's usually a bad idea to use stream ciphers for disk encryption. And essentially, this is another example of a two-time pad attack because the same pad is used to encrypt two different messages. They happen to be very similar, but nevertheless, these are two different messages, and the attacker can learn what the change was. And in fact, he might be able to even learn what the actual changed words were as a result of this. Okay, so the lesson here is generally we need to do something different for disk encryption. We'll talk about what to do for disk encryption in a later segment, but essentially the one-time pad is generally not a good idea for encrypting blocks on disk. So just again, to summarize the two-time pad attack, we saw that you're supposed, I hope I've convinced you that you're never, ever, ever supposed to use a stream cipher key more than once. Even though there are natural settings where that might happen, you have to take care and make sure that you're not using the same key more than once. So for network traffic, typically what you're supposed to do is every session would have its own key. Within the session, the message from the client to the server would look as one complete stream. It would be encrypted using one key. The messages from the server to the client would be treated as one stream and encrypted using a different key. And then for disk encryption, typically you would not use a stream cipher because as changes are made to the file, you would be leaking information about the contents of the file. Okay, so that concludes our brief discussion of the two-time pad. Next attack I want to mention is the fact that the one-time pad and stream ciphers in general provide no integrity at all. All they do is they try to provide confidentiality when the key is only used once. They provide no integrity at all. But even worse than that, it's actually very easy to modify ciphertexts and have known effects on the corresponding plaintexts. So let me explain what I mean by that. This property, by the way, is called malleability, and we'll see what I mean by that in just a second. So imagine we have some message M that gets encrypted. So here, it gets encrypted using a stream cipher. And the ciphertext, of course, is then going to be M XOR K. Now, an attacker intercepts the ciphertext. Well, that doesn't tell him what the plaintext is. But what he can do is now, beyond eavesdropping, he can actually become an active attacker and modify the ciphertext. So when I say modify the ciphertext, let's suppose that he XORs the ciphertext with a certain value P. Let's call this the perturbation P. Well, the resulting ciphertext then becomes M XOR K XOR P. So now let me ask you, when we decrypt the ciphertext, what is it going to decrypt to? Well, I hope everybody sees that manipulating XORs, basically the decryption becomes M XOR P. So you notice that by XORing with this pad P, the attacker was able to have a very specific effect on the resulting plaintext. Okay? So to summarize this, basically you can modify the ciphertext. These modifications are undetected, but even worse, they're undetected. They have a very specific impact on the resulting plaintext. Namely, whatever you XOR the ciphertext with is going to have that exact effect on the plaintext. So to see where this can be dangerous, let's look at a particular example. Suppose the user sends an email that starts from the words "from Bob." And the attacker basically gets to intercept the corresponding ciphertext. Well, he doesn't know what the ciphertext is, but let's just, for the sake of it, let's pretend that he actually knows that this message is actually from Bob. What he wants to do is he wants to modify the ciphertext so that the plaintext would now look like it came from somebody else. Say he wants to make it look like this message actually came from Alice. All he has is the ciphertext. Well, what he can do is he can XOR it with a certain set of 3 characters. We'll see what those 3 characters are in just a second, such that the resulting ciphertext is actually an encryption of the message from Eve. And so that now when the user decrypts that, all of a sudden he'll see, hey, this message is from Eve. It's not. He'll think this message is from Eve, not from Bob, and that might cause, the wrong thing to take place. So here, the attacker, even though he himself could not have created a ciphertext that says from Eve, by modifying an existing ciphertext, all of a sudden he was able to make the ciphertext that he could not have done without intercepting at least one ciphertext. So again, by intercepting one ciphertext, he was able to change it so now it looks like it's from Eve rather than from Bob. So just to be specific, let's look at what these 3 characters need to be. So let's look at the word Bob, and I'm going to write it in ASCII. So Bob in ASCII corresponds to 42 hex, 6F hex, and 62 hex. So little b is encoded as 62, little o is encoded as 6F. The word Eve is encoded as 45 hex, 76 hex, and 65 hex. Now when I XOR these 2 words, I'm literally going to XOR them as bit strings, so Bob XOR Eve. It's not difficult to see that what I get is the 3 characters 07, 19, and 07. So really what these 3 characters here are going to be are simply 07, 19, and 07. And by XORing these three characters at the right positions into the ciphertext, the attacker was able to change the ciphertext to look like it came from Eve rather than from Bob. So this is an example where having a predictable impact on the ciphertext can actually cause quite a bit of problems. And this is this property called malleability. And we say that the runtime pad is malleable because it's very easy to compute on ciphertexts and make prescribed changes to the corresponding plaintext. So to prevent all this, I'm going to do that actually in 2 or 3 lectures, and we're going to basically show how to add integrity to encryption mechanisms in general. But right now I want you to remember that the one-time pad by itself has no integrity and is completely insecure against attackers that actually modify the ciphertexts. In this segment I want to give a few examples of stream ciphers that are used in practice. I'm going to start with 2 old examples that actually are not supposed to be used in new systems, but nevertheless they're still fairly widely used, and so I just want to mention the names so that you're familiar with these concepts. The first stream cipher I want to talk about is called RC4, designed back in 1987. And I'm only going to give you the high-level description of it, and then we'll talk about some weaknesses of RC4 and leave it at that. So RC4 takes a variable size seed. Here I just gave as an example where it would take 128 bits as the seed size, which would then be used as the key for the stream cipher. The first thing it does is it expands the 128-bit secret key into 2048 bits, which are going to be used as the internal state for the generator. And then once it's done this expansion, it basically executes a very simple loop where every iteration of this loop outputs 1 byte of output. So essentially you can run the generator for as long as you want and generate 1 byte at a time. Now RC4 is actually, as I said, fairly popular. It's used in the HTTPS protocol quite commonly actually. These days, for example, Google uses RC4 in its HTTPS. And it's also used in WEP, as we discussed in the last segment, but of course in WEP it's used incorrectly and it's completely insecure the way it's used inside of WEP. So over the years, some weaknesses have been found in RC4, and as a result, it's recommended that new projects actually not use RC4, but rather use a more modern pseudorandom generator, as we'll discuss towards the end of the segment. So let me just mention 2 of the weaknesses. So the first one is, it's kind of bizarre basically. If you look at the second byte of the output of RC4, it turns out the second byte is slightly biased. If RC4 was completely random, the probability that the second byte happens to be equal to 0 would be exactly 1 over 256. There are 256 possible bytes. The probability that it's 0 should be 1 over 256. It so happens that for RC4, the probability is actually 2 over 256, which means that if you use the RC4 output to encrypt a message, the second byte is likely to not be encrypted at all. In other words, it'll be XORed with 0, with twice the probability that it's supposed to. So 2 over 256 instead of 1 over 256. And by the way, I should say that there's nothing special about the second byte. It turns out the first and the third bytes are also biased. And in fact, it's now recommended that if you're going to use RC4, what you should do is ignore basically the first 256 bytes of the output and just start using the output of the generator starting from byte 257. The first couple of bytes turned out to be biased, so you just ignore them. The second attack that was discovered is that in fact if you look at a very long output of RC4, it so happens that you're more likely to get the sequence 00. In other words, you're more likely to get 16 bits, 2 bytes of 00 than you should. Again, if RC4 was completely random, the probability of seeing 00 would be exactly 1 over 256 squared. It turns out RC4 is a little biased, and the bias is 1 over 256 cubed. It turns out this bias actually starts after several gigabytes of data are produced by RC4, but nevertheless this is something that can be used to predict the generator, and definitely it can be used to distinguish the output of the generator from truly random sequence. Basically, the fact that 00 appears more often than it should gives a distinguisher. And then in the last segment, we talked about related key attacks that were used to attack WEP, that basically say that if one uses keys that are closely related to one another, then it's actually possible to recover the root key. So these are the weaknesses that are known about RC4, and as a result, it's recommended that new systems actually not use RC4 and instead use a modern pseudorandom generator. Okay, the second example I want to give you is a badly broken stream cipher that's used for encrypting DVD movies. When you buy a DVD in the store, the actual movie is encrypted using a stream cipher called the Content Scrambling System, CSS. CSS turns out to be a badly broken stream cipher, and we can very easily break it, and I want to show you how the attack algorithm works. We're doing it so that you can see an example of an attack algorithm, but in fact, there are many systems out there that basically use this attack to decrypt encrypted DVDs. So the CSS stream cipher is based on something that hardware designers like. It's designed to be a hardware stream cipher that's supposed to be easy to implement in hardware, and is based on a mechanism called a linear feedback shift register. So a linear feedback shift register is basically a register that consists of cells where each cell contains 1 bit. And then basically what happens is there are these taps into certain cells, not all the cells, certain positions are called taps. And then these taps feed into an XOR, and then at every clock cycle, the shift register shifts to the left, the last bit falls off, and then the first bit becomes the result of this XOR. So you can see that this is a very simple mechanism to implement in hardware. It takes very few transistors, just a shift right. The last bit falls off, and the first bit just becomes the XOR of the previous bits. So the seed for this LFSR basically is the initial state of the LFSR, and it's the basis of a number of stream ciphers. So here are some examples. So as I said, DVD encryption uses 2 LFSRs. I'll show you how that works in just a second. GSM encryption, these are algorithms called A51 and A52. That uses 3 LFSRs. Bluetooth encryption is an algorithm called E0. These are all stream ciphers, and that uses 4 LFSRs. Turns out all of these are badly broken and actually really should not be trusted for encrypting traffic, but they're all implemented in hardware, so it's a little difficult now to change what the hardware does. But the simplest of these, CSS, actually has a cute attack on it, so let me show you how the attack works. So let's describe how CSS actually works. So the key for CSS is 5 bytes, namely 40 bits. 5 times 8 is 40 bits. The reason they had to limit themselves to only 40 bits is that DVD encryption was designed at a time where US export regulations only allowed for export of crypto algorithms where the key was only 40 bits. So the designers of CSS were already limited to very, very short keys, just 40-bit keys. So their design works as follows. Basically, CSS uses 2 LFSRs. One is a 17-bit LFSR. In other words, the register contains 17 bits. And the other one is a 25-bit LFSR. It's a little bit longer, 25-bit LFSR. And the way these LFSRs are seeded is as follows. So the key for the encryption basically looks as follows. You start off with a 1, and you concatenate to it the first 2 bytes of the key. First 2 bytes of the key. And that's the initial state of the LFSR. And then the second LFSR basically is initialized the same way. 1 concatenated the last 3 bytes of the key. 3 bytes of key, and that's loaded into the initial state of the LFSR. You can see that the first 2 bytes are 16 bits plus leading 1, that's 17 bits overall, whereas the second LFSR is 24 bits plus 1, which is 25 bits. And you notice we used all 5 bits of the key. So then these LFSRs are basically run for 8 cycles, so they generate 8 bits of output, and then they go through this adder that does basically addition modulo 256. Yeah, so this is an addition box modulo 256. There's one more technical thing that happens. In fact, what's actually also added is the carry from the previous block, but that is not so important. That's a detail that's not so relevant. Okay, so every block, you notice we're doing addition modulo 256, so we're ignoring the carry, but the carry is basically added either at 0 or 1 to the addition of the next block. Okay, and then basically this output 1 byte per round. Okay, and this byte is then of course used, it's XORed with the appropriate byte of the movie that's being encrypted. Okay, so it's a very simple stream cipher. It takes very little hardware to implement. It'll run fast even on very cheap hardware, and it will encrypt movies. So it turns out this is easy to break in time roughly 2 to the 17. In roughly 2 to the 17 time. And let me show you how. So suppose you intercept a movie. So here we have an encrypted movie that you want to decrypt. So let's say that this is all encrypted. So you have no idea what's inside of here. However, it so happens that just because DVD encryption is using MPEG files, it so happens that you know a prefix of the plaintext. Let's just say maybe this is 20 bytes. Well, we know that if you XOR these two things together, so in other words, you do the XOR here, what you'll get is the initial segment of the PRG. So you'll get the first 20 bytes of the output of CSS, the output of this PRG. Okay, so now here's what we're going to do. So we have the first 20 bytes of the output. And now we do the following. We try all 2 to the 17 possible values of the first LFSR. Okay, so 2 to the 17 possible values. So for each value, so for each of these 2 to the 17 initial values of the LFSR, we're going to run the LFSR for 20 bytes. Okay, so we'll generate 20 bytes of outputs from this first LFSR, assuming for each one of the 2 to the 17 possible settings. Now, remember, we have the full output of the CSS system, so what we can do is we can take this output that we have and subtract it from the 20 bytes that we got from the first LFSR, and if in fact our guess for the initial state of the first LFSR is correct, what we should get is the first 20 byte output of the second LFSR, right? Because that's, by definition, what the output of the CSS system is. Now, it turns out that looking at a 20 byte sequence is very easy to tell whether this 20 byte sequence came from a 25-bit LFSR or not. If it didn't, then we know that our guess for the 17-bit LFSR was incorrect. And then we move on to the next guess for the 17-bit LFSR, and the next guess, and so on and so forth, until eventually we hit the right initial state for the 17-bit LFSR, and then we'll see that the 20 bytes that we get as the candidate output for the 25-bit LFSR is in fact a possible output for a 25-bit LFSR, and then not only will we have learned the correct initial state for the 17-bit LFSR, we will have also learned the correct initial state of the 25-bit LFSR, and then we can predict the remaining output of CSS, and of course using that we can then decrypt the rest of the movie. We can actually recover the remaining plain text. Okay, this is things that we talked about before. So I said this a little quick, but hopefully it was clear. We are also going to be doing a homework exercise on this type of stream ciphers, and you'll kind of get the point of how these attack algorithms work. And I should mention that there are many open source systems now that actually use this method to decrypt CSS encrypted data. Okay, so now that we've seen 2 weak examples, let's move on to better examples. And in particular, the better pseudo-random generators come from what's called the eStream project. This is a project that concluded in 2008, and they qualified basically 5 different stream ciphers. But here I want to present just one. So first of all, the parameters for these stream ciphers are a little different from what we're used to. So these stream ciphers, as normal, they have a seed, but in addition, they also have what's called a nonce, and we'll see what the nonce is used for in just a minute. So they take 2 inputs, a seed and a nonce. We'll see what the nonce is used for in just a second, and then of course they produce a very large output, so n here is much, much, much bigger than s. Now, when I say nonce, what I mean is a value that's never going to repeat as long as the key is fixed. And I'll explain that in more detail in just a second, but for now just think of it as a unique value that never repeats as long as the key is the same. And so, of course, once you have this PRG, you would encrypt, you get a stream cipher just as before, except now, as you see, the PRG takes as input both the key and the nonce. And the property of the nonce is that the pair k comma r, so the key comma the nonce, is never repeats. It's never used more than once. So the bottom line is that you can reuse the key because the nonce makes the pair unique, because k and r are only used once. I'll say they're unique. Okay, so this nonce is kind of a cute trick that saves us the trouble of moving to a new key every time. Okay, so the particular example from the eStream that I want to show you is called Salsa 20. It's a stream cipher that's designed for both software implementations and hardware implementations. It's kind of interesting. You realize that some stream ciphers are designed for software, like RC4. Everything it does is designed to make software implementation run fast, whereas some other stream ciphers are designed for hardware, like CSS, using an LFSR that's particularly designed to make hardware implementations very cheap. Salsa, the nice thing about that is that it's designed so that it's both easy to implement it in hardware and its software implementation is also very fast. So let me explain how Salsa works. Well, Salsa takes either 128 or 256-bit keys. I'll only explain the 128-bit version of Salsa. So this is the seed. And then it also takes a nonce, just as before, which happens to be 64 bits, and then it'll generate a large output. Now, how does it actually work? Well, the function itself is defined as follows. Basically, given the key and the nonce, it will generate a very long, a long pseudo-random sequence as long as necessary. And it'll do it by using this function that I'll denote by h. This function h takes three inputs, basically the key, the seed k, the nonce r, and then a counter that increments from step to step. So it goes from 0, 1, 2, 3, 4, as long as we need it to be. Okay, so basically by evaluating this h on this kr, but using this incrementing counter, we can get a sequence that's as long as we want. So all I have to do is describe how this function h works. And let me do that here for you. The way it works is as follows. Well, we start off by expanding the state into something quite large, which is 64 bytes long. And we do it as follows. Basically, we stick a constant at the beginning. So there's tau 0. These are 4 bytes. It's a 4-byte constant. So the spec for salsa basically gives you the value for tau 0. Then we put k in, which is 16 bytes. Then we put another constant. Again, this is 4 bytes. And as I said, the spec basically specifies what this fixed constant is. Then we put the nonce, which is 8 bytes. Then we put the index. This is the counter 0, 1, 2, 3, 4, which is another 8 bytes. Then we put another constant, tau 2, which is another 4 bytes. Then we put the key again. This is another 16 bytes. And then finally we put a third constant, tau 3, which is another 4 bytes. Okay, so as I said, if you sum these up, you see that you get 64 bytes. So basically we've expanded the key and the nonce and the counter into 64 bytes. Basically the key is repeated twice, I guess. And then what we do is we apply a function. I'll call this function little h. Okay, so we apply this function little h, and this is a function that's one-to-one, so it maps 64 bytes to 64 bytes. And it's a completely invertible function. Okay, so this function h is, as I say, it's an invertible function. So given the input, you can get the output, and given the output, you can go back to the input. And it's designed specifically so it's A, easy to implement in hardware, and B, on an x86, it's extremely easy to implement because x86 has this SSE2 instruction set, which supports all the operations you need to do for this function. It's very, very fast. As a result, it also has a very fast stream cipher. And then it does this basically again and again. So it applies this function h again, it gets another 64 bytes, and so on and so forth. Basically, it does this 10 times. Okay, so the whole thing here, I'll say, repeats 10 times. So basically, apply h 10 times. And then by itself, this is actually not quite random. It's not going to look random because, like we said, h is completely invertible. So given this final output, it's very easy to just invert h and go back to the original input and then test that the input has the right structure. So you do one more thing, which is to basically XOR the input and the final output. Actually, sorry, it's not an XOR, it's actually an addition. So you do an addition word by word. So there are 64 bytes, you do a word by word addition, 4 bytes at a time, and finally you get the 64 byte output. That's it. That's the whole pseudo-random generator. So that's the whole function little h, and as I explained, this whole construction here is the function big H, and then you evaluate big H by incrementing the counter I from 0, 1, 2, 3 onwards, and that will give you a pseudo-random sequence that's as long as you need it to be. And basically there are no significant attacks on this. This has security that's very close to 2 to the 128. We'll see what that means more precisely later on, but it's a very fast stream cipher, both in hardware and in software, and as far as we can tell, seems to be unpredictable as required for a stream cipher. So I should say that the eStream project actually has 5 stream ciphers like this. I only chose Salsa because I think it's the most elegant, but I can give you some performance numbers here. So you can see these are performance numbers on a 2.2 gigahertz, x86 type machine, and you can see that RC4 actually is the slowest because essentially, well, it doesn't really take advantage of the hardware. It only does byte operations, and so there's a lot of wasted cycles that aren't being used. But the eStream candidates, both Salsa and another candidate called Sosa Manuk, I should say these are eStream finalists. These are actually stream ciphers that are approved by the eStream project, you can see that they achieve significant rates. This is 643 megabytes per second on this architecture, more than enough for a movie, and these are actually quite impressive rates. And so now you've seen examples of two old stream ciphers that shouldn't be used, including attacks on those stream ciphers. You've seen what the modern stream ciphers look like with this nonce, and you see the performance numbers for these modern stream ciphers. So if you happen to need a stream cipher, you could use one of the eStream's finalists. In particular, you could use something like Salsa. In the next three segments, we will change gears a little bit and talk about the definition of a PRG. This definition is a really good way to think of a PRG, and we will see many applications for this definition. So consider a PRG with key space k that outputs n-bit strings. Our goal is to define what does it mean for the output of the generator to be indistinguishable from random. In other words, we're going to define a distribution that basically is defined by choosing a random key in the key space. Remember that arrow with R above it means choosing uniformly from the set script k. And then we output basically the output of the generator. And what we'd like to say is that this distribution of pseudo-random strings, is indistinguishable from a truly uniform distribution. In other words, if we just choose a truly uniform string in 0, 1 to the n, and simply output this string, we'd like to say that these two distributions are indistinguishable from one another. Now, if you think about it, this sounds really surprising, because if we draw a circle here of all possible strings in 0, 1 to the n, then the uniform distribution basically can output any of these strings with equal probability. That's the definition of the uniform distribution. However, a pseudo-random distribution generated by this generator G, because the seed space is so small, the set of possible outputs is really, really small. It's tiny inside of 0, 1 to the n, and this is really all that the generator can output. And yet what we're arguing is that an adversary who looks at the output of the generator in this tiny set can't distinguish it from the output of the uniform distribution over the entire set. Okay? That's the property that we're actually shooting for. So to understand how to define this concept of indistinguishability from random, we need the concept of a statistical test. So let me define what a statistical test on 0, 1 to the n is. I'm going to define these statistical tests by the letter A. And a statistical test is basically an algorithm that takes as input an n-bit string and simply outputs 0 or 1. Now I'll tell you that 0, we're going to think of it as though the statistical test said the input you gave me is not random. And 1, we're going to think of it as saying that the input you gave me actually is random. Okay, so all the statistical test does is it basically takes the input x that was given to it, the n-bit string that was given to it, and decides whether it looks random or it doesn't look random. Let's look at a couple of examples. So the first example basically will use the fact that for a random string, the number of zeros is roughly equal to the number of ones in that string. In other words, the statistical test is going to say 1 if and only if basically the number of zeros in the given string x minus the number of ones in the given string x is these two numbers are not too far apart. In other words, the difference between the number of zeros and the number of ones, let's just say, is less than 10 times square root of n. Okay, so if the difference is less than 10 times square root of n, the statistical test will say, hey, the string x looks random. If the difference happens to be much bigger than 10 times square root of n, that starts to look suspicious, and then the statistical test will say, hey, the string you gave me does not look random. Okay, so this is our first example of a statistical test. Let's look at another similar example. We'll say here, the statistical test will say 1 if and only if, say, the number of times that we have two consecutive zeros inside of x. Well, let's think about this for a second. This basically, again, counts in this string of n bits, it counts the number of times that we see the pattern 0, 0, two consecutive zeros. Well, for a random string, we will expect to see 0, 0 with probability 1/4, and therefore in a random string, we'll expect about n over 4 0 zeros. Yeah, n over 4 blocks of 0, 0. And so what the statistical test will do is it will say, well, if the number of 0 zeros is roughly n over 4, in other words, the difference between the number and n over 4 is, say, less than 10 square root of n, then we will say that x looks random. And if the gap is much bigger than n over 4, we'll say, hey, this string doesn't really look random, and then the statistical test will output 0. Okay, so here are two examples of statistical tests that basically, for random strings, they will output 1 with very high probability. But for strings that, don't look random, for example, think of the all zero string. For the all zero string, neither one of these tests will output 1. And in fact, the all zero string does not look random. Let's look at one more example of a statistical test, just to kind of show you that basically statistical tests can pretty much do whatever they want. So here's a third example. Let's say that the statistical test outputs 1 if and only if, say, the biggest block, so we'll call this the maximum run of 0 inside of the string x. This is basically the longest sequence of zeros inside of the string x. In a random string, you expect the longest sequence of zeros to be roughly of length log n. So we'll say if the longest sequence of 0 happens to be less than 10 times log n, then this test will say that x was random. But if all of a sudden we see a run of zeros that say is much bigger than 10 log n, then the statistical test will say the string is not random. Okay, so this is another crazy thing that the statistical test will do. By the way, you notice that if you give this test the all 1 string, so 1, 1, 1, 1, 1, this test will also output 1. In other words, this test will think that the all 1 string is random, even though it's not. Yeah, even though the all 1 string is not particularly random. Okay, so statistical tests don't have to get things right. They can do whatever they like. They can decide to output random or not, 0 or 1, however they like. And similarly, there are many, 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 many other statistical tests. There are literally hundreds of statistical tests that one can think of. And I can tell you that in the old days, basically the way you would define that something looks random is you would say, hey, here's a battery of statistical tests, and all of them said that the string looks random. Therefore, we say that this generator, the generator of the string, is a good generator. In other words, this definition that uses a fixed set of statistical tests is actually not a good definition for security, or more generally for crypto. But before we talk about actually defining security, the next thing we talk about is how do we evaluate whether a statistical test is good or not. So to do that, we define the concept of advantage. And so let me define the advantage. So here we have a generator that outputs n-bit strings, and we have a statistical test on n-bit strings. And we define the advantage of this generator, I'll denote it by advantage sub PRG, the advantage of the statistical test A relative to the generator G. I'll define it as follows. It's basically the difference between two quantities. The first quantity is basically we ask how likely is the statistical test to output 1 when we give it a pseudorandom string. Okay, so here k is chosen uniformly from the seed space. And we ask how likely is the statistical test to output 1 when we give it a pseudorandom output generated by the generator. Versus now we ask how likely is the statistical test to output 1 when we give it a truly random string. So here R is truly random in 0, 1 to the n. Okay? And yeah, we look at the difference between these two quantities. Now you realize because these are differences of probabilities, this advantage is always going to lie in the interval 0, 1. So let's think a little bit about what this advantage actually means. So first of all, if the advantage happens to be close to 1, well, what does that mean? That means that somehow the statistical test A behaved differently when we gave it pseudo-random inputs, when we gave it the output of the generator, from when we gave it truly random inputs, right? It somehow behaved differently. In one case, it output 1 with a certain probability, and in the other case, it output 1 with a very different probability. Okay, so somehow it was able to behave differently, and what that really means is that the statistical test can basically distinguish the output of the generator from random. Okay, so in some sense we'll say that the statistical test broke the generator G because it was able to distinguish the output from random. However, if the advantage is close to 0, well, what does that mean? That means that basically the statistical test behaves pretty much the same on pseudo-random inputs as it does on truly random inputs. And basically there we would say that A could not distinguish the generator from random. Okay, so this gives you a little bit of intuition about why this concept of advantage is important. It basically tells us whether A was able to break the generator, namely distinguish it from random, or not able to break it. So let's look first of all at a very silly example. Suppose we have a statistical test A that simply ignores its inputs and always outputs 0. Okay, it always outputs 0. What do you think is the advantage of the statistical test relative to a generator G? So I hope everybody said the advantage is 0. Let me just explain why that's the case. Well, if the statistical test always outputs 0, that means that when we give a pseudo-random input, it will never output 1. So the probability that it outputs 1 is 0. Similarly, when we give a truly random input, it still will never output 1. And so the probability that it outputs 1 is 0. And so 0 minus 0 is 0, so its advantage is 0. So basically, a statistical test that ignores its input is not able to distinguish truly random input from a pseudo-random input, obviously. Okay, so now let's look at a more interesting example. So suppose we have a generator G that satisfies a funny property. It so happens that for 2/3 of the keys, the first bit of the output of the generator happens to be 1. Okay, so if I choose a random key with probability 2/3, the generator will output 1 as its first bit. Okay, so that's the property of the generator that we're looking at. Now let's look at the following statistical test. The statistical test basically says, if the most significant bit of the string you gave me is 1, I'm going to say 1, meaning I think it's random. If the most significant bit of the string you gave me is not 1, well, namely 0, I'm going to say 0. Okay, so now my question to you is, what is the advantage of this statistical test on the generator G? Okay, so remember I just wrote down the definition here again, and I'll let you think about this for a second. So let me explain. Suppose we give the statistical test pseudo-random input. By definition of G, we know that with probability 2/3, the first bit in the input will start with the bit 1. But if it starts with the bit 1, then the statistical test will output 1. In other words, the probability that the statistical test outputs 1 is exactly 2/3. Now let's look at the case of a random string. If I give you a random string, how likely is it that the most significant bit of the random string is 1? Well, for a random string, that happens exactly half the time. And so in this case, the statistical test will output 1 with probability 1/2. And so the overall advantage is 1/6, and 1/6 is actually a non-negligible number. That's actually a fairly large number, which basically means that this A was able to distinguish the output. We'll say that A breaks the generator G with advantage 1/6. Okay, which basically means that this generator is no good, is broken. Okay, so now that we understand what statistical tests are, we can go ahead and define what is a secure pseudo-random generator. So basically we say that a generator G is secure if essentially no efficient statistical test can distinguish its output from random. More precisely, what we'll say is that basically for all efficient statistical tests A, it so happens that if I look at the advantage of the statistical test A relative to G, this advantage basically is negligible. Okay, so in other words, it's very close to 0, and as a result, this statistical test was not able to distinguish the output from random, and that has to be true for all statistical tests. So this is a very, very pretty and elegant definition that says that a generator is secure not only if a particular battery of statistical tests says that the output looks random, but in fact all efficient statistical tests will say the output looks random. Okay? One thing I'd like to point out is that the restriction to efficient statistical tests is actually necessary. If we ask that all statistical tests, regardless of whether they're efficient or not be able to distinguish the output from random, then in fact that cannot be satisfied. So in other words, if we took out the requirements that the test be efficient, then this definition would be unsatisfiable, and I'll leave this as a simple puzzle for you to think about. But basically the fact is that restricting this definition to only efficient statistical tests is actually necessary for this to be satisfiable. Now that we have a definition, the next question is, can we actually construct a generator and then prove that in fact it is a secure PRG? In other words, prove that no efficient statistical test can distinguish its output from random. And it turns out that the answer is we actually can't. In fact, it's not known if there are any provably secure PRGs. And I'll just say very briefly, the reason is that if you could prove that a particular generator is secure, that would actually imply that P is not equal to NP. And I don't want to dwell on this because I don't want to assume you guys know what P and NP are. But I'll just tell you as a simple fact that in fact if P is equal to NP, then it's very easy to show that there are no secure PRGs. And so if you could prove to me that a particular PRG is secure, that would imply that P is not equal to NP. Again, I will leave this to you as a simple puzzle to think about. But even though we can't actually rigorously prove that a particular PRG is secure, we still have lots and lots and lots of heuristic candidates, and we even saw some of those in the previous segment. Okay, now that we understand what is a secure PRG, I want to talk a little bit about some applications and implications of this definition. And so the first thing I want to show you is that in fact a secure PRG is necessarily unpredictable. In a previous segment, we talked about what it means for a generator to be unpredictable, and we said that basically what that means is that given a prefix of the output of the generator, it's impossible to predict the next bit of the output. Okay, so we'd like to show that if a generator is secure, then necessarily it means it's unpredictable. And so the way we're going to do that is using the contrapositive. That is, we're going to say that if you give me a generator that is predictable, then necessarily it's insecure. In other words, necessarily I can distinguish it from random. And so let's see, this is actually a very simple fact, and so let's see how we would do that. So suppose you give me a predictor. In other words, suppose you give me an efficient algorithm such that, in fact, if I give this algorithm the output of the generator, but I give it only the first I bits of the output, it's able to predict the next bit of the output. In other words, given the first I bits, it's able to predict the I plus first bit, and it does that with a certain probability. So let's say if we choose a random K from the key space, then clearly a dumb predictor would be able to predict the next bit with probability 1/2, simply just guess a bit. You'll be right with probability 1/2. However, this algorithm A is able to predict the next bit with probability 1/2 plus epsilon. So it's bounded away from 1/2, and in fact we require that this be true for some non-negligible epsilon. So for example, epsilon equals 1/1000 would already be a dangerous predictor because it can predict the next bit given a prefix with non-negligible advantage. Okay, so suppose we have such an algorithm. Let's see that we can use this algorithm to break our generator. In other words, to show that the generator is distinguishable from random and therefore is insecure. So what we'll do is we'll define a statistical test. So let's define a statistical test B as follows. Basically, B given a string X, what it will do is it will simply run algorithm A on the first I bits of the string X that it was given. And statistical test B is simply going to ask, was A successful in predicting the I plus first bit of the string? If it was successful, then it's going to output 1. And if it wasn't successful, then it's going to output 0. Okay, this is our statistical test. Let's put it in a box so we can take it wherever we like. And we can run the statistical test on any n-bit string that's given to us as input. So now let's look at what happens. Suppose we give the statistical test a truly random string. So a truly random string R. And we ask, what is the probability that this statistical test outputs 1? Well, for a truly random string, the I plus first bit is totally independent of the first I bits. So whatever this algorithm A is going to output is completely independent of what the I plus first bit of the string R is. And so whatever A outputs, the probability that it's going to be equal to some random bit xi plus 1, random independent bit xi plus 1, that probability is exactly 1/2. In other words, algorithm A simply has no information about what the bit xi plus 1 is, and so necessarily the probability that it's able to predict xi plus 1 is exactly 1/2. On the other hand, let's look at what happens when we give our statistical test a pseudo-random sequence. Okay, so now we're going to run the statistical test on the output of the generator, and we ask how likely is it to output 1? Well, by definition of A, we know that when we give it the first I bits of the output of the generator, it's able to predict the next bit with probability 1/2 plus epsilon. So in this case, our statistical test B will output 1 with probability greater than 1/2 plus epsilon. And basically what this means is if we look at the advantage of our statistical tests over the generator G, it's basically the difference between this quantity and that quantity. And the difference between the two, you can see, is clearly greater than an epsilon. So what this means is that if algorithm A is able to predict the next bit with advantage epsilon, then algorithm B is able to distinguish the output of the generator with advantage epsilon. Okay, so if A is a good predictor, B is a good statistical test that breaks the generator. And as we said, the contrapositive of that is that if G is a secure generator, then there are no good statistical tests, and as a result, there are no predictors. Okay, and which means that the generator is, as we said, unpredictable. Okay, so far what we've seen is that if the generator is secure, necessarily it's impossible to predict the I plus first bit given the first I bits. Now, there's a very elegant and remarkable theorem due to Yao back in 1982 that shows that in fact the converse is also true. In other words, if I give you a generator that's unpredictable, so you cannot predict the I plus first bit from the first I bits, and that's true for all I, that generator in fact is secure. Okay, so let me state the theorem a little bit more precisely. So here we have our generator that outputs n-bit outputs. The theorem says the following: basically for all bit positions, it's impossible to predict I plus first bit of the output given the first I bits, and that's true for all I. In other words, again, the generator is unpredictable for all bit positions. Then that in fact implies that the generator is a secure PRG. I want to paraphrase this in English, and so the way to kind of interpret this result is to say that if basically these next bit predictors, these predictors that try to predict the I plus first bit given the first I bits, if they're not able to distinguish G from random, then in fact no statistical test can distinguish G from random. So kind of next bit predictors are in some sense universal predictors when it comes to distinguishing things from random. This theorem, by the way, it's not too difficult to prove, but there's a very elegant idea behind its proof. I'm not going to do the proof here, but I encourage you to think about this as a puzzle and try to kind of prove this theorem yourself. Let me show you kind of one cute implication of this theorem. So let me ask you the following question. Suppose I give you a generator, and I tell you that given the last bit of the output, it's easy to predict the first bit of the outputs. Okay, so given the last n bits, you can compute the first n bits. That's kind of the opposite of predictability, right? Predictability meant given the first bits, you can produce the next bits. Here, given the last bits, you can produce the first ones. And my question to you, does that mean that the generator is predictable? Can you somehow, from this fact, still build a predictor for this generator? So this is kind of a simple application of Yao's theorem, and let me explain to you. The answer is actually yes. Let me explain why. How do we build this generator? Well, actually, we're not going to build it. I'm just going to show you that the generator exists. Well, because the last n over 2 bits imply the first n over 2 bits, that necessarily means that the generator, here, let me write it this way, that necessarily means that G is not secure. Because just as we did before, it's very easy to build a statistical test that will distinguish the output of G from uniform. So G is not secure. But if G is not secure, by Yao's theorem, that means that G is predictable. So in other words, there exists some I for which, given the first I bits of the output, you can build the I plus first bit of the output. Okay? And so even though I can't quite point to you to a predictor, we know that a predictor must exist. So that's one cute, simple application of Yao's theorem. Now, before we end this segment, I want to kind of generalize a little bit what we did and introduce a little bit of important notation that's going to be useful actually throughout. So we're going to generalize the concept of indistinguishability from uniform to indistinguishability of two general distributions. So suppose I give you P1 and P2, and we ask, can these two distributions be distinguished? And so we'll say that the distributions are computationally indistinguishable, and we'll denote this by P1 is squiggly P, P2. This means that in polynomial time, P1 cannot be distinguished from P2, and we'll say that they're indistinguishable basically just as before, if basically for all efficient statistical tests A, it so happens that if I sample from the distribution P1 and I give the output to A, versus if I sample from the distribution P2 and I give the sample to A, then basically A behaves the same in both cases. In other words, the difference between these two probabilities is negligible. And this has to be true for all statistical tests, for all efficient statistical tests. Okay, so if this is the case, then we say that, well, A couldn't distinguish, its advantage in distinguishing two distributions is negligible, and if that's true for all efficient statistical tests, then we say that the two distributions are basically computationally indistinguishable because an efficient algorithm cannot distinguish them. And just to show you how useful this notation is, basically using this notation, the definition of security for a PRG just says that if I give you a pseudo-random distribution, in other words, I choose k at random and then output g of k, that distribution is computationally indistinguishable from the uniform distribution. So you can see this very simple notation captures the whole definition of pseudorandom generators. Okay, so we're going to make use of this notation in the next segment when we define what does it mean for a cipher to be secure. My goal for the next two segments is to show you that if we use a secure PRG, we get a secure stream cipher. The first thing we have to do is define what does it mean for a stream cipher to be secure. So whenever we define security, we always define it in terms of what can the attacker do and what is the attacker trying to do. In the context of stream ciphers, remember these are only used with a one-time key, and as a result, the most the attacker is ever going to see is just one ciphertext encrypted using the key that we're using. And so we're going to limit the attacker's abilities to basically obtain just one ciphertext. And in fact, later on, we're going to allow the attacker to do much, much, much more. But for now, we're just going to give him one ciphertext. And we want to define what does it mean for the cipher to be secure. So the first definition that comes to mind is basically to say, well, maybe we want to require that the attacker can't actually recover the secret key. Okay, so given the ciphertext, he shouldn't be able to recover the secret key. But that's a terrible definition because think about the following brilliant cipher. So here, but the way we encrypt a message using a key k is basically we just output the message. Okay, this is a brilliant cipher. Yeah, of course, it doesn't do anything. Given a message, it just outputs the message as the ciphertext. So this is not a particularly good encryption scheme. However, given the ciphertext, namely the message, the poor attacker cannot recover the key because he doesn't know what the key is. And so as a result, this cipher, which clearly is insecure, would be considered secure under this requirement for security. So this definition will be no good. Okay, just recovering the secret key is the wrong way to define security. So the next thing we can try and attempt is basically to say, well, maybe the attacker doesn't care about the secret key. What he really cares about is the plaintext. So maybe it should be hard for the attacker to recover the entire plaintext. But even that doesn't work because let's think about the following encryption scheme. So suppose what this encryption scheme does is it takes two messages. So I'm going to use two lines to denote the concatenation of two messages. M0 line M1 means concatenate M0 and M1. And imagine what the scheme does is really it outputs M0 in the clear and concatenates to that the encryption of M1, perhaps even using the one-time pad. Okay? And so here the attacker is going to be given one ciphertext, and his goal would be to recover the entire plaintext. But the poor attacker can't do that because here maybe we encrypted M1 using the one-time pad, so the attacker can't actually recover M1 because we know the one-time pad is secure given just one ciphertext. So this construction would satisfy the definition, but unfortunately, clearly this is not a secure encryption scheme because we just leaked half of the plaintext. M0 is completely available to the attacker. So even though he can't recover all of the plaintext, he might be able to recover most of the plaintext, and that's clearly insecure. So of course we already know the solution to this, and we talked about Shannon's definition of security, perfect secrecy, where Shannon's idea was that in fact when the attacker intercepts a ciphertext, he should learn absolutely no information about the plaintext. He shouldn't even learn one bit about the plaintext, or even he shouldn't even be able to predict a little bit about a bit of the plaintext. Absolutely no information about the plaintext. So let's recall very briefly Shannon's concept of perfect secrecy. Basically we said that, given a cipher, we said the cipher has perfect secrecy if given two messages of the same length. It so happens that the distribution of ciphertexts, if we pick a random key and we look at the distribution of ciphertext, we encrypt M0, we get exactly the same distribution as when we encrypt M1. The intuition here was that if the adversary observes a ciphertext, then he doesn't know whether it came from the distribution, the result of encrypting M0, or it came from the distribution as the result of encrypting M1. And as a result, he can't tell whether we encrypted M0 or M1. And that's true for all messages of the same length. And as a result, the poor attacker doesn't really know what message was encrypted. Of course, we already said that this definition is too strong in the sense that it requires really long keys. If a cipher that has short keys can't possibly satisfy this definition, and in particular stream ciphers can't satisfy this definition. Okay, so let's try to weaken the definition a little bit, and let's think to the previous segment, and we can say that instead of requiring that the two distributions be absolutely identical, what we can require is that the two distributions just be computationally indistinguishable. In other words, a poor, efficient attacker cannot distinguish the two distributions, even though the distributions might be very, very, very different. But just given a sample for one distribution and a sample from another distribution, the attacker can't tell which distribution he was given a sample from. It turns out this definition is actually almost right, but it's still a little too strong. This still cannot be satisfied. So we have to add one more constraint, and that is that instead of saying that this definition should hold for all M0, M1, it needs to hold for only pairs M0, M1 that the attacker can actually exhibit. Okay, so this actually leads us to the definition of semantic security. And so, again, this is semantic security for a one-time key. In other words, when the attacker is only given one ciphertext. And so the way we define semantic security is by defining two experiments. Okay, we'll define experiment 0 and experiment 1. And more generally, we'll think of these as experiment parenthesis B, where B can be 0 or 1. Okay, so the way the experiment is defined is as follows. We have an adversary that's trying to break the system, an adversary A. That's kind of the analog of a statistical test in the world of pseudo-random generators. And then the challenger does the following. So really we have two challengers, but the challengers are so similar that we can just describe them as a single challenger that in one case takes as input the bit set to 0, and the other case takes as input the bit set to 1. And let me show you what these challengers do. The first thing the challenger is going to do is it's going to pick a random key, and then the adversary basically is going to output two messages M0 and M1. Okay, so this is an explicit pair of messages that the attacker wants to be challenged on. And as usual, we're not trying to hide the length of the messages. We require that the messages be equal length. And then the challenger basically will output either the encryption of M0 or the encryption of M1. Okay, so in experiment 0, the challenger will output the encryption of M0. In experiment 1, the challenger will output the encryption of M1. Okay, so that's the difference between the two experiments. And then the adversary is trying to guess, basically, whether he was given the encryption of M0 or given the encryption of M1. Okay, so here's a little bit of notation. Let's define the event WB to be the event that in experiment B, the adversary output 1. Okay, so that's just an event. That basically in experiment 0, W0 means that the adversary output 1. In experiment 1, W1 means the adversary output 1. And now we can define the advantage of this adversary, basically to say what this is called the semantic security advantage of the adversary A against the scheme E, to be the difference of the probability of these two events. In other words, we're looking at whether the adversary behaves differently when he was given the encryption of M0 from when he was given the encryption of M1. And I want to make sure this is clear, so I'm going to say it one more time. So in experiment 0, he was given the encryption of M0. In experiment 1, he was given the encryption of M1. Now, we're just interested in whether the adversary output 1 or not in these experiments. If in both experiments the adversary output 1 with the same probability, that means that the adversary wasn't able to distinguish the two experiments. Experiment 0 basically looks to the adversary the same as experiment 1, because in both cases it output 1 with the same probability. However, if the adversary is able to output 1 in one experiment with significantly different probability than in the other experiment, then the adversary was actually able to distinguish the two experiments. Okay? So, to say this more formally, essentially the advantage, again, because it's a difference of two probabilities, the advantage is a number between 0 and 1. If the advantage is close to 0, that means that the adversary was not able to distinguish experiment 0 from experiment 1. However, if the advantage is close to 1, that means the adversary was very well able to distinguish experiment 0 from experiment 1, and that really means that he was able to distinguish an encryption of M0 from an encryption of M1. Okay, so that's our definition. Actually, that's just the definition of the advantage, and then the definition is just what you would expect. Basically, we'll say that a symmetric encryption scheme is semantically secure if for all efficient adversaries, here I'll put this in quotes again, for all efficient adversaries, the advantage is negligible. In other words, no efficient adversary can distinguish the encryption of M0 from the encryption of M1. And basically this is what it says repeatedly, that for these two messages that the adversary was able to exhibit, he wasn't able to distinguish these two distributions. Now, I want to show you, this is actually a very elegant definition. It might not seem so right away, but I want to show you some implications of this definition, and you'll see exactly why the definition is the way it is. Okay, so let's look at some examples. So the first example is, suppose we have a broken encryption scheme. In other words, suppose we have an adversary A that somehow, given the ciphertext, he's always able to deduce the least significant bit of the plaintext. Okay, so given the encryption of M0, this adversary is able to deduce the least significant bit of M0. So that's a terrible encryption scheme because it basically leaks the least significant bit of the plaintext just given the ciphertext. So I want to show you that the scheme is therefore not semantically secure. So that kind of shows that if a system is semantically secure, then there is no attacker of this type. Okay, so let's see, why is the system not semantically secure? Well, so what we're going to do is we're going to basically use our adversary, who's able to learn the least significant bits. We're going to use him to break semantic security. So we're going to use him to distinguish experiment 0 from experiment 1. Okay, so here's what we're going to do. We're algorithm B. We're going to build algorithm B. And this algorithm B is going to use algorithm A in its belly. Okay, so the first thing that's going to happen is, of course, the challenger is going to choose a random key. The first thing that's going to happen is we need to output two messages. The messages that we're going to output basically are going to have different least significant bits. So one message is going to end with 0, and one message is going to end with 1. Now, what is the challenger going to do? The challenger is going to give us the encryption of either M0 or M1, depending on whether we're in experiment 0 or in experiment 1. And then we just forward this ciphertext to the adversary. Okay, to adversary A. Now, what's the property of adversary A? Given the ciphertext, adversary A can tell us what the least significant bits of the plaintext is. In other words, the adversary is going to output the least significant bit of M0 or M1. But lo and behold, that's basically the bit B. And then we're just going to output that as our guess. So let's call this thing B prime. Okay, so now this describes the semantic security adversary. And now you tell me, what is the semantic security advantage of this adversary? Well, so let's see. So in experiment 0, what's the probability that adversary B outputs 1? Well, in experiment 0, it's always given the encryption of M0, and therefore adversary A was always output the least significant bit of M0, which happens to be 0. In experiment 0, B always outputs 0, so the probability that it outputs 1 is 0. However, in experiment 1, we're given the encryption of M1, so how likely is adversary B to output 1 in experiment 1? Well, it always outputs 1, again, by the properties of algorithm A, and therefore the advantage basically is 1. So this is a huge advantage. It's as big as it's going to get, which means that this adversary completely broke the system. Okay, so we consider, so under semantic security, basically just deducing the least significant bit is enough to completely break the system under a semantic security definition. Okay, now the interesting thing here, of course, is that this is not just about the least significant bit. In fact, take any predicate of the message, for example, the most significant bit, bit number 7, maybe the XOR of all the bits in the message, and so on and so forth. Any kind of information, any bit about the plaintext that can be learned basically would mean that the system is not semantically secure. So basically all the adversary have to do would be to come up with two messages, M0 and M1, such that under one thing that A learns, it's the value 0, and under the other thing, the value is 1. So for example, if A was able to learn the XOR of all the bits of the message, then M0 and M1 would just have different XORs for all the bits of their messages, and then this adversary A would also be sufficient to break semantic security. Okay, so basically if a cipher is semantically secure, then no bit of information is revealed to an efficient adversary. Okay, so this is exactly the concept of perfect secrecy, only applied just to efficient adversaries rather than all adversaries. So the next thing I want to show you is that in fact the one-time pad in fact is semantically secure. It had better be semantically secure because it's more than that, it's perfectly secure. So let's see why that's true. Well, so again, it's one of these experiments. So suppose we have an adversary that claims to break semantic security of the one-time pad. The first thing the adversary is going to do is he's going to output two messages, M0 and M1, of the same length. Now, what does he get back as a challenge? As a challenge, he gets either the encryption of M0 or the encryption of M1 under the one-time pad. And he's trying to distinguish between those two possible ciphertexts that he gets, right? In experiment 0, he gets the encryption of M0, and experiment 1, he gets the encryption of M1. Well, so let me ask you, so what is the advantage of adversary A against the one-time pad? So remember, the property of the one-time pad is that K XOR M0 is distributed identically to K XOR M1. In other words, these distributions are absolutely identical distributions, identical. This is a property of XOR. If we XOR the random pad K with anything, either M0 or M1, we get uniform distribution. So in both cases, algorithm A is given as input exactly the same distribution, namely the uniform distribution on ciphertexts. And therefore, it's going to behave exactly the same in both cases, because it was given the same distribution as input. And as a result, its advantage is 0, which means that the one-time pad is semantically secure. Now, the interesting thing here is not only is it semantically secure, it's semantically secure for all adversaries. We don't even have to restrict the adversaries to be efficient. No adversary, doesn't matter how smart you are, no adversary will be able to distinguish K XOR M0 for K XOR M1 because the two distributions are identical. Okay, so the one-time pad is semantically secure. Okay, so that completes our definition of semantic security. And the next thing we're going to do is prove that a secure PRG, in fact, implies that the stream cipher is semantically secure. So now that we understand what a secure PRG is, and we understand what semantic security means, we can actually argue that a stream cipher with a secure PRG is in fact semantically secure. So that's our goal for this segment. It's a fairly straightforward proof, and we'll see how it goes. So the theorem we want to prove is that basically given a generator G that happens to be a secure pseudorandom generator, in fact the stream cipher that's derived from this generator is going to be semantically secure. Okay, and I want to emphasize that there was no hope of proving a theorem like this for perfect secrecy, for Shannon's concept of perfect secrecy, because we know that a stream cipher cannot be perfectly secure because it has short keys. And perfect secrecy requires keys to be as long as the message. So this is really kind of the first example that we see where we're able to prove that a cipher with short keys has security. The concept of security is semantic security, and this actually validates that really this is a very useful concept. And in fact, we'll be using semantic security many, many times throughout the course. Okay, so how do we prove a theorem like this? What we're actually going to be doing is we're going to be proving the contrapositive. What we're going to show is the following. So we're going to prove this statement down here, but let me parse it for you. Suppose you give me a semantic security adversary A. What we'll do is we'll build PRG adversary B that satisfies this inequality here. Now, why is this inequality useful? Basically, what do we know? We know that if B is an efficient adversary, then we know that since G is a secure generator, we know that this advantage is negligible, right? A secure generator has a negligible advantage against any efficient statistical test. So the right-hand side basically is going to be negligible, but because the right-hand side is negligible, we can deduce that the left-hand side is negligible, and therefore the adversary that you looked at actually has negligible advantage in attacking the stream cipher E. Okay, so this is how this will work. Basically, all we have to do is given an adversary A, we're going to build an adversary B. We know that B has negligible advantage against the generator, but that implies that A has negligible advantage against the stream cipher. Okay, so let's do that. So all we have to do again is given A, we have to build B. So let A be a semantic security adversary against the stream cipher. So let me remind you what that means. Basically, there's this challenger. The challenger starts off by choosing a key K, and then the adversary is going to output two messages, two equal length messages, and he's going to receive the encryption of M0 or M1, and then he outputs B prime. Okay, that's what a semantic security adversary is going to do. So now we're going to start playing games with this adversary, and that's how we're going to prove our lemma. All right, so the first thing we're going to do is we're going to make the challenger also choose a random R, okay, a random string R. So, well, the adversary doesn't really care what the challenger does internally. The challenger never uses R, so this doesn't affect the adversary's advantage at all. The adversary just doesn't care that the challenger also picks R. But now comes the trick. What we're going to do is instead of encrypting using GK, we're going to encrypt using R. And you can see kind of basically what we're doing here. Essentially, we're changing the challenger, so now the challenge ciphertext is encrypted using a truly random pad as opposed to the pseudo-random pad GK. Okay, now the property of the pseudo-random generator is that its output is indistinguishable from truly random. So because the PRG is secure, the adversary can't tell that we made this change. The adversary can't tell that we switched from a pseudo-random string to a truly random string. Again, because the generator is secure. Well, but now look at the game that we ended up with. So the adversary's advantage couldn't have changed by much because he can't tell the difference. But now look at the game that we ended up with. Now this game is truly a one-time pad game. This is a semantic security game against the one-time pad, because now the adversary is getting a one-time pad encryption of M0 or M1. But in the one-time pad, we know that the adversary's advantage is 0 because you can't beat the one-time pad. The one-time pad is secure, unconditionally secure. And as a result, because of this, essentially, since the adversary couldn't have told the difference when we moved from pseudo-random to random, but he couldn't win the random game, that also means that he couldn't win the pseudo-random game. And as a result, the stream cipher, the original stream cipher, must be secure. So that's the intuition for how the proof is going to go. But I want to do it rigorously once. From now on, we're just going to argue by playing games with a challenger, and we won't be doing things as formal as I'm going to do next. But I want to do formally and precisely once, just so that you see how these proofs actually work. Okay, so I'm going to have to introduce some notation. And I'll do the usual notation. Basically, in the original semantic security game, when we're actually using a pseudo-random pad, I'm going to use W0 and W1 to denote the event that the adversary outputs 1 when he gets the encryption of M0 or gets the encryption of M1, respectively. Okay, so W0 corresponds to outputting 1 when receiving the encryption of M0, and W1 corresponds to outputting 1 when receiving the encryption of M1. So that's as in the standard definition of semantic security. Now, once we flipped to the random pad, I'm going to use R0 and R1 to denote the event that the adversary outputs 1 when receiving the one-time pad encryption of M0 or the one-time pad encryption of M1. So we have 4 events, W0, W1 from the original semantic security game, and R0 and R1 from the semantic security game once we switched over to the one-time pad. So now let's look at relations between these variables. So first of all, R0 and R1 are basically events from a semantic security game against a one-time pad. So the difference between these probabilities is, as we said, is basically the advantage of algorithm A, of adversary A, against the one-time pad, which we know is 0. Okay, so that's great. So that basically means that probability of R0 is equal to the probability of R1. So now let's put these events on a line segment between 0 and 1. So here are the events, W0 and W1 are the events we're interested in. We want to show that these two are close. Okay? And the way we're going to do it is basically by showing, and I should say, here is probability R0 and R1, and since they're both the same, I just put them in the same place. What we're going to do is we're going to show that both W0 and W1 are actually close to the probability of RB, and as a result, they must be close to one another. Okay, so the way we do that is using a second claim. So now we're interested in the distance between probability of WIB and probability of RB. Okay, so we'll prove the claim in a second. Let me just state the claim. The claim says that there exists an adversary B such that the difference between these two probabilities is basically the advantage of B against the generator G. And this is for both B's. Okay, so given these two claims, the theorem is done because basically, what do we know? We know that this distance is now less than the advantage of B against G. That's from claim 2. And similarly, this distance is less, actually it's even equal to, I don't have to say less, it's equal to the advantage of B against G. And as a result, you can see that the distance between W0 and W1 is basically at most twice the advantage of B against G. That's basically the theorem we were trying to prove. Okay, so the only thing that remains is just proving this claim 2. And if you think about what claim 2 says, it basically captures the question of what happens in experiment 0, what happens when we replace the pseudo-random pad GK by a truly random pad R, right? Here in experiment 0, say, we're using a pseudo-random pad, and here in experiment 0, we're using a truly random pad. And we're asking, can the adversary tell the difference between these two? And we want to argue that he cannot because the generator is secure. Okay, so here's what we're going to do. So let's prove claim 2. So we want to argue that in fact there is a PRG adversary B that has exactly the difference of the two probabilities as its advantage. Okay, and since the point is, since this is negligible, and that's basically what we wanted to prove. Okay, so let's look at statistical test B. So what is statistical test B? It's going to use adversary A in its belly, so we get to build statistical test B however we want. As we said, it's going to use adversary A inside of it for its operation, and it's a regular statistical test. So it takes an n-bit string as input, and it's supposed to output, random or not random, 0 or 1. Okay, so let's see. So it's going to, first thing it's going to do is it's going to run adversary A, and adversary A is going to output two messages, M0 and M1. And then what adversary B is going to do is basically going to respond with M0 XOR the string that it was given as input. All right, that's the statistical test. And then whatever A outputs, it's going to output as its output. And now let's look at its advantage. So what can we say about the advantage of this statistical test against the generator? Well, so by definition, it's the probability that if we choose a truly random string, so here R is in 0, 1 to the n, it's the probability that B outputs 1, minus the probability that when we choose a pseudo-random string, B outputs 1. Okay? Okay, but let's think about what this is. So what can you tell me about the first expression? So what can you tell me about this expression over here? Well, by definition, that's exactly, if you think about what's going on here, this is exactly the probability R0, right? Because this game that we're playing with the adversary here is basically he outputs M0, M1, right? Here he outputted M0, M1, and he got the encryption of M0 under a truly one-time pad. Okay, so this is basically a probability of R0. Here, let me write this a little better. So this is basically a probability of R0. Now, what can we say about the next expression? Well, what can we say about what happens when B is given a pseudo-random string Y as input? Well, in that case, this is exactly experiment 0 in the true stream cipher game, because now we're computing M XOR M0 XOR GK. So this is exactly W0. Okay, that's exactly what we had to prove. So it's a kind of a trivial proof. Okay, so that completes the proof of claim 2. And again, just to make sure this is all clear, once we have claim 2, we know that W0 must be close to W1, and that's the theorem. That's what we had to prove. Okay, so now we've established that a stream cipher is in fact semantically secure, assuming that the PRG is secure.
Before we start with the technical material, I want to tell you a little bit about the history of cryptography. There's a beautiful book on this topic by David Kahn called The Codebreakers that covers the history of cryptography all the way from the Babylonian era to the present. Here I'm just going to give you a few examples of historical ciphers, all of which are badly broken. So to talk about ciphers, the first thing I'm going to do is introduce our friends Alice and Bob, who are going to be with us for the rest of the quarter. So Alice and Bob are trying to communicate securely, and there is an attacker who's trying to eavesdrop on their conversation. So to communicate securely, they're going to share a secret key, which I'll denote by K. They both know this secret key, but the attacker does not know anything about this key K. So now they're going to use a cipher, which is a pair of algorithms, an encryption algorithm denoted by E and a decryption algorithm D. These algorithms work as follows. The encryption algorithm E takes the message M as input, and it takes as input the key K. I'm going to put a wedge above the key input just to denote the fact that this input is really the key input. And then it outputs a ciphertext, which is the encryption of the message M using the key K. I'm always going to write the key first, and when I write :equals, what I mean is that the expression defines what the variable C stands for. Now the ciphertext is transmitted over the internet to Bob somehow. Actually, it could be transmitted over the internet, could be transmitted using an encrypted file system. It doesn't really matter. But when the ciphertext reaches Bob, he can plug it into the decryption algorithm and give the decryption algorithm the same key K. Again, I'm going to put a wedge here as well to denote the key input. And the decryption algorithm outputs the original plaintext message. Now, the reason we say that these are symmetric ciphers is that both the encryptor and decryptor actually use the same key K. As we'll see later in the course, there are ciphers where the encryptor uses one key and the decryptor uses a different key. But here we're just going to focus on symmetric ciphers where both sides use the same key. Okay, so let me give you a few historic examples of ciphers. The first example, the simplest one, is called a substitution cipher. I'm sure all of you played with substitution ciphers when you were in kindergarten. Basically, a key for a substitution cipher is a substitution table that basically says how to map letters. So here, for example, the letter A would be mapped to C, the letter B would be mapped to W, the letter C would be mapped to N, so on and so forth, and then the letter Z would be mapped, say, to A. So this is one example of a key for a substitution cipher. So just to practice the notation we introduced before, the encryption of a certain message using this key, let's say the message is BCZA, the encryption of this message using this key here would be, is done by substituting one letter at a time. So B becomes W, C becomes N, Z becomes A, and A becomes C. So the encryption of BCZA is WNAC, and this defines the ciphertext. Similarly, we can decrypt the ciphertext using the same key, and of course we'll get back the original message. Okay, so just for historical reasons, there's one example of something that's related to the substitution cipher called the Caesar cipher. The Caesar cipher actually is not really a cipher at all, and the reason is that it doesn't have a key. What a Caesar cipher is basically a substitution cipher where the substitution is fixed, namely it's a shift by 3. So A becomes D, B becomes E, C becomes F, and so on and so forth. What is it? Y becomes B, and Z becomes C. It's a fixed substitution that's applied to all plaintext messages. So again, this is not a cipher because there is no key. The key is fixed. So if an attacker knows how our encryption scheme works, he can easily decrypt the message. The key is not random, and therefore decryption is very easy once you understand how the scheme actually works. Okay, so now let's go back to the substitution cipher where the keys really are chosen at random. These substitution tables are chosen at random. And let's see how we break this substitution cipher. Turns out to be very easy to break. The first question is, how big is the key space? How many different keys are there, assuming we have 26 letters? So I hope all of you said that the number of keys is 26 factorial because a substitution key is simply a table, a permutation of all 26 letters. The number of permutations of 26 letters is 26 factorial. If you calculate this out, 26 factorial is about 2 to the 88, which means that describing a key in a substitution cipher takes about 88 bits. So each key is represented by about 88 bits. Now, this is a perfectly fine size for a key space. In fact, we're going to be seeing ciphers that are perfectly secure or are adequately secure with key spaces that are roughly of this size. However, even though the substitution cipher has a large key space of size 2 to the 88, it's still terribly insecure. So let's see how to break it. And to break it, we're going to be using letter frequencies. So the first question is, what is the most frequent letter in English text? So I imagine all of you know that, in fact, E is the most common letter. And that is going to, if we make that quantitative, that's going to help us break a substitution cipher. So just given the ciphertext, we can already recover the plaintext. So the way we do that is, first of all, using frequencies of English letters. So here's how this works. So you give me an encrypted message using a substitution cipher. What I know is, all I know is that the message is in English, the plaintext is in English. And I know that the letter E is the most frequent letter in English, and in fact it appears 12.7% of the time in standard English text. So what I'll do is I'll look at the ciphertext you gave me, and I'm going to count how many times every letter appears. Now, the most common letter in the ciphertext is going to be the encryption of the letter E with very high probability. So now I'm able to recover one entry in the key table. Namely, now I know what the letter E maps to. The next most common letter in English is the letter T, that appears about 9.1% of the time. So now again, I count how many times each letter appears in the ciphertext, and the second most frequent letter is very likely to be the encryption of the letter T. So now I've recovered the second entry in the key table. And I can continue this way. In fact, the letter A is the next most common letter. It appears 8.1% of the time. So now I can guess that the third most common letter in the ciphertext is the encryption of the letter A, and now I've recovered 3 entries in the key table. Well, so now what do I do? The remaining letters in English appear roughly the same amount of time, other than some rare letters like Q and X. But we're kind of stuck at this point. We figured out 3 entries in the key table, but what do we do next? So the next idea is to use frequencies of pairs of letters. Sometimes these are called digrams. So what I'll do is I'll count how many times each pair of letters appears in the ciphertext. And I know that in English, the most common pairs of letters are things like HE, AN, IN, I guess TH is another common pair of letters. And so I know that the most common pair of letters in the ciphertext is likely to be the encryption of one of these four pairs. And so by trial and error, I can sort of figure out more elements in the key table. And again, by more trial and error, this way, by looking at trigrams, I can actually figure out the entire key table. So the bottom line here is that, in fact, this substitution cipher is vulnerable to the worst possible type of attack, namely a ciphertext-only attack. Just given the ciphertext, the attacker can recover the decryption key and therefore recover the original plaintext. So there's really no point in encrypting anything using a substitution cipher because the attacker can easily decrypt it all. You might as well send your plaintext completely in the clear. So now we're going to fast forward to the Renaissance, and I guess we're moving from the Roman era to the Renaissance, and look at a cipher designed by a fellow named Vigenère who lived in the 16th century. He designed a couple of ciphers. Here I'm going to show you a variant of one of his ciphers. This is called a Vigenère cipher. So in a Vigenère cipher, the key is a word. In this case, the word is crypto. It's got 6 letters in it. And then to encrypt the message, what you do is you write the message under the key. So in this case, the message is, "What a nice day today." And then you replicate the key as many times as needed to cover the message. And then the way you encrypt is basically you add the key letters to the message letters modulo 26. So just to give you an example here, for example, if you add Y and A, you get Z. If you add T and A, you get U. And you do this for all the letters. And remember, whenever you add modulo 26. So if you go past Z, you go back to A. So that's the Vigenère cipher. And in fact, decryption is just as easy as encryption. Basically, the way you would decrypt is, again, you would write the ciphertext under the key, you would replicate the key, and then you would subtract the key from the ciphertext to get the original plaintext message. So breaking a Vigenère cipher is actually quite easy. Let me show you how you do it. The first thing we need to do is we need to assume that we know the length of the key. So let's just assume we know that. In this case, the length of the key is 6. And then what we do is we break the ciphertext into groups of 6 letters each. Okay, so we're going to get a bunch of groups like this. Each one contains 6 letters. And then we're going to look at the first letter in each group. Okay, so in this case, yes, we're looking at the first letter every 6 characters. Now, what do we know about these 6 letters? We know that, in fact, they're all encrypted using the same letter in the ciphertext. All of these are encrypted using the letter C. In other words, ZLW is a shift by 3 of the plaintext letters. So if we collect all these letters, then the most common letter among this set is likely to be the encryption of E. Right? E is the most common letter in English. Therefore, if I look at every 6th letter, the most common letter in that set is likely to be the encryption of the letter E. Aha! So let's just suppose that, in fact, the most common letter every 6th letter happens to be the letter H. Then we know that E plus the first letter of the key is equal to H. That says that the first letter of the key is equal to H minus E. And in fact, that is the letter C. So now we've recovered the first letter of the key. And now we can continue doing this with the second letter. So we look at the second letter in every group of 6 characters. And again, we repeat the same exercise. We find the most common letter among this set. And we know that this most common letter is likely the encryption of E. And therefore, whatever this most common letter is, if we subtract E from it, we're going to get the second letter of the key. And so on and so forth with the third letter every 6 characters. And this way we recover the entire key, and that allows us to decrypt the message. Now, the only caveat is that I had to assume ahead of time that I know the length of the key, which in this case is 6. But if I don't know the length of the key ahead of time, that's not a problem either. What I would do is I would run this decryption procedure assuming the key length is 1. Then I'd run it assuming the key length is 2. Then I would run it assuming the key length is 3. And so on and so on and so on until finally I get a message, I get a decryption that makes sense, that's sensical. And once I do that, I know that I've kind of recovered the right length of the key. And I know that I've also recovered the right key and therefore the right message. Okay, so very, very quickly you can decrypt Vigenère ciphers. Again, this is a ciphertext only attack. The interesting thing is that Vigenère had a good idea here. This addition mod 26 is actually a good idea, and we'll see that later, except it's executed very poorly here. And so we'll correct that a little bit later. Okay, we're going to fast forward now from the Renaissance to the 19th century, where everything became electric. And so people wanted to design ciphers that use electric motors. In particular, these ciphers are called rotor machines because they use rotors. So an early example is called a Hebern machine, which uses a single rotor. Here you have a picture of this machine. The motor, I guess the rotor is over here, and the secret key is captured by this disk here. It's embedded inside of this disk, which rotate by 1 notch every time you press a key on the typewriter. Okay, so every time you hit a key, the disk rotates by 1 notch. Now, what does this key do? Well, the key actually encodes a substitution table. So, and therefore the disk actually is the secret key. And as I said, this disk encodes a substitution table. In this case, if you happen to press C as the first letter, output would be the letter T. And then the disk would rotate by 1 notch. After rotating by 1 notch, the new substitution table becomes the one shown here. You see that E basically moves up, and then the remaining letters move down. So imagine this is basically a 2-dimensional rendering of the disk rotating by 1 notch. Then you press the next letter, and the disk rotates again. You notice again N moved up, and the remaining letters moved down. So in particular, if we hit the letter C 3 times, the first time the output would be T. The second time the output would be S, and the third time the output would be K. So this is how this single rotor machine works. And as it turned out, very quickly after it was advertised, it was again broken basically using letter frequencies, digram frequencies, and trigram frequencies. It's not that hard given enough ciphertext to directly recover the secret key and then the message. Again, a ciphertext only attack. So to kind of work against these frequency attacks, these statistical attacks, these rotor machines became more and more complicated over time until finally, I'm sure you've all heard of the Enigma. The Enigma is kind of complicated rotor machine. It uses 3, 4, or 5 rotors. There are different versions of the Enigma machine. Here you see an example of the Enigma machine with 3 rotors. The secret key in the Enigma machine is the initial setting of the rotors. Okay, so in the case of 3 rotors, there would be 26 cube possible different keys. When you type on the typewriter, basically these rotors here rotate at different rates. Oh, I forgot to say this is a diagram of an Enigma machine using 4 rotors. As you type on the typewriter, the rotors rotate and output the appropriate letters of the ciphertext. So in this case, the number of keys is 26 to the 4th, which is 2 to the 18, which is actually relatively a small key space. Today you can kind of brute force search using a computer through 2 to the 18 different keys very, very quickly. You know, my wristwatch can do it in just a few seconds, I guess. And so this Enigma machine was using relatively small key spaces, but I'm sure you've all heard that the British cryptographers at Bletchley Park were able to mount ciphertext-only attacks on the Enigma machine. They were able to decrypt German ciphers back in World War II, and that played an important role in many different battles during the war. After the war, I guess that was the end kind of the mechanical age, and started the digital age where folks were using computers. And as the world kind of migrated to using computers, the government realized that it's buying a lot of digital equipment from industry. And so it wanted industry to use a good cipher so that when it buys equipment from industry, it would be getting equipment with a decent cipher. And so the government put out this request for proposal for a data encryption standard, a federal data encryption standard. And we're going to talk about this effort in more detail later on in the course. But in 1974, a group at IBM put together a cipher that became known as DES, the Data Encryption Standard, which became a federal standard for encrypting data. The key space for DES is 2 to the 56, which is relatively small these days, but was large enough back in 1974. And another interesting thing about DES is rather than, unlike rotor machines, which encrypt one character at a time, the data encryption standard encrypts 64 bits at a time, namely 8 characters at a time. And we'll see the significance of this later on in the course. Because DES uses such a small key space, these days it can be broken by a brute force search. And so these days DES is considered insecure and should not be used in projects. Unfortunately, it is used in some legacy systems, but it definitely is on its way out and definitely should not be used in new projects. Today, there are new ciphers, things like the Advanced Encryption Standard, which uses 128-bit keys. Again, we'll talk about the Advanced Encryption Standard in much more detail later on in the course. There are many, many other types of ciphers. I mentioned Salsa 20 here. We'll see why in just a minute. But this is all for the quick historical survey. And now we can get into the more technical material.
In this segment, we're going to continue with a few more tools from discrete probability. And I want to remind everyone that if you want to read more about this, there's more information in this Wikibooks article that is linked over here. So first, let's do a quick recap of where we are. We said that discrete probability is always defined over a finite set, which we're going to denote by U. And typically for us, U is going to be the set of all n-bit binary strings, which we denote by 0, 1 to the n. Now, a probability distribution P over this universe U is basically a function that assigns to every element in the universe a weight in the interval 0 to 1, such that if we sum the weight of all these elements, the sum basically sums up to 1. Now, we said that a subset of the universe is what's called an event, and we said that the probability of an event is basically the sum of all the weights of the elements in the event. And we said that the probability of an event is some real number in the interval 0 to 1. And I want to remind everyone that basically the probability of the entire universe is basically 1 by the fact that the sum of all the weights sums up to 1. Then we defined what a random variable is. Formally, a random variable is a function from the universe to some other set. But the thing that I want you to remember is that the random variable takes values in some set V. And in fact, the random variable defines a distribution on this set V. So the next concept we need is what's called independence. And I'm going to very briefly define this. If you want to read more about independence, please go ahead and look at the Wikibooks article. But essentially, we say that two events A and B are independent of one another if when you know that event A happens, that tells you nothing about whether event B actually happened or not. Formally, the way we define independence is to say that the probability of A and B, namely that both events happen, is actually equal to the probability of event A times the probability of event B. So multiplication, in some sense, the fact that probabilities multiply under conjunction, captures the fact that these events are independent. And as I said, if you want to read more about that, please take a look at the background material. Now, the same thing can be said for random variables. So suppose we have two random variables, x and y, they take values in some set V. Then we say that these random variables are independent if the probability that x is equal to A and y is equal to B is equal to the product of these two probabilities. Basically, what this means is even if you know that x is equal to A, that tells you nothing about the value of y. Okay, that's what this multiplication means. And again, this needs to hold for all A and B in the space of values of these random variables. So just again, to jog your memory, if you've seen this before, a very quick example. Suppose we look at a set of 2-bit strings, so 0, 0, 0, 1, 1, 0, and 1, 1. And suppose we choose a random element from this set. Okay, so we randomly choose one of these 4 elements with equal probability. Now let's define two random variables. X is going to be the least significant bit that was generated, and y is going to be the most significant bit that's generated. So I claim that these random variables, x and y, are independent of one another. And the way to see that intuitively is to realize that choosing R uniformly from the set of 4 elements is basically the same as flipping a coin, an unbiased coin, twice. The first bit corresponds to the outcome of the first flip, and the second bit corresponds to the outcome of the second flip. And of course, there are 4 possible outcomes. All 4 outcomes are equally likely, which is why we get the uniform distribution over 2-bit strings. Now, variables x and y, why are they independent? Basically, if I tell you the result of the first flip, namely I tell you the least significant bit of r, so I tell you how the first coin, whether it fell on its head or fell on its tail, that tells you nothing about the result of the second flip. Which is why intuitively you might expect these random variables to be independent of one another. But formally, we would have to prove that for all 0-1 pairs, the probability of x equals 0 and y equals 0, x equals 1, y equals 1, and so on, these probabilities multiply. Let's just do it for one of these pairs. So let's look at the probability that x is equal to 0 and y is equal to 0. Well, you see that the probability that x is equal to 0 and y is equal to 0 is basically the probability that r is equal to 0, 0. And what's the probability that r is equal to 0, 0? Well, by the uniform distribution, that's basically equal to 1/4. That's 1 over the size of the set, which is 1/4 in this case. And well, lo and behold, that's in fact, these probabilities multiply because, again, the probability that x is equal to 0, the probability that the least significant bit of r is equal to 0, this probability is exactly 1/2, because there are exactly 2 elements that have their least significant bit equal to 0. 2 out of 4 elements gives you a probability of 1/2. And similarly, the probability that y is equal to 0 is also 1/2, so in fact the probabilities multiply. Okay, so that's this concept of independence. And the reason I wanted to show you that is because we're going to look at an important property of XOR that we're going to use again and again. So before we talk about XOR, let me just do a very quick review of what XOR is. So of course, XOR of 2 bits means the addition of those bits modulo 2. So just to kind of make sure everybody's on the same page, if we have 2 bits, so 0, 0, 0, 1, 1, 0, and 1, 1, their XOR, the truth table of the XOR, is basically just the addition modulo 2. You can see 1 plus 1 is equal to 2, modulo 2, that's equal to 0. So this is the truth table for the XOR, and I'm always going to denote XOR by this circle with a plus inside. And then when I want to apply XOR to bit strings, I apply the addition modulo 2 operation bitwise. So for example, the XOR of these 2 strings would be 1, 1, 0, and I guess I'll let you fill out the rest of the XORs just to make sure we're all on the same page. So of course it comes out to 1, 1, 0, 1. Now we're going to be doing a lot of XORing in this class. In fact, there's a classical joke that the only thing cryptographers know how to do is just XOR things together. But I want to explain to you why we see XOR so frequently in cryptography. Basically, XOR has a very important property, and the property is the following. Suppose we have a random variable y that's distributed arbitrarily over 0, 1 to the n. So we know nothing about the distribution of y. But now suppose we have an independent random variable that happens to be uniformly distributed also over 0, 1 to the n. So it's very important that x is uniform and that it's independent of y. So now let's define the random variable, which is the XOR of x and y. Then I claim that no matter what distribution y started with, this z is always going to be a uniform random variable. So in other words, if I take an arbitrarily malicious distribution and I XOR it with an independent uniform random variable, what I end up with is a uniform random variable. Okay, and this is again kind of a key property that makes XOR very useful for crypto. So this is actually a very simple fact to prove. Let's just go ahead and do it. Let's just prove it for 1 bit, so for n equals 1. Okay, so the way we'll do it is we'll basically write out the probability distributions for the various random variables. So let's see, for the random variable y, well, the random variable can be either 0 or 1. And let's say that p0 is the probability that it's equal to 0, and p1 is the probability that it's equal to 1. Okay, so that's one of our tables. Similarly, we're going to have a table for the variable x. Well, the variable x is much easier. That's a uniform random variable. So the probability that it's equal to 0 is exactly 1/2. Probability that it's equal to 1 is also exactly 1/2. Now let's write out the probabilities for the joint distribution. In other words, let's see what the probability is for the various joint values of y and x. In other words, how likely is it that y is 0 and x is 0, y is 0 and x is 1, y is 1 and x is 0, and 1, 1. Well, so what we do is basically, because we assume the variables are independent, all we have to do is multiply the probabilities. So the probability that y is equal to 0 is p0. Probability that x is equal to 0 is 1/2. So the probability that we get 0, 0 is exactly p0 over 2. Similarly, for 0, 1, we'll get P0 over 2. For 1, 0, we'll get P1 over 2. And for 1, 1, again, the probability that y is equal to 1 and x is equal to 1, well, that's P1 times the probability that x is equal to 1, which is a half. So it's P1 over 2. Okay, so those are the 4 probabilities for the various options for x and y. So now let's analyze what is the probability that z is equal to 0. Well, the probability that z is equal to 0 is basically the same as the probability that, let's write it this way, xy is equal to 0, 0, or xy is equal to 1, 1. Those are the 2 possible cases that z is equal to 0 because z is the XOR of x and y. Now these events are disjoint, so this expression can simply be written as the sum of the 2 expressions given above. So basically it's the probability that xy is equal to 0, 0 plus the probability that xy is equal to 1, 1. So now we can simply look up these probabilities in our table. So the probability that xy is equal to 0, 0 is simply p0 over 2. And the probability that xy is equal to 1, 1 is simply p1 over 2. So we get p0 over 2 plus p1 over 2. But what do we know about p0 and p1? Well, it's a probability distribution. Therefore, p0 plus p1 must equal 1. And therefore, this fraction here must equal to a half. p0 plus p1 is equal to 1. So therefore, the sum of these 2 terms must equal a half. And we're done. Basically, we proved that the probability that z is equal to 0 is 1/2. Therefore, the probability that z is equal to 1 is also 1/2. Therefore, z is a uniform random variable. So this simple theorem is the main reason why XOR is so useful in cryptography. The last thing I want to show you about discrete probability is what's called the birthday paradox. And I'm going to do it really fast here because we're going to come back later on and talk about this in more detail. So the birthday paradox says the following. Suppose I choose n random variables in our universe U. Okay, and it just so happens that these variables are independent of one another. They actually don't have to be uniform. All we need to assume is that they're distributed in the same way. The most important property, though, is that they're independent of one another. So the theorem says that if you choose roughly the square root of the size of U elements, we're kind of ignoring this 1.2 here. It doesn't really matter. But if you choose square root of the size of U elements, then basically there's a good chance that there are 2 elements that are the same. In other words, if you sample about square root of U times, then it's likely that 2 of your samples will be equal to one another. And by the way, I should point out that this inverted E just means exists. So there exists indices I and j such that Ri is equal to Rj. So here's a concrete example that we'll actually see many, many times. So suppose our universe consists of all strings of length 128 bits. So the size of U is gigantic. It's actually 2 to the 128. It's a very, very large set. But it so happens that if you sample, say, around 2 to the 64 times from the set, this is about the square root of U, then it's very likely that 2 of your sample messages will actually be the same. So why is this called the birthday paradox? Well, traditionally it's described in terms of people's birthdays. So you would think that each one of these samples would be someone's birthday. And so the question is, how many people need to get together so that there are 2 people that have the same birthday? So just as a simple calculation, you can see there are 365 days in the year. So you would need about 1.2 times the square root of 365 people until the probability that 2 of them have the same birthday is more than a half. This, if I'm not mistaken, is about 24, which means that if 24 random people get together in a room, it's very likely that 2 of them will actually have the same birthday. This is why it's called a paradox, because 24 supposedly is a smaller number than you would expect. Interestingly, people's birthdays are not actually uniform across all 365 days in the year. There's actually a bias towards September, but I guess that's not relevant to the discussion here. The last thing I wanted to do is just show you the birthday paradox a bit more concretely. So suppose we have a universe of about 1 million samples. Then you can see that when we sample roughly 1,200 times, the probability that we sample the same element twice is roughly a half. But the probability of sampling the same number twice actually converges very quickly to 1. You can see that if we sample about 2,200 items, then the probability that 2 of those items are the same already is 90%. And at 3000 it's basically 1. So this converges very quickly to 1 as soon as you go beyond the square root of the size of the universe. So we're going to come back and study the birthday paradox in more detail later on, but I just for now wanted you to know what it is. So that's the end of this segment, and then in the next segment we'll start with our first example encryption systems. Now that we understand stream ciphers, we're going to move on and talk about a more powerful primitive called a block cipher. So a block cipher is made up of two algorithms, E and D. These are encryption and decryption algorithms. And both of these algorithms take as input a key K. Now the point of a block cipher is that it takes an n-bit plaintext as input, and it outputs exactly the same number of bits as output. So it maps n bits of input to exactly n bits of output. Now there are two canonical examples of block ciphers. The first one is called triple des. In triple des, the block size, namely the number of input bits, is 64. So triple des will map 64-bit blocks to 64-bit blocks, and it does it using a key that's 168 bits long. We're going to talk about how triple des is built in the next segment. Another block cipher, which is more recent, is called AES. Now AES has slightly different parameters. So here the block size is 128 bits. So AES will map 128 bits of input to 128 bits of output. And it actually has three possible sizes of keys, and I wrote down these sizes over here. Basically, the longer the key, the slower the cipher is, but presumably the more secure it is to break. And we're going to talk about what it means for block ciphers to be secure in just a minute. Now, block ciphers are typically built by iteration. They take in as input a key K. For example, in the case of AES, the key could be 128 bits long. And the first thing that happens to the key is it gets expanded into a sequence of keys, K1 to Kn, called round keys. Now, the way the cipher uses these round keys is by iteratively encrypting the message again and again and again using what's called a round function. So here we have this function R that takes two inputs. This function R is going to be called a round function. It takes as input the round key, and it takes as input the current state of the message. So here we have our input message. Say for AES, the message would be 128 bits exactly, because each block in AES is exactly 128 bits. And then the first thing that happens is we apply the first round function using the key K1 to the message. And we get some new message out as a result. Then we take this message M1, we apply the next round function to it using a different key, using the key K2, and we get the next round message out. And so on and so forth until all the rounds have been applied. And then the final output is actually the result of the cipher. And again, this would be also in the case of AES, this was 128 bits. And the resulting ciphertext would also be 128 bits. Now, different ciphers have different number of rounds, and they have different round functions. So for example, for triple des, the number of rounds is 48, and we're going to see exactly how the round function for triple des works. For AES, for example, the number of rounds is only 10, and again, we're going to look at how the round functions for AES work as well in just a minute. Before we do that, I just wanted to mention performance numbers. So you can see here, these are the performance numbers for the two typical block ciphers, triple des and AES. And these are the corresponding numbers for the stream ciphers that we looked at in the previous module, RC4, Salsa, and Sosa Manuk. And you can see that the block ciphers are considerably slower than stream ciphers, but we'll see that we can do many things with block ciphers that we couldn't do very efficiently with constructions like RC4. Now, my goal for this week is to show you how block ciphers work, but more importantly, I want to focus on showing you how to use block ciphers correctly for either encryption or integrity or whatever application you have in mind. So to show you how to use block ciphers correctly, it actually makes a lot of sense to abstract the concept a little bit so that we have kind of a clean, abstract concept of a block cipher to work with, and then we can argue and reason about what constructions are correct and what constructions are incorrect. And so an abstraction, it's a very elegant abstraction of a block cipher, is what's called a pseudo-random function and a pseudo-random permutation. So let me explain what these things are. So a pseudo-random function basically is defined over a key space, an input space, and an output space. And all it is basically a function that takes a key and an input as inputs and outputs some element in the output space. Okay, so it takes an element in K, an element in X, and outputs an element in Y. And the only requirement, essentially, is that there's an efficient way to evaluate the function. For functions, we're not requiring that they be invertible. We just need them to be evaluatable given the key and the input X. Now, a related concept that more accurately captures what a block cipher is called a pseudo-random permutation. So a pseudo-random permutation is, again, defined over a key space and then just a set X. And what it does is it takes an element in the key space and an element in X and outputs basically one element in X. Now, as usual, the function E should be easy to evaluate, so there should be an algorithm to evaluate the function E. But more importantly, once we fix the key K, it's important that this function E be one-to-one. In other words, if you think of the space X as a set here, and here's the same set X again, then basically the function E, what it does is it's a one-to-one function, so every element in X gets mapped to exactly one element in X. And then because it's one-to-one, of course, it's also invertible. So given some output, there's only one input that maps to that output, and the requirement is that there's an efficient inversion algorithm, call it D, that given a particular output, will output the original preimage that mapped to that output. So really a pseudo-random permutation captures very accurately and syntactically what a block cipher is, and often I'll use the terms interchangeably, either a block cipher or a pseudo-random permutation. I'll use whichever term depending on the context where we're discussing things. Okay, so we have two examples, as we said, of pseudo-random permutations, triple des and AES. Say for AES 128, the key space would be 128 bits, and the output space would be 128 bits. For triple des, as we said, the block size is only 64 bits, and the key size is 168 bits. Okay, so we'll use these running examples actually throughout, so whenever I say a PRP, concretely, you should be thinking AES or triple des. Now, one thing that I wanted to point out is that, in fact, any pseudo-random permutation, namely any block cipher, you can also think of it as a PRF. In fact, a PRP is a PRF that has more structure. In particular, PRP is a PRF where the input space and the output space are the same, so X is equal to Y, and in fact is efficiently invertible once you have the secret key K. Okay, so in some sense, a PRP is a special case of a PRF, although that's not entirely accurate, and we'll see why in just a second. So far we just described the kind of the syntactic definition of what is a pseudo-random permutation and a pseudo-random function. So now let's talk about what it means for a PRF or a PRP to be secure, and this concept will essentially capture what it means for a block cipher to be secure. Okay, so this is why I wanted to show you these definitions before we look at actual block cipher constructions, so at least it's clear in your mind what it is we're trying to construct. Okay, so here we have a PRF, and I'm going to need a little bit of notation, not too much though, so I'm going to need to define the set funds of x, y. This is basically the set of all functions from the set x to the set y. Denoted here as a big circle, funds of x, y. Now this set is gigantic. Its size is basically, the size of y to the size of x. So for example, for AES, remember both x and y would be 2 to the 128. So for AES, the size of the set is enormous. It'll be 2 to the 128 times 2 to the 128. So it's kind of a double exponential. So this is a gigantic number. This is more particles than there are in the universe. But regardless, we can kind of think of this set abstractly. We never have to kind of write it down. We can just keep it in our head and not worry about computing on it. So this is a particular gigantic set of the set of all functions from x to y. Now we're going to look at a much smaller set of functions, namely I'll call this set S sub f, and that's going to denote the set of all functions from x to y that are specified by the PRF as soon as we fix a particular key k. Okay, so we fix the key k, we let the second argument float, and that basically defines a function from x to y. And we're going to look at the set of all such functions for all possible keys in the key space. Okay, so if you think about it again, for AES, if we're using 128-bit keys, the size of this, I'll say SAES, is basically going to be 2 to the 128. So much, much, much smaller than the set of all possible functions from x to y. And now we say that a PRF is secure basically if a random function from x to y, so literally we pick some arbitrary function in this gigantic set of all functions from x to y, and we say that the PRF is secure if in fact a random function from x to y is indistinguishable from a pseudo-random function from x to y, namely when we pick a random function from the set SF. Okay, so more precisely, basically, again, the uniform distribution on the set of pseudo-random function is indistinguishable from the uniform distribution on the set of all functions. Let me be just a little bit more precise, just to give you a little bit more intuition about what I mean by that, and then we'll move on to actual constructions. So let me be a bit more precise about what it means for a PRF to be secure. And so what we'll do is basically the following. So we have our adversary just trying to distinguish a truly random function from a pseudo-random function. So what we'll do is we'll let him interact with one of the two. So here in the top cloud, we're choosing a truly random function. In the bottom cloud, we're just choosing a random key for a pseudo-random function. And now what this adversary is going to do is he's going to submit points in x. So he's going to submit a bunch of x's. In fact, he's going to do this again and again and again. So he's going to submit x1, x2, x3, x4. And then for each one of those queries, we're going to give him either the value of the truly random function at the point x, or the value of the pseudo-random function at the point x. Okay, so the adversary doesn't know which one he's getting. By the way, for all queries, he's always getting either the truly random function or the pseudo-random function. In other words, he's either interacting with a truly random function for all his queries, or he's interacting with a pseudo-random function for all his queries. And we say that the PRF is secure if this poor adversary can't tell the difference. He cannot tell whether he's interacting with a truly random function or interacting with a pseudo-random function. Okay, and we're going to come back actually later on and define PRFs more precisely. But for now, I wanted to give you the intuition for what it means for a PRF to be secure, so you'll understand what it is that we're trying to construct when we construct these pseudo-random functions. And I should say that the definition for a pseudo-random permutation is pretty much the same, except instead of choosing a random function, we're going to choose a random permutation on the set x. In other words, a random one-to-one function on the set x. The adversary can either query this random function on the set x, or he can query a pseudo-random permutation, and the PRP is secure if the adversary cannot tell the difference. Okay, so again, the goal is to make these functions and permutations look like truly random functions or permutations. Okay, so let's look at a simple question. So suppose we have a secure PRF. So we know that this PRF f happens to be defined in the set x, and it so happens, it outputs 128 bits every time. It so happens that this PRF cannot be distinguished from a truly random function from x to 0, 1 to the 128. Now we're going to build a new PRF. Let's call this PRFG. And the PRFG is going to be defined as follows. We say if x is equal to 0, always output 0. Otherwise, if x is not equal to 0, just output the value of f. So my question to you is, do you think this G is a secure PRF? Well, so the answer, of course, is that it's very easy to distinguish the function G from a random function. All the adversary has to do is just query the function at x equals 0. For a random function, the probability that the result is going to be 0 is 1 over 2 to the 128. Whereas for the pseudo-random function, he's always going to get 0. Because at 0, the function is always defined to be 0 no matter what the key. And so all he would do is he would say, hey, I'm interacting with a pseudo-random function if he gets 0 at x equals 0. And he'll say, I'm interacting with a random function if he gets non-zero at x equals 0. So it's very easy to distinguish this G from random. So what this example shows is that even if you have a secure PRF, it's enough that on just one known input, the output is kind of not random. The output is fixed. And already the entire PRF is broken, even though you realize everywhere else the PRF is perfectly indistinguishable from random. Okay, so just to show you the power of PRF, let's look at a very easy application. I want to show you that in fact pseudo-random functions directly give us a very simple pseudo-random generator. Okay, so let's assume we have a pseudo-random function. So this one happens to go from n bits to n bits. And then let's define the following generator. Its seed space is going to be the key space for the PRF, and its output space is going to be basically t blocks of n bits each. Okay, so you can see the output is a total of n times t bits for some parameter t that we can choose. And it turns out basically you can do this very simple construction. This is sometimes called counter mode, where essentially you take the PRF and you evaluate it at 0, you evaluate it at 1, you evaluate it at 2, at 3, at 4, up to t, and you concatenate all these values. That's the generator. Okay, so we basically took the key for the PRF and we expanded it into n times t bits. Okay? A key property of this generator is that it's parallelizable. And what I mean by that is if you have two processors or two cores that you can compute on, then you can have one core compute the even entries of the output, and you can have another core compute the odd entries of the output. So basically, if you have two cores, you can make this generator run twice as fast as it would if you only have a single core. So the nice thing about this is, of course, we know that pseudo-random generators give us stream ciphers, and so this is an example of a parallelizable stream cipher. And I just wanted to point out that many of the stream ciphers that we looked at before, for example RC4, those were inherently sequential. So even if you had two processors, you couldn't make the stream cipher work any faster than if you just had a single processor. Now the main question is, why is this generator secure? And so here I'm only going to give you a little bit of intuition, and we're going to come back and argue this more precisely later on. But I'll just say that security basically follows directly from the PRF property. And the way we reason about security is we say, well, this PRF by definition is indistinguishable from a truly random function on 128 bits. So in other words, if I take this generator and instead I define a generator using a truly random function, in other words, I'll write the output of the generator as f of 0 concatenated f of 1 and so on and so forth, using a truly random function, then the output of the generator using the truly random function would be indistinguishable from the output of the generator using a pseudo-random function. That is the essence of the security property of a PRF. But with a truly random function, you notice that the output is just truly random, because for a truly random function, f of 0 is a random value, f of 1 is an independent random value, f of 2 is an independent random value, and so on and so forth. So the entire output is a truly random output. And so with a truly random function, this generator produces truly random output and is therefore a perfectly secure generator. And so you see how the PRF security property lets us argue security. Basically, we argue that when we replace the PRF with a truly random function, the construction is necessarily secure, and that says that the construction with a pseudo-random function is also secure. Okay, and we're going to see a couple more examples like this later on. So now you understand what a block cipher is, and you have intuition for what security properties it's trying to achieve. And in the next segment, we're going to look at constructions for block ciphers. So now that we understand what block ciphers are, let's look at a classic example called the data encryption standard. So just a quick reminder, block ciphers basically map n bits of input to n bits of output. And we talked about two canonical examples, triple DES and AES. In this segment, we're going to talk about DES, and we'll talk about triple DES actually in the next segment. And then I also mentioned before that block ciphers are often built by iteration. In particular, we're going to look at block ciphers that are built by a form of iteration where a key k is first expanded into a bunch of round keys, and then a round function is applied to the input message again and again and again. And essentially, after all these round functions are applied, we obtain the resulting ciphertext. Okay, and again, we're going to look at how DES, the data encryption standard, uses this format. I just want to be clear that in fact, to specify a block cipher of this type, one needs to specify the key expansion mechanism, and one needs to specify the round function. In the segment here, I'm going to focus on the round function. I'm not going to talk much about key expansion, but I just wanted to mention that in fact, key expansion is also a big part of describing how a block cipher works. Okay, so let's talk about the history of DES. Essentially, in the early 1970s, IBM realized that their customers are demanding some form of encryption. And so they formed a crypto group, and the head of that group was Horst Feistel, who in the early 70s designed a cipher called Lucifer. Now it's interesting, in fact Lucifer had a number of variations, but one of the later variations in fact had a key length that was 128 bits and a block length that's also 128 bits. Okay? In 1973, the government realized that it's buying many commercial off-the-shelf computers, and so it wanted its suppliers to actually have a good crypto algorithm that they could use in products sold to the government. So in 1973, the National Bureau of Standards, as it was called at the time, put out a request for proposals for a block cipher that's going to become a federal standard. And in fact, IBM submitted a variant of Lucifer. That variant actually went through some modification during the standardization process. And then finally, in 1976, the National Bureau of Standards adopted DES as a federal standard. And in fact, for DES, it's interesting that the key length was far reduced from Lucifer. It's only 56 bits, and the block length was also reduced to 64 bits. And in fact, these decisions, especially the decision to reduce the key length, is kind of the Achilles heel of DES and was a source of many complaints over its life. In particular, already back in 1997, DES was broken by exhaustive search, meaning that a machine was able to search through all 2 to the 56 possible keys to recover a particular challenge key. And in fact, we're going to talk about exhaustive search quite a bit. It's quite an interesting question, and there are various ways to defend against exhaustive search. And basically, this 1997 experiment kind of spelled the doom of DES. It meant that DES itself is no longer secure, and as a result, the National Institute of Standards, as it became known, issued a request for proposals for a next generation block cipher standard. And in 2000, it standardized on a cipher called Rindell, which became the Advanced Encryption Standard, AES, and we'll talk about AES later on. But in this segment, I want to describe how DES works. Now, DES as a cipher, it's an amazingly successful cipher. It's been used in banking industry. In fact, there's a classic network called the Electronic Clearinghouse, which banks use to clear checks with one another, and DES is used for integrity in those transactions. It's also used in commerce. In fact, it was very popular up until recently as the main encryption mechanism for the web. Of course, now that's been replaced with AES and other ciphers. Overall, it's a very successful cipher in terms of deployment. DES also has a very rich history of attacks, which we'll talk about in the next segment. Okay, so now let's talk about the construction of DES. So the core idea behind DES is what's called a Feistel network, due to Horst Feistel. And basically, it's a very clever idea for building a block cipher out of arbitrary functions f1 to fd. Okay, so imagine we have these functions f1 to fd that happens to map n bits to n bits. Now these are arbitrary functions. They don't have to be invertible or anything. What we want to do is build an invertible function out of those d functions. And the way we'll do it is by building a new function, we'll call it capital F, that maps 2 n bits to 2 n bits. And the construction is described right here. So here we have our input. You notice there are 2 blocks of n bits. In other words, the input is actually 2 n bits. R and L stand for right and left. Typically, people describe a Feistel network from top to bottom, in which case these n bits really would be right and left. But here it's more convenient for me to describe it horizontally. So if we follow the R input, you realize it basically gets copied into the L output without any change at all. Okay? However, the L input is changed somewhat. Basically, what happens is the R input is fed into the function f1, and the resultant is XORed with L0, and that becomes the new R1 input. Okay, so this is called one round of a Feistel network, and it's done using the function f1. Now we do this again with another round of the Feistel network with the function f2, and we do it again and again and again till we get to the last round, and we do it again with the function fd, and finally the output is rd ld. Okay, so if you like, we can write this in symbols, that basically li is simply equal to ri minus 1, and ri, let's see, that's the more complicated one, ri is equal, well, let's just follow the lines here, ri is just equal to fi applied to ri minus 1 XOR li. Okay, and this is basically I goes from 1 to d. So this is the equation that defines a Feistel network mapping a 2 n-bit input to 2 n-bit output. So here we have again, I just copied the picture of the Feistel network, and the amazing claim is that in fact it doesn't matter which functions you give me. For any functions f1 to fd that you give me, the resulting Feistel network function is in fact invertible. And the way we're going to prove that is basically we're going to construct an inverse, because not only is it invertible, it's efficiently invertible. So let's see. So let's look at one round of a Feistel network. So here, this is the input, Ri, Li, and this is the output, Ri plus 1, Li plus 1. And now what I'm going to ask you is to invert this. So let's see. So suppose now the input that we're given is Ri plus 1, Li plus 1. And we want to compute Ri, Li. So we want to compute the round in the reverse direction. So let's see if we can do it. Well, let's look at Ri. So Ri is very easy. Basically, Ri is just equal to Li plus 1. So Li plus 1 just becomes Ri. But now let me ask you to write the expression for Li in terms of Ri plus 1 and Li plus 1. So I hope everybody sees that basically Li plus 1 is fed into the function Fi plus 1. The result is XORed with Ri plus 1, and that gives the Li input. So this is the inverse of one round of a Feistel network. And if we draw this as a diagram, let's just write the picture for the inverse. So here you notice the input is Ri plus 1, Li plus 1, and the output is Ri, Li, right? So we're inverting the round. So you notice that the inverse of a Feistel round looks pretty much the same as the Feistel round in the forward direction. It's literally, just for a technical reason, it's kind of the mirror image of one another, but it's basically the same construct. And when we put these inverted rounds back together, we essentially get the inverse of the entire Feistel network. So you notice we start off with round number d, with the inverse of round number d, then we do the inverse of round number d minus 1, and so on and so forth, until we get to the inverse of the first round, and we get our final output, which is R0, L0. Right? This is the input, and we manage to invert basically RD, LD, and get R0, L0. And the interesting thing is that basically the inversion circuit looks pretty much the same as the encryption circuit, and the only difference is that the functions are applied in reverse order. Right? We started with FD and ended with F1, whereas when we were encrypting, we started with F1 and ended with FD. So for hardware designers, this is very attractive because basically if you want to save hardware, you realize that your encryption hardware is identical to your decryption hardware. So you only have to implement one algorithm and you get both algorithms the same way. The only difference is that the functions are applied in reverse order. Okay, so this Feistel mechanism is a general method for building invertible functions from arbitrary functions f1 to fd. And in fact, it's used in many different block ciphers, although interestingly, it's not actually used in AES. So there are many other block ciphers that use a Feistel network. Of course, they differ from DES in the functions f1 to fd, but AES actually uses a completely different type of structure that's actually not a Feistel network. We'll see how AES works in a couple of segments. So now that we know what Feistel networks are, let me mention an important theorem about the theory of Feistel networks that shows why they're a good idea. This theorem is due to Luby and Rockoff back in 1985, and it says the following. Suppose I have a function that is a secure pseudo-random function. Okay, so it's indistinguishable from random and happens to act on n bits. So it maps n bits to n bits and uses a key k. Then it turns out that if you use this function in 3 rounds of a Feistel network, what you end up with is a secure pseudo-random permutation. In other words, what you end up with is an invertible function that's indistinguishable from a truly random invertible function. And I hope you remember that the definition of a secure block cipher is that it needs to be a secure pseudo-random permutation. So what this theorem says is if you start with a secure pseudo-random function, you end up with a secure block cipher. Basically, that's what this says. Now let me explain in a little bit more detail what's actually going on here. So essentially, the PRF is used in every round of the Feistel network. So in other words, here what's actually computed is the PRF using one secret key, K0. Here what's computed is the PRF using a different secret key, of course applied to R1. And here we have yet another secret key, K1 applied, K2 applied to R2. And you notice this is why basically this Feistel construction uses keys in K cubed. In other words, it uses 3 independent keys. So it's very important that the keys are actually independent. So really we need 3 independent keys. And then we end up with a secure pseudo-random permutation. Okay, so that's the theory behind Feistel networks. And now that we understand that, we can actually look at the specifics of DES. So DES is basically a 16-round Feistel network. Okay, so there are functions f1 to f16 that map 32 bits to 32 bits, and as a result, the DES itself acts on 64-bit blocks, 2 times 32. Now, the 16-round functions in DES are actually all derived from a single function f, just used with different keys. So in fact, these are the different round keys. So ki is a round key, and it's basically derived from the key k, derived from the 56-bit DES key k. Okay, and I'll describe what this function f is in just a minute. But basically, you see that by using 16 different round keys, we get 16 different round functions, and that gives us the Feistel network. So just at a high level, how the DES works, basically you have a 64-bit input. The first thing it does is this initial permutation that just permutes the 64 bits around, namely it maps bit number 1 to bit number 6, bit number 2 to bit number 17, and so on. This is not for security reasons, this is just specified in the standard. Then we go into the 16-round Feistel network that actually you now know how it works. Basically uses the function f1 to f16 as specified before. And then basically we have another permutation, this is called the final permutation, That's just the inverse of the initial permutation. Again, it just permutes bits around. This is not necessary for security reasons. And then we finally get the final output. Okay, now as we said, there's a key expansion step, which I'm not going to describe. But basically this 56-bit DES key is expanded into these round keys, where each round key is 48 bits. Okay, so we have 16 48-bit round keys, and they're basically used in the 16 rounds of DES. And then when you want to invert the cipher, all you do is you use these round keys, these 16 round keys, in reverse order. Okay, so now that we understand the DES structure, the only thing that's left to do is specify the function capital F. So let me explain how this function works. So basically it takes as inputs its 32-bit value, let's call it X, but in reality you remember this is R0, R1, R2, R3, and so on and so forth. These are 32-bit values. And then it takes also a 48-bit round key. So here we have our key Ki, which happens to be 48 bits. The first thing it does is it goes through an expansion box. And this expansion box basically takes 32 bits and maps them into 48 bits. Now all the expansion box does is just replicate some bits and move other bits around. So for example, bit number 1 of X is replicated into positions 2 and 48 in the output. Bit number 2 of X is positioned in as bit number 3 of the output. And so on and so forth. Just by replicating some of the bits of X, we expand the input into 48 bits. The next thing we do is we compute an XOR with a round key. Sometimes people say that cryptographers only compute XORs. This is an example of that, where, well, we just do XORs in this function. And then comes the magic of DES, where actually these 48 bits are broken into 8 groups of 6 bits. 6, 7, 8. And so let me draw. And then what happens is, so each one of these wires is 6 bits. And then they go into what are called S boxes. And I'll explain the X boxes in just a minute. The X boxes are kind of the smarts of DES. S8, and then the S boxes basically map 6 bits to 4 bits. So the outputs of the S boxes are these 4 bits. They're collected. This gives us 32 bits, right? 8 groups of 4 bits gives us 32 bits. And then finally, this is fed into yet another permutation, which just maps the bits around. So for example, bit number 1 will go to bit number 9, bit number 2 will go to bit number 15, and so on. So it just permutes the 32 bits around. And that's the final 32-bit output of this F function. Okay? So by using different round keys, essentially we get different round functions, and that's how we form the 16 round functions of DES. Now, the only thing that's left to specify are these S boxes. So the S boxes literally are just functions from 6 bits to 4 bits, and they're just implemented as a lookup table, right? So describing a function from 6 bits to 4 bits basically amounts to writing the output of the function on all 2 to the 6 possible inputs. 2 to the 6 is 64, so we just have a table that literally contains 64 values, where each value is 4 bits. So here's an example. This happens to be the 5th S box, and you see that this is a table that contains 64 values, right? It's 4 by 16, so 64 values. And for example, if you want to look at the output that corresponds to 0, 1, 1, 0, 1, 1. Okay, then you look at these 2 bits, this is 0, 1, and you look at these 4 bits, this is 1, 1, 0, 1, and you see that the output is 1, 0, 0, 1. The 4 bits output 1, 0, 0, 1. Okay, so the S boxes are just implemented as these tables. Now the question is, how are these S boxes chosen? How are these tables actually chosen by the designers of DES? To give you some intuitions for that, let's start with a very bad choice for S boxes. So imagine the S boxes were linear. What do I mean by that? I mean that imagine that these 6-bit inputs literally were just XORed with one another in different ways to produce the 4-bit outputs. Okay, another way of writing that is that we can write the S box as a matrix vector product. So here you have the matrix AI and the vector, the 6-bit vector X. And you can see that if we write this matrix vector product, basically we take the inner product of this vector with the input vector. Remember, these are all bits. So the 6-bit vector, inner product, another 6-bit vector, and we do that modulo 2. you realize basically what we're computing is x2 XOR x3, right? Because only position 2 and position 3 have 1s in it. And similarly, the next inner product will produce x1 XOR x4 XOR x5, and so on and so forth. Okay, so you can literally see that if the S boxes are implemented this way, then all they do is just apply the matrix A to the input vector x, which is why we say that in this case the S boxes are completely linear. Now I claim that in fact if the S boxes were linear, then DES would be totally insecure. And the reason is, if the S boxes are linear, then all that DES does is just compute XOR of various things and permute and shuffle bits around. So it's just XORs and bit permutations, which means that as a result, all of DES is just a linear function. In other words, there will be a matrix B of these dimensions. Basically, it's a matrix B that has width 832. Basically, what I would do is I would write the 64-bit message plus the 16 round keys as one long vector, right? So the message is 64 bits, and there are 16 round keys, each one is 48, and that, if you do the math, it's basically 832. Okay, so I write these guys, the keys and the message, as one long vector, and then there would be this matrix that essentially, when you compute these matrix vector products, essentially you get the different bits of the ciphertext. So there's 64 of these rows, and as a result you get 64 bits of ciphertext. Okay, so this is what it means for DES to be linear. So if you think a little bit about this, you realize the S boxes are the only nonlinear part of DES. So if the S boxes were linear, then the entire circuit is linear, and therefore it can be expressed as this matrix. Now, if that's the case, then DES would be terrible as a secure pseudo-random permutation. And let me give you a very simple example. Basically, if you take the XOR of 3 outputs of DES, well, let's think what that means. Basically, we would be looking at B times the matrix B that defines DES times one vector, XOR B times another vector, XOR B times a third vector. We can take the B out of the parentheses, so we'd be basically doing B times this vector over here, but of course K XOR K XOR K XOR K, this is just K. And so if you think about what that means, basically we just got back DES of K at the point M1 XOR M2 XOR M3. But this means that now DES has this horrible relation that can be tested, right? So basically if you XOR the output of 3 values M1, M2, and 3, you'll get the value of DES at the point M1 XOR M2 XOR M3. Now this is not a relation that's going to hold for a random function. A random function is not going to satisfy this equality, and so you get a very easy test to tell you that DES is not a random function. And in fact, it's not even, maybe you can take that as a small exercise, it's not even difficult to see that given enough input-output pairs, you can literally recover the entire secret key. Yeah, you just need 832 input-output pairs, and you'll be able to recover the entire secret key. And so if the S boxes were linear, DES would be completely insecure. It turns out, actually, even if the S boxes were close to being linear, in other words, the S boxes were linear most of the time, so maybe for 60 out of the 64 inputs, the S boxes were linear, it turns out that would also be enough to break DES, and we're going to see why later on. In particular, if you choose the S boxes at random, it turns out they'll tend to be somewhat close to linear functions. As a result, you'll be able to totally break DES. You'll just be able to recover the key in basically very little time. And so the designers of DES actually specified a number of rules they use for choosing the S boxes. And it's not surprising, the first rule is that these functions are far away from being linear. Okay, so in other words, there is no function that agrees with a large fraction of the outputs of the S box. And then there are all these other rules. For example, they're exactly 4-to-1 maps, right? So every output has exactly 4 preimages, and so on and so forth. So we understand now why they chose the S boxes the way they did. And in fact, it's all done to defeat certain attacks on DES. Okay, so that's the end of the description of DES. And then in the next 2 segments, we're going to look at the security of DES. Now that we understand how DES works, let's look at a few attacks on DES. And we're going to start with an attack called exhaustive search. So our goal here is basically that given a few input-output pairs, MICI, our goal is to find a key that maps these M's to the C's. In other words, our goal is to find a key that maps M1, M2, M3 into C1, C2, C3. And as I said, our goal is to find a key that does this mapping. The first question is, how do we know that this key is unique? And so let's do a little bit of analysis to show that, in fact, just one pair is enough to completely constrain a DES key, and that's why this question makes sense. Okay, so let's see. So we're going to prove this simple lemma. Now let's assume that DES is what's called an ideal cipher. So what is an ideal cipher? Basically, we're going to pretend like DES is made up of random invertible functions. In other words, for every key, DES implements a random invertible function. Since there are 2 to the 56 keys in DES, we're going to pretend like DES really is a collection of 2 to the 56 functions that are invertible from 0, 1, 64 to 0, 1, 64. Okay, so of course DES is not a collection of 2 to the 56 random functions, but we can idealize the cipher and pretend that it is such a collection. Then what can we say? Then in fact, it turns out that just given one message and ciphertext, you just give me one pair, message and ciphertext, there is already only one key that maps this message to that ciphertext. So already, just given one pair, M and C, I can ask you, find me the key that maps M to C, and the solution is very likely to be unique. In fact, it's going to be unique with probability roughly 99.5%. I should say that this statement is true for all M and C, and the probability is just over the choice of the random permutation that make up the cipher. So let's do the proof. This is fairly straightforward. So what we're basically asking is, what's the probability that there exists some key that's not equal to k, such that, well, C we know is equal to DES of k comma m, by definition of C and m, but we're asking how likely is it that there's this other key k prime that also satisfies this equality. You realize that if this is true, if such a key k prime exists, then just given M and C, you can't decide whether the right key is K or K prime, because both of them work. Okay? But I want to argue that this happens with low probability. Well, so what does it mean that there exists a key K prime that satisfies this relation? Well, we're asking, what's the probability that the first key, the all0 key satisfies it, or the second key satisfies it, or the third key satisfies it, and so on and so forth. So by the union bound, we can bound this probability by the sum over all keys k prime, over all 56-bit keys, of the probability that des km is equal to des k prime m. Okay, so we're asking basically, what is this probability for a fixed key k prime that it happens to collide with the key k at the message m? Well, let's think about this for a second. Let's fix this value. Let's suppose it's some fixed value. And then we're asking, how likely is it that a random permutation pi k prime at the point m happens to produce exactly the same output as the key k at the point m? Well, it's not difficult to answer and see that in fact this is, for a single key k prime, the probability is at most 1 over 2 to the 64. Right? There are 2 to the 64 possible outputs for the permutation. What's the probability that it lands exactly on this output? Well, it's 1 over 2 to the 64. And we're summing over all 2 to the 56 keys. So we just multiply the 2. We get 1 over 2 to the 8, which is basically 1 over 256. Okay? So the probability that the key is not unique is 1 over 256. Therefore, the probability that it is unique is 1 minus that, which is 99.5%. Okay, so already, if you give me one plain text ciphertext pair, the key is completely determined. There's only one key that will map that plain text to that ciphertext, and the question is just, can you find that key? Now, it turns out, in fact, if you give me two pairs, so you give me M1 and M2, and their corresponding outputs, C1 and C2, the probability, basically, just do exactly the same analysis, the probability basically becomes 1, that there's only one such key. Okay, essentially, this is very, 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 very close to 1, and basically it says given two pairs, it's very, very likely that only one key will map this pair of messages to this pair of ciphertexts, and as a result, again, we can ask, well, find me that unique key. And by the way, the same is true for AES. If you look at AES 128, again, just given two input-output pairs, there's going to be only one key with very high probability. So essentially now we can ask for this exhaustive search problem. I give you 2 or 3 pairs, and I ask you, well, find me the key. So how are you going to do it? Well, you're going to do it by exhaustive search, essentially by trying all possible keys one by one until you find the right one. So this is what's known as the DES challenge. So let me explain how the DES challenge worked. The challenge was issued by a company called RSA, And what they did is basically they published a number of ciphertexts, but 3 of the ciphertexts had known plaintexts. So in particular, what they did is they took the message here, the unknown message is colon, and you can see they broke it up into blocks. If you look at these are basically 8-byte blocks. 8 bytes, as you know, is 64 bits. Right? So each one of these is 64 bits. And then they encrypted them using a secret key. They encrypted all using the same secret key to get kind of 3 ciphertexts. So this gives us 3 plaintext ciphertext pairs. And then they gave us a whole bunch of other ciphertexts, C4, C5, C6. And the challenge was decrypt these guys using the key that you found from an exhaustive search over the first 3 pairs that you were given. Okay. So that was called the DES challenge. And let me tell you a little bit about how long it took to solve it. So interestingly, in 1997, using an internet search, using distributed.net basically, they were able to search through enough of the key space to find the correct key in about 3 months. You realize the key space has size 2 to the 56, but on average you only have to search through half the key space to find the key, and so it took them 3 months. Then kind of a miraculous thing happened. The EFF actually contracted Paul Kocher to build special purpose hardware to break DES. This was a machine called DeepCrack. It cost about $250,000, and it broke the next DES challenge in only 3 days. Interestingly, by the way, RSA said that they would pay $10,000 for each solution of the challenge, so you can see that this is not quite economical. They spent $250K, they got $10,000 for solving the challenge. The next thing that happened is in 1999, RSA issued another challenge, and they said, well, you got to solve it in half the time of the previous solution. And so using both DeepCrack and the internet search together, they were able to break DES in 22 hours. So the bottom line here is essentially DES is completely dead. Essentially, if you forget or you lose your DES 56-bit key, don't worry. Within 22 hours, you can actually recover it. And in fact, anyone can recover it. And so DES essentially is dead and no longer secure. And just kind of a final nail in the coffin, as hardware technology improved, there was another project called Copacabana. They used FPGAs, just off-the-shelf FPGAs, only 120 FPGAs. It only cost $10,000, and they were able to do an exhaustive key search in about 7 days. So very, very cheap hardware, just off the shelf. You can break DES already very quickly. So the lesson from all this is essentially 56-bit ciphers are totally, totally dead. And so the question is what to do. People really liked DES. It was deployed in a lot of places. There were a lot of implementations. There was a lot of hardware support for it. So the question was what to do. And so the first thing that came to mind is, well, maybe we can take DES and we can kind of artificially expand the key size so we strengthen it against this exhaustive search attack. And the first idea that comes to mind is basically, well, let's iterate the block cipher a couple of times. And this is what's called triple DES. So triple DES is a general construction. Basically, it says the following. Suppose you give me a block cipher E. So here, it has a key space K, and it has a message space M, and an output space, of course, M as well. Let's define the triple construction, which now uses 3 keys. And it's defined as follows. Basically, here, the triple construction uses 3 independent keys, encrypts the same message block as before, and what it does is it will encrypt using the key K3, then it will decrypt using the key K2, and then it will encrypt again using the key K1. Okay, so it's basically encrypting 3 times using 3 independent keys. You might be wondering, why is it doing EDE? Why not just do EEE? Why do we have to have a D in the middle? Well, that's just for kind of a hack. You notice what happens if you set up K1 equals K2 equals K3? What happens if all 3 keys are the same? Well, basically, what would happen is one E and one D would cancel, and you would just get normal DES out. So it's just a hack so that if you have a hardware implementation of triple DES, you can set all 3 keys to be the same, and you'll get a hardware implementation of single DES. Of course, it'll be 3 times as slow as a regular implementation of single DES, but nevertheless, it's still an option. Okay, so for triple DES, in fact, now we get a key size that's 3 times 56, which is 168 bits. So this is 168 bits is way too long to actually do exhaustive search on. That will take time 2 to the 168, which is more than all the machines on Earth working for 10 years would be able to do. Unfortunately, of course, the cipher is 3 times slower than DES. So this is a real problem with triple DES. Now, I want to mention that, in fact, you might think that triple DES has security 2 to the 168, but in fact, there is a simple attack that actually runs in time 2 to the 118, and I want to show you how that attack works. Okay, so, but in fact, 2 to the 118 is still a large number. In fact, anything that's kind of bigger than 2 to the 90 is considered sufficiently secure. 2 to the 118 is definitely sufficiently secure against exhaustive search, and generally is considered a high enough level of security. So clearly, triple DES is 3 times as slow as DES. So the question is, why did they repeat the cipher 3 times? Why not repeat the cipher just 2 times? Or in particular, the question is, what's wrong with double DES? So here we have double DES. Basically, you see it uses only 2 keys, and it uses only 2 applications of the block cipher. And as a result, it's only going to be twice as slow as DES, not 3 times as slow as DES. Well, the key length for double DES is 2 times 56, which is 112 bits. And in fact, doing exhaustive search on a space of 112 bits is too much. 2 to the 112 is too big of a number to do exhaustive search over such a large space. So the question is, what's wrong with this construction? Well, it turns out this construction is completely insecure, and I want to show you an attack. So suppose I'm given a bunch of inputs, say M1 to M10, and I'm given the corresponding outputs C1 to C10. What's my goal? Well, my goal is basically to find keys, a pair of keys K1, K2, such that if I encrypt the message, the message capital M using these keys, in other words, if I do this encryption, this double DES encryption, then I get the ciphertext vector that was given to me. Okay, so our goal is to solve this equation here. Now you stare at this equation a little bit and you realize, hey, wait a minute, I can rewrite it in kind of an interesting way. I can apply the decryption algorithm, and then what I'll get is that I'm really looking for keys K1, K2 that satisfy this equation here, where basically all I did is I applied the decryption algorithm using K1 to both sides. Okay, now whenever you see an equation like this, what just happened here is that we separated our variables into 2 sides. The variables now appear on independent sides of the equation, and that usually means that there's a faster attack than exhaustive search. And in fact, this attack is called a meet-in-the-middle attack, where really the meet in the middle is going to somehow attack this particular point in the construction. Okay, so we're going to try and find a key that maps M to a particular value here and maps C to the same value. Okay, so let me show you how the attack works. So the first thing we're going to do is we're going to build a table. Here, let me clear up some space here. The first step is to build a table that for all possible values of K2 encrypts M under that value. Okay, so here we have this table. So you notice these are all, I'll say it like this, these are all 2 to the 56 DES keys, single DES keys. Okay, so the table has 2 to the 56 entries. And what we do is basically for each entry, we compute the encryption of M under the appropriate key. So this is the encryption of M under the all0 key, the encryption of M under the 1 key, and then at the bottom, we have the encryption of M under the all1 key. Okay, so there are 2 to the 56 entries, and we sort this table based on the second column. Okay, so far so good. So by the way, this takes time to build this table, takes time 2 to the 56, and I guess we also want to sort. Sorting takes n log n time, so it's 2 to the 56 times log 2 to the 56. Okay, so now that we have this table, we've essentially built all possible values in the forward direction for this point. Now what we're going to do is this meet in the middle attack, where now we try to go in the reverse direction with all possible keys K. Essentially, we compute the decryption of C under all possible keys K1. Okay, so now for each potential decryption, remember the table holds all possible values in the midpoint. So then for each possible decryption, we check, hey, is the decryption in the table, in the second column in the table? If it is in the table, then aha, we found a match. And then what do we know? We know that essentially, well, we found a match. So we know that, say, for example, a decryption using a particular key K1 happened to match this entry in the table, K sub 2, or more generally Ki, then we know that the encryption of M under Ki is equal to the decryption of C under K. Okay, so we kind of build this meet in the middle where the 2 sides, the encryption of M under Ki and the decryption of C under K collided. But if they collided, then we know that in fact this pair, ki and k, is equal to the pair that we're looking for. And so we've just solved our challenge. So now let's look at what's the running time of this. Well, we had to build a table and then sort it. And then for all possible decryptions, we had to do a search through the table. So there were 2 to the 56 possible decryption. Each search in a sorted table takes log of 2 to the 56 time. If you just work it out, this turns out to be 2 to the 63, which is way smaller than 2 to the 112. Okay, so this is a serious attack. It's probably doable today. That runs in a total time of 2 to the 63, which is about the same time as the exhaustive search attack on DES. So really, double DES really didn't solve the exhaustive search problem because, well, there's an attack on it that runs in about the same time as exhaustive search on single DES. Now, someone might complain that in fact this algorithm, well, we have to store this big table, so it takes up a lot of space, but, you know, so be it. That's nevertheless, the running time is still quite smaller, significantly smaller than 2 to the 112. Now you notice, by the way, the same attack applies to triple DES. What you would do is you would implement a man-in-the-middle attack against this point. You would build a table of size 2 to the 56 of all possible encryptions of M, and then you would try to decrypt with all 2 to the 112 keys until you find a collision, and when you find a collision, you've basically found K1, K2, K3. Okay, so even triple DES has an attack that basically explores only 2 to the 112 possible keys. But 2 to the 112 is a large enough number, so triple DES, in fact, as far as we know, is sufficiently secure. I should mention that triple DES is actually a NIST standard, and so triple DES is actually used quite a bit. And in fact, DES should never, ever be used. If for some reason you're forced to use some version of DES, use triple DES, not DES. Okay, I want to mention one more method for strengthening DES against exhaustive search attacks. This method actually is not standardized by NIST because it doesn't defend against more subtle attacks on DES. But nevertheless, if all you're worried about is exhaustive search and you don't want to pay the performance penalties of triple DES, then this is an interesting idea. So let me show you how it works. So let E be a block cipher that operates on n-bit blocks. We're going to define the EX construction, and for DES we're going to get DESX to be the following. So we use 3 keys, K1, K2, K3, and then basically before encryption we XOR with K3, then we encrypt using K2, and then after encryption we XOR with K1. That's it. That's the whole construction. So basically, you notice it doesn't slow the block cipher much because all we did is we applied the cipher plus 2 additional XORs, which are super fast. The key length for this is in fact, well, we got 2 keys that are as long as the block size, and we got 1 key that's as long as the key size, so the total is 184 bits. Now, it turns out actually the best attack that's known is actually an attack that takes time 2 to the 120, and it's actually fairly simple. So it's a generic attack on EX. It will always take time, basically the block size plus the key size, and it's a simple homework problem for you to try to figure out this attack. I think this is a good exercise. Okay, in fact, there's some analysis to show that there is no exhaustive search attack on this type of construction. So it's a fine construction against exhaustive search, but there are more subtle attacks on DES that we'll talk about in the next segment that basically this construction will not prevent. One thing that I want to point out, unfortunately I found this mistake in a number of products, is if you just decide to XOR on the outside, or if you just decide to XOR on the inside, as opposed to XORing on both sides, which is what DESX does. You notice DESX XORs both on the outside and on the inside. If you just do one of them, then basically this construction does nothing to secure your cipher. It'll still be as vulnerable to exhaustive search as the original block cipher E. Okay, so this is another homework problem, and actually you'll see that as part of our homeworks. Okay, so this basically concludes our discussion of exhaustive search attacks, and next we'll talk about more sophisticated attacks on DES. There is an immense literature on attacking block ciphers. In this segment, I just want to give you a taste for what these attacks look like, and I hope I'll convince you that you should never, ever design your own block cipher and just stick to the standards like triple DES and AES. The first set of attacks I want to talk about are attacks on the implementation of the block cipher. As an example, imagine you have a smart card that's implementing a block cipher. So the smart card, for example, could be used for credit card payments and might have a secret key inside of it to authenticate your credit card payments as you stick the card into a payment terminal, say. So now if an attacker obtains your smart card, what he could do is he could actually take the smart card to a lab and then run the card and measure very precisely how much time the card took to do encryption and decryption. Now, if the amount of time that the implementation took to do encryption depends on bits of the secret key, then by measuring the time, the attacker will learn something about your secret key, and in fact, he might even be able to completely extract your secret key. And there are many examples of implementations that simply by measuring the time very precisely for many operations of encryption algorithm, you can completely extract the secret key. Another example is rather than just measuring the time, you could actually measure the power consumption of the card as it's operating. So literally, you can connect it to a device that will measure the current that the card is drawing and then graph the current very, very precisely. Now, these cards are not very fast, and as a result, you can actually measure the exact amount of power consumed at every clock cycle as the card was executing. When you do that, you actually get graphs of this form. So this is an example of a smart card operating while it's doing the DIS computation. So you can see very clearly, here's when it was doing the initial permutation, here's when it's doing the final permutation, and then here you can count there are actually 16 hills and troughs corresponding to the 16 rounds. And essentially, when you zoom in on a graph like this, you can basically read the key bits off one by one just by looking at how much power the card consumed as it was doing the different operations. It turns out that even cards that take steps to mask this type of information are still vulnerable. There's an attack called a differential power analysis, where basically you measure the power consumed by the card over many runs of the encryption algorithm. And as long as there's any even small dependence between the amount of current consumed and the bits of the secret key, basically that dependence will show up after enough runs of the encryption algorithm, and as a result you'll be able to completely extract the secret key. Okay, so these attacks were actually discovered by Paul Kocher and his colleagues up at Kriptografi Research, and there's actually a fairly large industry devoted to just defending against these power attacks. As far as timing attacks are concerned, I want to mention that these are real. They're not just about smart cards. For example, you can imagine a multi-core processor where the encryption algorithm is running on one core and the attacker code happens to be running on another core. Now, these cores actually share the same cache, and as a result, an attacker can actually look at the exact cache misses that the encryption algorithm incurred. It turns out that by looking at cache misses, you can completely figure out the secret key used by the algorithm. So one core can essentially extract information from the other core just by looking at cache misses. So implementing these block ciphers is actually quite subtle because you have to make sure that the side channel attacks don't leak information about your secret key. Another type of attack that's been discussed in the literature is what's called a fault attack. So here, basically, if you're attacking a smart card, you can actually cause the smart card to malfunction, perhaps by overclocking it, perhaps by warming it up. Essentially, you can cause the processor to malfunction and output erroneous data. It turns out that if during encryption there are errors in the last round of the encryption process, that the resulting ciphertexts that are produced are enough to actually expose the secret key K. It's quite an interesting result that in fact if you have any errors, if you ever output a wrong result, that actually could completely compromise your secret key. So of course the defense against this means that before you output the result of your algorithm, you should check to make sure that the correct result was computed. Now of course that's non-trivial, because how do you know that the error didn't happen in your checking algorithm? But there are known ways around that. So basically you can actually compute something 3 or 4 times, take majority over all those results, and be assured that the output really is correct as long as not too many faults occurred inside of your computation. These are attacks on the implementation. I hope these examples kind of show you that not only should you not invent your own block ciphers, you should never even implement these crypto primitives yourself, because A, you have to make sure there are no side channel attacks on your implementation, and B, you have to make sure that the implementation is secure against fault attacks. Okay, so instead you should just use standard libraries like the ones available in OpenSSL and many other libraries out there. So don't implement these primitives yourself, just use existing libraries. Alright, so now I want to turn to kind of more sophisticated attacks on block ciphers, and I'll particularly talk about how these attacks apply to DES. Okay, so these attacks were discovered by Biham and Shamir back in 1989, and I'll particularly describe a version of the attack discovered by Matsui in 1993. So the goal here is basically, given many input-output pairs, can we actually recover the key better than exhaustive search? So anything that runs better than exhaustive search already counts as an attack on the block cipher. Okay, so the example I want to give you is what's called linear cryptanalysis. And here, imagine it so happens that C is the encryption of M using key K. And suppose it so happens that if I look at a random key and a random message, somehow there's a dependence between the message, ciphertext, and the key bits. In particular, if I XOR a subset of the message bits, so this is just a subset of the message bits, if I XOR that with a certain subset of the ciphertext bits, so these two the attacker sees. The attacker has the message and the attacker has the ciphertext. And then you compare that to an XOR of a subset of the key bits. Now, if the two were completely independent, which is what you'd like, you definitely don't want your message and your ciphertext to somehow predict your key bits. If the two are like completely independent, then this equality will hold with probability exactly 1/2. But suppose it so happens that there's a bias, and this probability holds with probability half plus epsilon for some small epsilon. It so happens that in fact for DES, there is such a relation. The relation holds specifically because of a bug in the design of the fifth S-box. It turns out the fifth S-box happens to be too close to a linear function, and that linear function basically, as it propagates through the entire DES circuit, generates a relation of this type. You notice this is basically a linear relation that's being computed here. So this small, tiny linearity in the fifth S-box generates this relation over the entire circuit where the epsilon is tiny. Epsilon is 1/2^21, and I wrote down what that is. So the bias is really small, but nevertheless there is a bias using these particular subsets of bits. Now I'm not going to show you how to derive this relation, or I'm not going to show you even what it is. I'll just tell you how to use a relation like this once you find it. Okay, so here's our relation that we have, and the question is how to use it. So with a little bit of statistics, you can actually use an equation like this to determine some of the key bits. And here's how you do it. Suppose you were given 1/epsilon² message ciphertext pairs, and these have to be independently random messages and the corresponding ciphertexts. What you would do is you would use the formula above. In fact, you would use the left-hand side of the formula above to compute this relation between the message and ciphertext for all the pairs you were given. Now, what do you know? You know that for half plus epsilon of these values, you know that these things will be equal to an XOR of the key bits. So if you take majority over all the values you've computed, it turns out it's not so difficult to see that in fact you'll get the correct prediction for the XOR of the key bits with probability 97.7%. In other words, if this relation happens to be correct more than half the time, then the majority will be right. And because there's a bias, there's an epsilon bias, the probability that you will be correct more than half the time is in fact 97.7%, in which case the majority in fact will give you the correct XOR of the key bits. Okay, so this is kind of cool. Within 1/epsilon² time, you can figure out an XOR of a bunch of key bits. So now let's apply this to DES. So for DES we have epsilon, which is 1/21, which means that if you give me 2⁻42 input-output pairs, I can figure out an XOR of the key bits. And now it turns out, I'm not going to exactly show you how, roughly speaking, using this method, you don't just get one key bit. In fact, you get two key bits. You can kind of use this relation, one's going in a forward direction and one's going in the backwards direction. So that gives you two XORs of bits of the secret key. Okay, so that's 2 bits of information about the secret key. And then it turns out you can get 12 more bits because essentially you can figure out what the inputs are to the fifth S-box. Okay, so I'm not going to exactly show you how, but it turns out you can get 12 more bits, which is a total of 14 bits overall. So now using this method, you've recovered 14 bits of the secret key, and of course it took you time 2⁻42. Okay, so then what do you do? Well, so the rest of it is easy. Now what you're going to do is you're going to do exhaustive search on the remaining bits. Well, how many remaining bits are there? Well, there are 42 remaining bits, so the exhaustive search would take you time 2⁻42. So what's the total attack time? Well, the first step of the algorithm to determine the 14 bits took 2⁻42 time, and the remaining brute force search also took 2⁻42 time. So overall, the attack took 2⁻43 time. Okay, so now this is much better than exhaustive search. Within 2⁻43 time, we broke DES, but of course this required 2⁻42 random input-output pairs, whereas exhaustive search only required 3 pairs. Okay, so this is a fairly large number of input-output pairs that are needed, but given such a large number, you can actually recover the key faster than exhaustive search. Okay, so what's the lesson in all this? The lesson is firstly, any tiny bit of linearity, basically in the fifth S box, which was not designed as well as the other S boxes, basically led to an attack on the algorithm. Okay, a tiny bit of linearity already introduced this linear attack. And I want to emphasize again that this is not the sort of thing you would think of when you design a cipher. And so again, the conclusion here is there are very subtle attacks on block ciphers, one which you will not be able to find yourself. And so just stick to the standards. Don't ever design your block cipher. Okay, so that's all I want to say about sophisticated attacks. Now let's move on to the last type of attack that I want to mention, which I'll call quantum attacks, which are, again, these are generic attacks on all block ciphers. So let me explain what I mean by this. So first of all, let's look at a generic problem. It's a generic search problem. Suppose I have a function on some large domain X that happens to output either 0 or 1. And it so happens that this function is mostly 0, and there's like maybe one input where the function happens to evaluate to 1. And your goal is basically, find me the input where the function happens to be 1. Maybe there's only one such input, but your goal is to find it. Well, so on a classical computer, what can you do? The function is given to you. It's given to you as a black box. So the best you can do is just try all possible inputs. So this is going to take time, which is linear in the size of the domain. Now, it turns out there's an absolutely magical result that says that if you build a computer that's based on quantum physics as opposed to classical physics, you can solve this problem faster. So let me explain what I mean by this. So first of all, in the 70s and 80s, it was observed, I think it was actually Richard Feynman who observed this initially, that said that it turns out to be very difficult to simulate quantum experiments on a classical computer. So Feynman said, hey, if that's the case, maybe these quantum experiments are computing things that a classical computer can't compute. So they're somehow able to compute very quickly things that are very difficult to do classically. And that turned out to be correct. And in fact, the example I want to show you is one of these amazing things that, in fact, if you could build a quantum computer that's using quantum physics, then in fact you can solve this search problem not in time x, but in time square root of x. So somehow, even though the computer doesn't know anything about the function f, it's treating it as a black box, nevertheless, it's able to find a point when the function is 1 in times square root of x. I'm not going to explain this here, but at the end of the class, we're going to have an advanced topics lecture. And if you'd like me to explain how this algorithm works, I can explain it in that advanced topics lecture. It's actually quite interesting. And in fact, quantum computers have quite an impact on crypto. And again, as I said, I can explain this in the very last lecture. All right. So what does this have to do with breaking block ciphers? So far, it's just a generic search problem. Well, actually, I guess I should say before I show you the application, I should mention that, well, you might be wondering, well, can someone build a quantum computer? And this is still completely unknown. But at this point, nobody really knows if we can build large enough quantum computers to actually take advantage of this beautiful algorithm due to Grover. All right, so what does this have to do with block ciphers? Well, so suppose I give you a message and a ciphertext pair. Just one or just a few. We can define a function as follows. It's a function on k. It's a function on the key space. And the function will basically output 1 if it so happens that the encryption of M with K maps to C, and it will output 0 otherwise. Now we argue that basically this is exactly the type of function that's 1 at one point in the key space, and that's it. So by Grover's algorithm, we can actually find the secret key in times square root of K. So what does that mean? For DES, this would totally destroy DES. This would say that in time 2 to the 28, you can find a key. 2 to the 28 is about 200 million, so 200 million steps, which is, this takes a millisecond on a modern computer. This would totally destroy DES. But even AES with 128-bit keys, you would be able to find the secret key in time roughly 2 to the 64. And 2 to the 64 is these days considered insecure. That's within the realm of exhaustive search. And so basically, if somebody was able to build a quantum computer, we would then say that AES 128 is no longer secure. Instead, if somebody, if tomorrow you open up the newspaper and you read an article that says, so-and-so built a quantum computer, the consequence of all that is that you should immediately move to block ciphers that use 256 bits. Because then the running time of Grover's algorithm is 2 to the 128, which is more time than we consider feasible. And basically, there are example ciphers with 256 bits, for example, AES 256. This is one of the reasons why AES was designed with 256 bits in mind, But to be honest, this is not the only reason. There are other reasons why you wanted to have larger key sizes. Okay, so this is, as I said, just a taste of the different attacks on block ciphers, and I'm going to leave it at that. If we decide on quantum for the last topic of the course, then we'll cover that in the very last lecture. Over the years, it became clear that DES and triple DES are simply not designed for modern hardware and are too slow. As a result, NIST started a new process to standardize on a new block cipher called the Advanced Encryption Standard, or AES for short. NIST started this effort in 1997 when it requested proposals for a new block cipher. It received 15 submissions a year later, and finally in the year 2000 it adopted the cipher called Rindel as the Advanced Encryption Standard. This was a cipher designed in Belgium, and we already said that its block size is 128 bits, and it's got three possible key sizes, 128 bits, 192, and 256. And now the assumption is that the larger the key size is, the more secure the block cipher is as a pseudo-random permutation. But because it also has more rounds involved in its operation, the slower the cipher becomes. So the larger the key, supposedly the more secure the cipher, but also the slower it becomes. So for example, AES 128 is the fastest of these ciphers, and AES 256 is the slowest. Now AES is built as what's called a substitution permutation network. It's not a Feistel network. Remember that in a Feistel network, half the bits were unchanged from round to round. In a substitution permutation network, all the bits are changed in every round, and the network works as follows. So here we have the first round of the substitution permutation network, where the first thing we do is we XOR the current state with the round key, in this case the first round key. Then we go through a substitution layer where blocks of state are replaced with other blocks based on what the substitution table says. And then we go through a permutation layer where bits are permuted and shuffled around. And then we do this again. We XOR with the next round key, we go through a substitution phase, and we permute the bits around. And so on and so on and so forth until we reach the final round where we XOR with the very last round key, and then out comes the output. Now, an important point about this design is that, in fact, because of how it's built, every step in this network needs to be reversible so that the whole thing is reversible. And so the way we would decrypt, essentially, is we would take the output and simply apply each step of the network in reverse order. So we start with a permutation step, and we have to make sure that step is reversible. Then we look at the substitution layer, and we have to make sure this step is reversible. And this is very different from DES. In DES, if you remember, the substitution tables were not reversible at all. In fact, they mapped 6 bits to 4 bits, whereas here, everything has to be reversible, otherwise it would be impossible to decrypt. And of course, the XOR with the round key is reversible as well. Okay, so inversion of a substitution permutation network is simply done by applying all the steps in the reverse order. So now that we understand the generic construction, let's look at the specifics of AES. So AES operates on a 128-bit block, which is 16 bytes. So what we do with AES is we write those 16 bytes as a 4x4 matrix. Each cell in the matrix contains 1 byte. And then we start with the first round. So we XOR with the first round key. And then we apply a certain function that includes substitutions and permutations and other operations on the state. And again, these 3 functions that are applied here have to be invertible so that, in fact, the cipher can be decrypted. And then we XOR with the next round key, and we do that again. Again, we apply the round function and XOR with the round key, and we do that again and again and again. We do it 10 times, although interestingly, in the last round, the mixed column step is actually missing. And then finally, we XOR with the last round key, and out comes the output. Again, at every phase here, we always keep this 4x4 array, and so the output is also 4x4, which is 16 bytes, which is 128 bits. Now, the round keys themselves, of course, come from a 16-byte AES key using key expansion. So the key expansion maps us from a 16-byte AES key into 11 keys, each one being 16 bytes. So these keys themselves are also a 4x4 array that's XORed into the current state. Okay, so that's the schematic of how AES works, and the only thing that's left to do is specify these 3 functions, byte sub, shift row, and mixed column. And those are fairly easy to explain. So I'm just going to give you the high-level description of what they are, and those interested in the details can look it up online. So the way byte substitution works is literally it's one S box containing 256 bytes. And essentially what it does is it applies the S box to every byte in the current state. So let me explain what I mean by that. So the current state is going to be this 4x4 table. So here we have the 4x4 table. And to each element in this table, we apply the S box. So let's call it the A table. And then what we do is essentially for all 4x4 entries, essentially the next step, Aij, becomes the current step evaluated at the lookup table. So we use the current cell as an entry, as an index into the lookup table, and then the value of the lookup table is what's output. Okay, so that's the first step. The next step that happens is shift row step, which is basically just a permutation. So essentially we kind of do a cyclic shift on each one of the rows. So you can see the second row is cyclically shifted by 1 position, the third row is cyclically shifted by 2 positions, and the third row is cyclically shifted by 3 positions. And the last thing we do is mix columns, where literally we apply a linear transformation to each one of these columns. So there's a certain matrix that multiplies each one of these columns, and it becomes the next column. So this linear transformation is applied independently to each one of the columns. Now I should point out that so far shift rows and mixed columns are very easy to implement in code, and I should say that the byte substitution itself is also easily computable, so that you can actually write code that takes less than 256 bytes to write, and you can kind of shrink the description of AES by literally storing code that computes the table rather than hardwiring the table into your implementation. And in fact, this is kind of a generic fact about AES, that if you kind of allow no pre-computation at all, including computing the S box on the fly, then in fact you get a fairly small implementation of AES, so it could fit on very constrained environments where there isn't enough room to hold complicated code. But of course this would be the slowest implementation because everything is computed now on the fly, and as a result the implementation obviously is going to be slower than if things were pre-computed. And then there's this trade-off. For example, if you have a lot of space and you can support large code, you can actually pre-compute quite a bit of the 3 steps that I just mentioned. In fact, there are multiple options of pre-computations. You can build a table that's only 4 kilobyte big, or you can build a table that's even longer, maybe 24 kilobytes. So basically you'll have these big tables in your implementation, but then your actual performance is going to be really good because all you're doing is just table lookups and XORs. You're not doing any other complicated arithmetic. And as a result, if you can do a lot of pre-computation, these 3 steps here, byte sub, shift rows, and mixed columns, can be converted just into a small number of table lookups and some XORs. All you can do is just compute the S box, so now your implementation would just have 256 bytes hard-coded. The rest would just be code that's actually computing these 3 functions. The performance would be slower than in the previous step, but the code footprint would also be smaller. So, and overall, there's this nice trade-off between code size and performance. So on high-end machines, on high-end servers, where you can afford to have a lot of code, you can pre-compute and store these big tables and get the best performance. Whereas on low-end machines like 8-bit smart cards, or think of like an 8-bit wristwatch, you would actually have a relatively small implementation of AES, but as a result, of course, it won't be so fast. So here's an example that's a little unusual. Suppose you wanted to implement AES in JavaScript, so you can send an AES library to the browser and have the browser actually do AES by itself. So in this case, what you'd like to do is you'd like to both shrink the code size so that on the network there's minimum traffic to send the library over to the browser, but at the same time you'd like the browser performance to be as fast as possible. So this is something that we did a while ago. Essentially the idea is that the code that actually gets sent to the browser doesn't have any pre-computed table, and as a result it's fairly small code, but then the minute it lands on the browser, what the browser will do is it will actually pre-compute all the tables. So in some sense the code goes from this being small and compact, it gets bloated with all these pre-computed tables, but those are stored on the laptop, which presumably has a lot of memory. And then once you have the pre-computed tables, you actually encrypt using them, and that's how you get the best performance. Okay, so if you have to send an implementation of AES over the network, you can kind of get the best of all worlds, where the code over the network is small, but when it reaches the target client, it can kind of inflate itself and then get the best performance as it's doing encryption on the client. Now, AES is such a popular block cipher. Now, essentially, when you build crypto into products, essentially you're supposed to be using AES. And as a result, Intel actually put AES support into the processor itself. So since Westmere, there are special instructions in the Intel processor to help accelerate AES. And so I listed these instructions here. They come in two pairs, AES enc and AES enc last. And then there's AES keygen assist. So let me explain what they do. So AES enc essentially implements one round of AES, namely apply the three functions in the XOR with the round key. And AES enc last basically implements the last round of AES. Remember, the last round didn't have the mixed columns phase. It only had the subs bytes and shift rows. And so that's what AES enc last does. And the way you call these instructions is using 128-bit registers, which correspond to the state of AES. And so you would have one register containing the state and one register containing the current round key. And then when you call AES enc on these two registers, basically they would run one round of AES and place the result inside this XMM1 state register. And as a result, if you wanted to implement the whole AES, all you would do is you would call AES enc 9 times, and then you would call AES enc last 1 time, and these 10 instructions are basically the entire implementation of AES. That's it. It's that easy to implement AES on this hardware. And they claim because these operations are now done inside the processor, not using external instructions, they're implemented in the processor, they claim that they can get a 14x speed up over, say, an implementation that's running on the same hardware, but implementing AES without these special instructions. So this is quite a significant speed up, and in fact there are now lots of products that make use of these special instructions. And let's just say that this is not specific to Intel. If you're an AMD fan, AMD also implemented exactly kind of similar instructions in their Bulldozer architecture and further in future architectures. Okay, so let's talk about the security of AES. I want to mention just two attacks here. Obviously, AES has been studied quite a bit, but the only two attacks on the full AES are the following two. So first of all, if you wanted to do key recovery, the best attack basically is only 4 times faster than exhaustive search, which means that instead of a 128-bit key, really you should be thinking of AES as a 126-bit key, because exhaustive search really is kind of 4 times faster than it should. Of course, 2 to the 126 is still more time than we have to compute, and this really does not hurt the security of AES. The more significant attack actually is on AES 256. It turns out there's a weakness in the key expansion design of AES, which allows for what's called a related key attack. So what's a related key attack? Essentially, if you give me about 2 to the 100 input-output pairs for AES, but from 4 related keys. So these are keys that are very closely related. Namely, key number 2 is the same as key number 1, except that a few bits of key number 1 have been flipped. Similarly, key number 3 is the same as key number 1, except that a few bits are flipped, and the same for key number 4. These are very closely related keys. If you like, their Hamming distance is very short. But if you do that, then in fact, there is a 2 to the 100 attack. Now you should say, well, 2 to the 100 is still impractical. This is still more time than we can actually run today. But nevertheless, the fact that it's so much better than an exhaustive search attack is so much better than 2 to the 256 is kind of a limitation of the cipher. But generally, it's not a significant limitation because it requires related keys. And so in practice, of course, you're supposed to be choosing your keys at random so that you have no related keys in your system, and as a result, this attack wouldn't apply. But if you do have related keys, then there's a problem. So this is the end of the segment, and in the next segment, we're going to talk about more provably secure constructions for block ciphers. In this segment, we ask whether we can build block ciphers from simpler primitives like pseudorandom generators. And we're going to show that the answer is yes. So to begin with, let's ask whether we can build pseudorandom functions as opposed to pseudorandom permutations from a pseudorandom generator. Okay? Can we build a PRF from a PRG? Our ultimate goal, though, is to build a block cipher, which is a PRP. And we'll get to that at the end. Okay, for now we build a PRF. So let's start with a PRG that doubles its input. Okay, so the seed for this PRG is an element in K, and the output is actually 2 elements in K. So here we have a schematic of this generator that basically takes as input a seed in K and outputs 2 elements in K as its output. And now what does it mean for this PRG to be secure? Recall, this means that essentially the output is indistinguishable from a random element inside of K squared. Now it turns out it's very easy to define basically what's called a 1-bit PRF from this PRG. So what's a 1-bit PRF? It's basically a PRF whose domain is only 1 bit. Okay, so it's a PRF that just takes 1 bit as input. Okay, and the way we'll do it is we'll say if the input bit x is 0, output the left output, and if the input bit x is 1, output the right output of the PRF. Okay, in symbols, basically we have what we wrote here. Now it's straightforward to show that in fact if G is a secure PRG, then this 1-bit PRF is in fact a secure PRF. If you think about it for a second, this is really a tautology. It's really just stating the same thing twice. So I'll leave it for you to think about this briefly and see and convince yourself that in fact this theorem is true. The real question is whether we can build a PRF that actually has a domain that's bigger than just 1 bit. Ideally, we'd like the domain to be 128 bits, just say as AES has. So the question is, can we build a 128-bit PRF from a pseudo-random generator? Well, so let's see if we can make progress. So the first thing we're going to do is we're going to say, well, again, let's start with a PRG that doubles its input. Let's see if we can build a PRG that quadruples its input. Okay, so it goes from k to k to the 4th instead of k to k squared. Okay, so let's see how to do it. So here we start with our original PRG that just doubles its input. But now remember, the fact that this is a PRG means that the output of the PRG is indistinguishable from 2 random values in k. Well, if the output looks like 2 random values in k, we can simply apply the generator again to those 2 outputs. So let's say we apply the generator once to the left output and once to the right output. And we're going to call the output of that, this quadruple of elements, we're going to call that G1k. And I wrote down in symbols what this generator does, but you can see basically from this figure exactly how the generator works. Okay, so now that we have a generator from k to k to the 4th, we actually get a 2-bit PRF. Namely, what we'll do is we'll say, given 2 bits, 0, 0, 0, 1, 1, 0, or 1, 1, we'll simply output the appropriate block that's the output of G1k. Okay, so now we can basically have a PRF that takes 4 possible inputs as opposed to just 2 possible inputs as before. So the question you should be asking me is, why is this G1k secure? Why is it a secure PRG? That is, why is this quadruple of outputs indistinguishable from random? And so let's do a quick proof of this. We'll just do a simple proof by pictures. So here's our generator that we want to prove is secure. And what that means is we want to argue that this distribution is indistinguishable from a random 4-tuple in k to the 4th. Okay, so our goal is to prove that these 2 are indistinguishable. Well, let's do it one step at a time. We know that the generator is a secure generator. Therefore, in fact, the output of the first level is indistinguishable from random. In other words, if we replace the first level by truly random strings, these 2 are truly random picked in the key space, then no efficient adversary should be able to distinguish these 2 distributions. In fact, if you could distinguish these 2 distributions, it's easy to show that you would break the original PRG. Okay, but essentially you can see that the reason we can do this replacement, we can replace the output of G with truly random values, is exactly because of the definition of the PRG, which says that the output of the PRG is indistinguishable from random, so we might as well just put random there, and no efficient adversary can distinguish the resulting 2 distributions. Okay, so far so good. But now we can do the same thing again to the left-hand side. In other words, we can replace these 2 pseudo-random outputs by truly random outputs. And again, because the generator G is secure, no efficient adversary can tell the difference between these 2 distributions. Put differently, if an adversary can distinguish these 2 distributions, then we would also get an attack on the generator G. And now finally, we're going to do this one last time. We're going to replace this pseudo-random pair by a truly random pair, and then lo and behold, we get the actual distribution that we were shooting for. We will get a distribution that's really made of 4 independent blocks. And so now we've proved this transition basically that these 2 are indistinguishable, these 2 are indistinguishable, and these 2 are indistinguishable, and therefore these 2 are indistinguishable, which is what we wanted to prove. Okay, so this is kind of the high-level idea for the proof. It's not too difficult to make this rigorous, but I just wanted to show you kind of the intuition for how the proof works. Well, if we were able to extend the generator's output once, there's nothing preventing us from doing it again. So here's the generator G1 that outputs 4 elements in the key space. And remember, the output here is indistinguishable from a random 4-tuple. That's what we just proved. And so there's nothing preventing us from applying the generator again. So we'll take the generator, apply it to this random looking thing, and we should be able to get this random looking thing, this pair over here that's random looking. And we can do the same thing again and again and again. And now basically we've built a new generator that outputs elements in k to the 8th as opposed to k to the 4th. And again, the proof of security is pretty much the same as the one I just showed you. Essentially, you gradually change the outputs into truly random outputs. So we would change this to a truly random output, then this, then that, then this, then that, and so on and so forth. Until finally we get something that's truly random, and therefore the original two distributions we started with, G2K and truly random, are indistinguishable. Okay, so far so good. So now we have a generator that outputs elements in k to the 8th. Now if we do that, basically we get a 3-bit PRF. In other words, at 0, 0, 0, this PRF would output this block, and so on and so forth, until the 1, 1, 1, it would output this block. Now the interesting thing is that in fact this PRF is easy to compute. So for example, suppose we wanted to compute the PRF at the point 1, 0, 1. Okay, it's a 3-bit PRF. So 1, 0, 1. How would we do that? Well, basically we would start from the original key k, and now we would apply the generator g, but we would only pay attention to the right output of g, because the first bit is 1. And then we will apply the generator again, but we would only pay attention to the left output of the generator, because the second bit is 0. And then we would apply the generator again and only pay attention to the right outputs, because the third bit is 1, and that would be the final output. Right? So you can see that that led us to 1, 0, 1, and in fact, because the entire generator is pseudorandom, we know in particular that this output here is pseudorandom. Okay, so this gives us a 3-bit PRF. Well, if it worked 3 times, there's no reason why it can't work n times. And so if we apply this transformation again and again, we arrive at what's called the GGM PRF. GGM stands for Goldreich, Goldwasser, and Micali. These are the inventors of this PRF. And the way it works is as follows. So we start off with a generator that just doubles its output. And now we're able to build a PRF that acts on a large domain, namely a domain of size 0, 1 to the n, where n could be as big as 128 or even more. So let's see. Suppose we're given an input in 0, 1 to the n. Let me show you how to evaluate the PRF. Well, by now you should actually have a good idea for how to do it. Essentially, we start from the original key, and then we apply the generator, and we take either the left or the right side, depending on the bit x0. And then we arrive at the next key, k1. And then we apply the generator again, and we take the left or the right side, depending on x1, and we arrive at the next key. And then we do this again and again, until finally we arrive at the output. So we've processed all n bits, and we arrive at the output of this function. And basically, we can prove security, again, pretty much along the same lines as we did before. And we can show that if G is a secure PRG, then in fact we get a secure PRF on 0, 1 to the n, on a very large domain. So that's fantastic. So now we have, essentially, we have a PRF that's provably secure, assuming the underlying generator is secure. And a generator is supposedly much easier to build than an actual PRF. And in fact, it works on blocks that could be very large, in particular 0, 1 to the 128, which is what we needed. So you might ask, well, why is this thing not being used in practice? And the reason is that it's actually fairly slow. So imagine we plug in as a generator, imagine we plug in the salsa generator. So now to evaluate this PRF at 128-bit inputs, we would basically have to run the salsa generator 128 times, 1 time per bit of the input. But then we would get a PRF that's 128 times slower than the original salsa, and that's much, much, much slower than AES. AES is a heuristic PRF, but nevertheless, it's much faster than what we just got here. And so even though this is a very elegant construction, it's not used in practice to build pseudorandom functions, although in a week we will be using this type of construction to build a message integrity mechanism. So the last step is basically, now that we have built a PRF, the question is whether we can actually build a block cipher. In other words, can we actually build a secure PRP from a secure PRG? Everything we've done so far is not reversible. Again, if you look at this construction here, we can't decrypt. Basically, given the final output, it's not possible to go back, or at least we don't know how to go back to the original input. So now the question of interest is, can we actually solve the problem we wanted to solve initially? Namely, can we actually build a block cipher from a secure PRG? So I'll let you think about this for a second and mark the answer. So of course I hope everybody said the answer is yes, and you already have all the ingredients to do it. In particular, you already know how to build a PRF from a pseudorandom generator. And we said that once we have a PRF, we can plug it into the Luby-Rokov construction, which, if you remember, was just a 3-round Feistel. So we said that if you plug a secure PRF into a 3-round Feistel, you get a secure PRP. So combining these two together basically gives us a secure PRP from a pseudorandom generator. And this is provably secure as long as the underlying generator is secure. So it's a beautiful result, but unfortunately, again, it's not used in practice because it's considerably slower than heuristic constructions like AES. Okay, so this completes our module on constructing pseudorandom permutations and pseudorandom functions. And then in the next module, we're going to talk about how to use these things to do proper encryption. Now that we know what block ciphers are and we know how to construct them, let's see how to use them for secure encryption. But before that, I want to briefly remind you of an important abstraction called a pseudorandom function and a pseudorandom permutation. So as we said in the last module, block ciphers map n bits of inputs to n bits of outputs, and we saw two examples of block ciphers, triple DES and AES. Now, an important abstraction of the concept of a block cipher is captured by this idea of a PRP and a PRF. And remember that a pseudorandom function, a PRF, basically is a function that takes two inputs. It takes a key and an element in some set X, and it outputs an element in some set Y. And for now, the only requirement is that there's an efficient algorithm to evaluate this function. We're going to talk about security for PRFs in just a minute. And then similarly, there's a related concept called a pseudorandom permutation, which is similar to a PRF. In fact, there's also an efficient algorithm to evaluate the pseudorandom permutation. However, there's an additional requirement that there's also an algorithm D that will invert this function E. So a PRP is basically a PRF, but where the function is required to be 1-to-1 for all keys, and there's an efficient inversion algorithm. So now let's talk about how to define secure PRFs. So we already said that essentially the goal of a PRF is to look like a random function from the set X to Y. So to capture that more precisely, we defined this notation funds xy to be the set of all functions from the set X to the set Y. Similarly, we defined the set S sub f to be the set of all functions from the set X to Y that are defined by the PRF. In other words, once you fix the key K, you obtain a function from the set X to the set Y, and the set of all such functions given a particular PRF would be the set S sub f. So as we said last time, funds xy is generally a gigantic set of all functions from X to Y. I think I mentioned that, in fact, for AES, where X and Y are 2 to the 128, the size of this set is 2 to the 128 times 2 to the 128. It's a double exponential, which is an absolutely enormous number. On the other hand, the number of functions defined by the AES block cipher is just 2 to the 128, namely one function from each key. And what we'd like to say is that a random choice from this huge set is indistinguishable from a random choice from this small set. And what do we mean by indistinguishable? We mean that an adversary who can interact with a random function in here can't distinguish that interaction from an interaction with a random function in here. Now let's define that more precisely. So we're going to, as usual, define two experiments, experiment 0 and experiment 1, and our goal is to say that the adversary can't distinguish these two experiments. So in experiment 0, the challenger basically is going to choose a random pseudo-random function. Okay, so he's going to fix the key K at random, and that's going to define this function little f over here to be one of the functions implemented by the PRF. In experiment 1, on the other hand, the challenger is going to choose a truly random function from the set X to the set Y, and again, we're going to call this truly random function little f. Either way, in either experiment 0 or experiment 1, the challenger ends up with this little function f that's either chosen from the PRF or chosen as a truly random function from X to Y. Now, the adversary basically gets to query this function little f. So he gets to submit a query x1, and he obtains the value of f at the point x1. Then he gets to submit an x2, and he obtains the value of f at the point x2. And so on and so forth. He makes q queries, and so he learns the value of the function little f at those q points. And now his goal is to say whether the function little f is chosen truly at random from funds xy or chosen just from the set of functions implemented by the PRF. So he outputs a certain bit b prime, and we'll refer to that output as the output of experiment, either experiment 0 or experiment 1. And as usual, we say that the PRF is secure if in fact the adversary can't distinguish these two experiments. In other words, the probability that he outputs 1 in experiment 0 is the same, pretty much the same, as the probability that he outputs 1 in experiment 1. In other words, the difference of these two probabilities is negligible. So this captures nicely the fact that the adversary couldn't distinguish a pseudo-random function from a truly random function from the set x to y. Now the definition for a secure pseudo-random permutation, a secure PRP, which is basically a secure block cipher, is pretty much the same. In experiment 0, the adversary is going to choose a random instance of the PRP, so he's going to choose a random k and define little f to be the function that corresponds to little k within the pseudo-random permutation. In experiment 1, the adversary is going to choose not a truly random function from x to y, but a truly random one-to-one function from x to x. Okay, so the goal of our PRP is to look like a random permutation from x to x, namely a random one-to-one function from the set x to itself. So the little function, little f here, is again going to be a random function from the set x to itself. And again, the challenger ends up with this function, little f. As before, the adversary gets to submit queries, and he gets to see the results of those queries, and then he shouldn't be able to distinguish, again, experiment 0 from experiment 1. So again, given the value of the function f at q points chosen by the adversary, he can't tell whether the function f came from a PRP or whether it's a truly random permutation from x to x. So let's look at a simple example. Suppose the set x contains only 2 points, 0 and 1. In this case, perms x is really easy to define. Essentially, there are 2 points, and we're looking at 0, 1, and we're asking what is the set of all invertible functions on the set 0, 1? Well, there are only 2 such functions. One function is the identity function, and the other function is basically the function that does crossovers, namely this function here. These are the only 2 invertible functions in the set 0, 1. So really, perms x only contains 2 functions in this case. Now let's look at the following PRP. The key space is going to be 0, 1, and of course x is going to be 0, 1. And let's define the PRP as basically x XOR k. Okay, so that's our PRP. And my question to you is this a secure PRP? In other words, is this PRP indistinguishable from a random function on perms x? I hope everybody said yes, because essentially the set of functions implemented in this PRP is identical to the set of functions in perms x. So a random choice of key here is identical to a random choice of function over here, and as a result, the 2 distributions, either pseudo-random or random, are identical. So clearly an adversary can't distinguish the 2 distributions. Now, we already said that we have a couple of examples of secure PRPs, triple DES and AES. And I just wanted to mention that if you want to make things very concrete, here's a concrete security assumptions about AES. Just to give an example, say that all algorithms that run in time 2 to the 80 have advantage against AES of at most 2 to the minus 40. This is a reasonable assumption about AES, and I just wanted to state it for concreteness. So let's look at another example. Consider again the PRP from the previous question, namely x XOR k. Remember the set x was just 1 bit, namely the values 0 and 1. And this time we're asking, is this PRP a secure PRF? In other words, is this PRP indistinguishable from a random function from x to x? Now the set of random functions from x to x, funds xx, in this case contains only 4 elements. There are the 2 invertible functions, which we already saw, namely the identity function and the negation function, the function that sends 0 to 1 and 1 to 0. But there are 2 other functions, namely the function that sends everything to 0 and the function that sends everything to 1. Okay? These are 4 functions inside funds of xx. And the question is this PRP that we just looked at, is it also indistinguishable from a random choice from funds xx? So I hope everybody said no, and the reason it's not a secure PRF is because there's a simple attack. Namely, the attacker is supposed to distinguish whether he's interacting with this PRP or is he interacting with a random function from funds xx. And the distinguisher is very simple. Basically, we're going to query the function at both x equals 0 and x equals 1. And then if we get a collision, in other words, if f of 0 is equal to f of 1, then for sure we're not interacting with a PRP, in which case we can just output 1. In other words, we're interacting with a random function. In other words, we say 0. So let's look at the advantage of this distinguisher. Well, when it's interacting with a PRP, will never output a 1 because f of 0 can never be equal to f of 1. In other words, the probability of outputting 1 is 0. However, when we interact with a truly random function in funds xx, the probability that f of 0 is equal to f of 1 is exactly 1/2, because half the functions satisfy f of 0 is equal to f of 1, and half the functions don't. So then we'll output 1 with probability 1/2. So the advantage of this distinguisher is 1/2, which is non-negligible, and as a result, this PRP here is not a secure PRF. Now it turns out this is only true because the set X is very small, and in fact there's an important lemma called the PRF switching lemma that says that a secure PRP is in fact a secure PRF whenever the set X is sufficiently large. And by sufficiently large, I mean, say, the output space of AES, which is 2 to the 128. So by this lemma, which we'll state more precisely in a second, AES, if it's a secure PRP, it is also a secure PRF. So the lemma basically says the following: if you give me a PRP over the set X, then for any adversary that queries the PRP at most Q points, so it makes at most Q queries into the challenge function, then the difference between its advantage in attacking the PRP when compared to a random function is very close to its advantage in distinguishing the PRP from a random permutation. In fact, the difference is bounded by this quantity here. And since we said that x is very large, this quantity, q squared over 2x, is negligible. Okay, that's going to be our goal. So essentially, when x is large, say 2 to the 128, q, say, is going to be 2 to the 32, that's a billion queries that the adversary makes, then still the ratio is going to be negligible, in which case we say that the adversary's advantage in distinguishing the PRP from a random function is pretty much the same as its advantage in distinguishing the PRP from a random permutation. So again, if E is already a secure PRP, then it's already a secure PRF. So for AES we believe is a secure PRP, and therefore AES we can also use it as a secure PRF. And so as a final note, I just want to mention that really from now on, you can kind of forget about the inner workings of AES and triple DES. We're simply going to assume that both are secure PRPs, and then we're going to see how to use them. But whenever I say PRP or PRF, you should be thinking in your mind basically AES or triple DES. So as our first example, let's look at a very simple way of using a block cipher for encryption. In particular, we'll see how to use a block cipher with a one-time key. So in this segment, we're just going to use the block cipher to encrypt using keys that are used one time. In other words, all the adversary gets to see is one ciphertext, and his goal is to break semantic security of that ciphertext. Now in the next segment, we're going to turn into more interesting applications of block ciphers, and we're going to see how to encrypt using keys that are used many, many times to encrypt many messages. So before we start, I want to mention that there is like a classic mistake in using a block cipher. Unfortunately, there are some products that actually work this way, and they are badly broken, so I want to make sure that none of you guys actually make this mistake. So this mode of operation is called an electronic codebook, and it works as follows. It's the first thing that comes to mind when you want to use a block cipher for encryption. What we do is we take our message, we break it into blocks, each block as big as the block cipher block. So in the case of AES, we would be breaking our message into 16-byte blocks. And then we encrypt each block separately. So this mode is often called electronic codebook, and unfortunately it's terribly insecure because you realize if two blocks are equal, for example here these two blocks happen to be equal, then necessarily the resulting ciphertexts are also going to be equal. So an attacker who looks at the ciphertext, even though he might not know what's actually written in these blocks, will know that these two blocks are equal, and as a result he learns something about the plaintext that he shouldn't have learned. And if this isn't clear enough for you abstractly, the best way to explain this is using a picture. And so here's this guy here that has this really dark black hair. And when we encrypt this image, this bitmap image, using electronic codebook mode, you see that his hair that contains lots of ones basically always gets encrypted the same way, so that his silhouette actually is completely visible even in the encrypted data. Okay, so this is a nice example of how the electronic codebook mode can actually leak information about the plaintext that could tell something to the attacker. So the question is how to correctly use block ciphers to encrypt long messages. And so I just want to briefly remind you of the notion we're trying to achieve, which is basically semantic security using a one-time key. So the adversary outputs two messages, M0 and M1, and then he gets either the encryption of M0 or the encryption of M1. These are two different experiments. And then our goal is to say that the adversary can't distinguish between these two experiments. So he can't distinguish the encryption of M0 from the encryption of M1. And the reason we call this security for a one-time key is that the key is only used to encrypt a single message, and as a result, the adversary will ever only see one ciphertext encrypted using this key. Okay, so the first thing we want to show is that in fact the mode that we just looked at, electronic codebook, in fact is not semantically secure. And this is true as long as you're encrypting more than one block. So here's an example. Suppose we encrypt 2 blocks using a block cipher. Let me show you that in fact electronic codebook would not be secure. So here's what we would do. So we're the adversary. So we would output 2 messages, M0 and M1, where in one message the blocks are distinct, and in the other message the blocks are the same. The 2 blocks are equal to one another. Well, so what is the challenger going to do? The challenger is going to encrypt either M0 or M1. Either way, we're going to get 2 blocks back. So the ciphertext actually contains 2 blocks. The first block is going to be an encryption of the word hello, and the second block is going to be either an encryption of the word hello or the word world. And then if the 2 ciphertext blocks are the same, then the adversary knows that he received an encryption of the message hello, hello. And if they're different, he knows that he received an encryption of the message hello, world. Okay, so he just follows the simple strategy here. And if you think about it for a second, you'll see what his advantage is. So what is the advantage? Well, this adversary, when he receives an encryption of the message M1, he will always output 0. And when he receives an encryption of the message M0, he will always output 1. And because of that, the advantage basically is 1, which means that the scheme is not secure, which again shows you the electronic codebook is not semantically secure and should never ever be used to encrypt messages that are more than 1 block long. So what should we do? Well, so here's a simple example. What we could do is we could use what's called the deterministic counter mode. So in the deterministic counter mode, basically we build a stream cipher out of the block cipher. So suppose we have a PRF, F. So again, you should think of AES when I say that. So AES is also a secure PRF. And what we'll do is basically we'll evaluate AES at the point 0, at the point 1, at the point 2, up to the point L. This will generate a pseudo-random pad, and we'll XOR that with all the message blocks and recover the ciphertext as a result. Okay, so really this is just a stream cipher that's built out of a PRF like AES and triple DES, and it's a simple way to do encryption. I wanted to just very quickly show you the security theorem. In fact, we've already seen the security theorem when it applied to stream ciphers using pseudo-random generators, so I'm not going to repeat this again. I'll just remind you that essentially for every adversary A that's trying to attack deterministic counter mode, we prove that there's an adversary B that's trying to attack the PRF. And since this quantity is negligible because the PRF is secure, we obtain that this quantity is negligible, and therefore the adversary has negligible advantage in defeating deterministic counter mode. And the proof in pictures is a really simple proof, so I'll just show it to you one more time for completeness. So basically what we want to show is when the adversary is given the encryption of the message M0, here this is the encryption of the message M0, M0 XOR counter applied to the PRF, versus in giving the encryption of the message M1, we want to argue that these 2 distributions are computationally indistinguishable. So the way we do that is basically we say, well, the top distribution, if instead of a PRF, we use a truly random function, namely here f is a truly random function, then the adversary, because of the property of the PRF, the adversary cannot distinguish these 2 experiments, right? A PRF is indistinguishable from a truly random function. Therefore, when we replace the PRF on the left with a truly random function on the right, the adversary is going to behave the same. Basically, he can't distinguish these 2 distributions. But now, because f is a truly random function, the pad here is a truly one-time pad, and therefore no adversary can distinguish an encryption of M0 from an encryption of M1 under the one-time pad. So again, these 2 distributions are the same. In fact, here there's an actual equality. These 2 distributions literally are the same distribution. And similarly, again, when we go back from a truly random function here to a PRF, because the PRF is secure, the adversary can't distinguish these 2 bottom distributions, the left from the right. And so by following these 3 qualities, basically we've proven that the things we wanted to prove equal are actually computationally indistinguishable. Okay, so that's a very simple proof to show that deterministic counter mode is in fact secure, and it's basically the same proof as we had when we proved that a stream cipher gives us semantic security. Okay, so that completes this segment, and in the next segment we'll talk about modes that enable us to use a key to encrypt multiple messages. In this segment, we will look at how to use block ciphers to encrypt multiple messages using the same key. This comes up in practice, for example, in file systems where the same key is used to encrypt multiple files. It comes up in networking protocols where the same key is used to encrypt multiple packets. So let's see how to do it. The first thing we need to do is to define what does it mean for a cipher to be secure when the same key is used to encrypt multiple messages. When we use the key more than once, the result of that is that the adversary gets to see many ciphertexts encrypted using the same key. As a result, when we define security, we're going to allow the adversary to mount what's called a chosen plaintext attack. In other words, the adversary can obtain the encryption of arbitrary messages of his choice. So for example, if the adversary is interacting with Alice, the adversary can ask Alice to encrypt arbitrary messages of the adversary's choosing, and Alice will go ahead and encrypt those messages and give the adversary the resulting ciphertexts. You might wonder, why would Alice ever do this? How can this possibly happen in real life? But it turns out this is actually very common in real life, and in fact this modeling is quite a conservative modeling of real life. For example, the adversary might send Alice an email. When Alice receives the email, she writes it to her encrypted disk, thereby encrypting the adversary's email using her secret key. If later the adversary steals this disk, then he obtains the encryption of an email that he sent to Alice under Alice's secret key. So that's an example of a chosen plaintext attack where the adversary provided Alice with a message and she encrypted that message using her own key, and then later the attacker was able to obtain the resulting ciphertext. So that's the adversary's power, and then the adversary's goal is basically to break semantic security. So let's define this more precisely. As usual, we're going to define semantic security under a chosen plaintext attack using two experiments, experiment 0 and experiment 1, that are modeled as a game between a challenger and an adversary. When the game begins, the challenger is going to choose a random key k, and now the adversary basically gets to query the challenger. So the adversary begins by submitting a semantic security query, namely he submits two messages, M0 and M1. I added another index, but let me ignore that extra index for a while. So the adversary submits two messages, M0 and M1, that happen to be of the same length, and then the adversary receives the encryption of one of those messages, either of M0 or of M1. In experiment 0, he receives the encryption of M0. In experiment 1, he receives the encryption of M1. So far this would look familiar. This looks exactly like a standard semantic security game. However, in a chosen plaintext attack, the adversary can now repeat this query again. So now he can issue a query with two other chosen plaintexts, again of the same length, and again he would receive the encryption of one of them. In experiment 0, he would receive the encryption of M0. In experiment 1, he would receive the encryption of M1. And the attacker can continue issuing queries like this. In fact, we'll say that he can issue up to Q queries of this type. Again, remember, every time he issues a pair of messages that happen to be of the same length, and every time he either gets the encryption of the left side or the right side. Again, in experiment 0, he will always get the encryption of the left message. In experiment 1, he will always get the encryption of the right message. And then the adversary's goal is basically to figure out whether he is in experiment 0 or in experiment 1. In other words, whether he was constantly receiving the encryption of the left message or the encryption of the right message. So in some sense, this is a standard semantic security game, just iterated over many queries that the attacker can issue adaptively, one after the other. Now, the chosen plaintext attack is captured by the fact that if the attacker wants the encryption of a particular message M, what he could do is, for example, use query J for some J, where in this query J he'll set both the 0 message and the 1 message to be exactly the same message M. In other words, both the left message and the right message are the same, and both are set to the message M. In this case, what he will receive, since both messages are the same, he knows that he's going to receive the encryption of this message M that he was interested in. So this is exactly what we meant by a chosen plaintext attack, where the adversary can submit a message M and receive the encryption of that particular message M of his choice. So some of his queries might be of this chosen plaintext flavor, where the message on the left is equal to the message on the right, but some of the queries might be standard semantic security queries, where the two messages are distinct, and that actually gives him information on whether he's in experiment 0 or in experiment 1. Now, by now, you should be used to this definition where we say that the system is semantically secure under a chosen plaintext attack if for all efficient adversaries, they cannot distinguish experiment 0 from experiment 1. In other words, the probability that at the end they output B prime, which we're going to denote by the output of experiment B, this output will be the same whether they're in experiment 0 or experiment 1. So the attacker couldn't distinguish between always receiving encryptions of the left messages versus always receiving encryptions of the right messages. So in your mind, I'd like you to be thinking of an adversary that is able to mount a chosen plaintext attack, namely be given the encryption of arbitrary messages of his choice, and his goal is to break semantic security for some other challenge ciphertexts. And as I said, this game models the real world where the attacker is able to fool Alice into encrypting for him messages of his choice, and then the attacker's goal is to somehow break some challenge ciphertext. So I claim that all the ciphers that we've seen up until now, namely deterministic counter mode or the one-time pad, are insecure under a chosen plaintext attack. More generally, suppose we have an encryption scheme that always outputs the same ciphertext for a particular message M. In other words, if I ask the encryption scheme to encrypt the message M once, and then I ask the encryption scheme to encrypt the message M again, if in both cases the encryption scheme outputs the same ciphertext, then that system cannot possibly be secure under a chosen plaintext attack. And both deterministic counter mode and the one-time pad were of that flavor. They always output the same ciphertext given the same message. And so let's see why that cannot be chosen plaintext secure. And the attack is actually fairly simple. What the attacker is going to do is he's going to output the same message twice. This just says that he really wants the encryption of M0. So here the attacker is given C0, which is the encryption of M0. So this was his chosen plaintext query, where he actually received the encryption of the message M0 of his choice. And now he's going to break semantic security. So what he does is he outputs two messages, M0 and M1 of the same length, and he's going to be given the encryption of MB. But lo and behold, we said that the encryption system always outputs the same ciphertext when it's encrypting the message M0. Therefore, if B is equal to 0, we know that C, this challenge ciphertext, is simply equal to C0 because it's the encryption of M0. However, if B is equal to 1, then we know that this challenge ciphertext is the encryption of M1, which is something other than C0. So all the attacker does is he just checks if C is equal to C0, he outputs 0. In other words, he outputs 1. So in this case, the attacker is able to perfectly guess this bit B, so he knows exactly whether he was given the encryption of M0 or the encryption of M1, and as a result, his advantage in winning this game is 1, meaning that the system cannot possibly be CPA secure. 1 is not a negligible number. So this shows that deterministic encryption schemes cannot possibly be CPA secure, but you might wonder, well, what does this mean in practice? Well, in practice, this means again that every message is always encrypted to the same ciphertext. What this means is if you're encrypting files on disk and you happen to be encrypting two files that happen to be the same, they'll result in the same ciphertext, and then the attacker, by looking at the encrypted disk, will learn that these two files actually contain the same content. The attacker might not learn what the content is, but he will learn that those two encrypted files are an encryption of the same content, and he shouldn't be able to learn that. Similarly, if you send two encrypted packets on the network that happen to be the same, the attacker will not learn the content of those packets, but he will learn that those two packets actually contain the same information. Think, for example, of an encrypted voice conversation. Every time there's quiet on the line, the system will be sending encryptions of 0. But since encryptions of 0 are always mapped to the same ciphertext, an attacker looking at the network will be able to identify exactly the points in the conversation where there is quiet, because he will always see those exact same ciphertexts every time. So these are examples where deterministic encryption cannot possibly be secure. And as I say, formally we say that deterministic encryption cannot be semantically secure under a chosen plaintext attack. So what do we do? Well, the lesson here is if the secret key is going to be used to encrypt multiple messages, it had better be the case that given the same plaintext to encrypt twice, the encryption algorithm must produce different ciphertexts. And so there are two ways to do that. The first method is what's called randomized encryption. Here the encryption algorithm itself is going to choose some random string during the encryption process, and it's going to encrypt the message M using that random string. So what this means is that a particular message M0, for example, isn't just going to be mapped to one ciphertext, but it's going to be mapped to a whole ball of ciphertexts, where on every encryption, basically we output 1 point in this ball. So every time we encrypt, the encryption algorithm chooses a random string, and that random string leads to 1 point in this ball. Of course, the decryption algorithm, when it takes any point in this ball, will always map the result to M0. Similarly, the ciphertext M1 will be mapped to a ball, and every time we encrypt M1, we basically output 1 point in this ball, and these balls have to be disjoint so that the encryption algorithm, when it obtains a point in the ball corresponding to M1, will always output the message M1. In this way, since the encryption algorithm uses randomness, if we encrypt the same message twice, with high probability we'll get different ciphertexts. Unfortunately, this means that the ciphertext necessarily has to be longer than the plaintext, because somehow the randomness that was used to generate the ciphertext is now encoded somehow in the ciphertext. So the ciphertext takes more space. And roughly speaking, the ciphertext size is going to be larger than the plaintext by basically the number of random bits that were used during encryption. So if the plaintexts are very big, if the plaintexts are gigabytes long, the number of random bits is going to be on the order of 128, so maybe this extra space doesn't really matter. But if the plaintexts are very short, maybe they themselves are 128 bits, then adding an extra 128 bits to every ciphertext is going to double the total ciphertext size, and that could be quite expensive. So as I say, randomized encryption is a fine solution, but in some cases it actually introduces quite a bit of cost. So let's look at a simple example. So imagine we have a pseudo-random function that takes inputs in a certain space R, which is going to be called a nonce space, and it outputs in the message space. And now let's define the following randomized encryption scheme. When we want to encrypt a message M, what the encryption algorithm is going to do is first it's going to generate a random R in this nonce space R, and then it's going to output a ciphertext that consists of two components. The first component is going to be this value R, and the second component is going to be an evaluation of the pseudo-random function at the point R, XORed with the message M. And my question to you is this encryption system semantically secure under a chosen plaintext attack? So the correct answer is yes, but only if the nonce space R is large enough so that little r never repeats with very, very high probability. And let's quickly argue why that's true. So first of all, because f is a secure pseudo-random function, we might as well replace it with a truly random function. In other words, this is indistinguishable from the case where we encrypt the message M using a truly random function little f evaluated at the point R and then XORed with M. But since this little r never repeats, every ciphertext uses a different little r, what this means is that the values of f of r are random, uniform, independent strings every time. So every time we encrypt a message, we encrypt it essentially using a new uniform random one-time pad. And since XORing a uniform string with any string simply generates a new uniform string, the resulting ciphertext is distributed as simply two random uniform strings. I'll call them R and R prime. And so both in experiment 0 and in experiment 1, all the attacker gets to see are truly uniform random strings R, R prime. And since in both experiments the attacker is seeing the same distribution, he cannot distinguish the two distributions. And so since security holds completely when we're using a truly random function, it's also going to hold when we're using a pseudo-random function. Okay, so this is a nice example of how we use the fact that a pseudo-random function behaves like a random function to argue security of this particular encryption scheme. Okay, so now we have a nice example of randomized encryption. The other approach to building chosen plaintext secure encryption schemes is what's called nonce-based encryption. Now, in a nonce-based encryption system, the encryption algorithm actually takes 3 inputs rather than 2. As usual, it takes the key and the message, but it also takes an additional input called a nonce. And similarly, the decryption algorithm also takes the nonce as input and then produces the resulting decrypted plaintext. So what is this nonce value n? This nonce is a public value. It does not need to be hidden from the adversary, but the only requirement is that the pair key, nonce is only used to encrypt a single message. In other words, this pair k, n must change from message to message. Then there are 2 ways to change it. One way to change it is by choosing a new random key for every message, and the other way is to keep using the same key all the time, but then we must choose a new nonce for every message. And as I said, I want to emphasize again, this nonce need not be secret and it need not be random. The only requirement is the nonce is unique. And in fact, we're going to use this term throughout the course. A nonce for us means a unique value that doesn't repeat. It does not have to be random. So let's look at some examples of choosing a nonce. Well, the simplest option is simply to make the nonce be a counter. So for example, in networking protocol, you can imagine the nonce being a packet counter that's incremented every time a packet is sent by the sender or received by the receiver. This means that the encryptor has to keep state from message to message, namely it has to keep this counter around and increment it after every message is transmitted. Interestingly, if the decryptor actually has the same state, then there's no need to include the nonce in the ciphertext since the nonce is implicit. Let's look at an example. The HTTPS protocol is run over a reliable transport mechanism, which means that packets sent by the sender are assumed to be received in order at the recipient. So if the sender sends packet 5 and then packet 6, the recipient will receive packet number 5 and then packet number 6 in that order. This means that if the sender maintains a packet counter, the recipient can also maintain a packet counter, and the two counters basically increment in sync. In this case, there's no reason to include the nonce in the packets because the nonce is implicit between the two sides. However, in other protocols, for example in IPsec, IPsec is a protocol designed to encrypt the IP layer. The IP layer does not guarantee in-order delivery, and so the sender might send packet number 5 and then packet number 6, but those will be received in reverse order at the recipient. In this case, it's still fine to use a packet counter as a nonce, but now the nonce has to be included in the packet so that the recipient knows which nonce to use to decrypt the received packet. So as I say, nonce-based encryption is a very efficient way to achieve CPA security, and in particular if the nonce is implicit, it doesn't even increase the ciphertext length. Of course, another method to generate a unique nonce is simply to pick the nonce at random, assuming the nonce space is sufficiently large so that with high probability the nonces will never repeat for the life of the key. Now in this case, nonce-based encryption simply reduces to randomized encryption. However, the benefit here is that the sender does not need to maintain any state from message to message. So this is very useful, for example, if encryption happens to take place on multiple devices. For example, I might have both a laptop and a smartphone. They might both use the same key, but in this case, if I required stateful encryption, then my laptop and the smartphone would have to coordinate to make sure that they never reuse the same nonce. Whereas if both of them simply pick nonces at random, they don't need to coordinate because with very high probability, they'll simply never choose the same nonce. Again, assuming the nonce space is big enough. So there are some cases where stateless encryption is quite important, in particular where the same key is used by multiple machines. So I want to define more precisely what security means for nonce-based encryption, and in particular I want to emphasize that the system must remain secure when the nonces are chosen by the adversary. The reason it's important to allow the adversary to choose the nonces is because the adversary can choose which ciphertext it wants to attack. So imagine the nonce happens to be a counter, and it so happens that when the counter hits the value 15, maybe at that point it's easy for the adversary to break semantic security. So the adversary will wait until the 15th packet is sent, and only then he will ask to break semantic security. So when we talk about nonce-based encryption, we generally allow the adversary to choose the nonce, and the system should remain secure even under those settings. So let's define the CPA game in this case. And it's actually very similar to the game before. Basically, the attacker gets to submit pairs of messages, MI0 and MI1. Obviously, they both have to be of the same length. And he gets to supply the nonce. And in response, the adversary is given the encryption of either MI0 or MI1, but using the nonce that the adversary chose. And of course, as usual, the adversary's goal is to tell whether he was given the encryption of the left plaintext or the right plaintext. And as before, the adversary gets to iterate these queries, and he can issue as many queries as he wants. We usually let Q denote the number of queries that the adversary issues. Now, the only restriction, of course, which is crucial, is that although the adversary gets to choose the nonces, he's restricted to choosing distinct nonces. The reason we force him to choose distinct nonces is because that's the requirement in practice. Even if the adversary fools Alice into encrypting multiple messages for him, Alice will never use the same nonce again, As a result, the adversary will never see messages encrypted using the same nonce, and therefore, even in the game, we require that all the nonces be distinct. And then, as usual, we say that the system is a nonce-based encryption system that's semantically secure under a chosen plaintext attack if the adversary cannot distinguish experiment 0, where he's given encryptions of the left messages, from experiment 1, where he's given encryption of the right messages. So let's look at an example of a nonce-based encryption system. As before, we have a secure PRF that takes inputs in the nonce space R and outputs strings in the message space M. Now, when a new key is chosen, we're going to reset our counter R to be 0. And now when we encrypt a particular message M, what we'll do is we'll increment our counter R and then encrypt the message M using the pseudorandom function applied to this value R. And as before, the ciphertext is going to contain two components, the current value of the counter and then the one-time pad encryption of the message M. And so my question to you is whether this is a secure, nonce-based encryption system. So the answer, as before, is yes, but only if the nonce space is large enough, so as we increment the counter R, it will never cycle back to 0, so that the nonces will always be unique. We argue security the same way as before. Because the PRF is secure, we know that this encryption system is indistinguishable from using a truly random function. In other words, if we apply a truly random function to the counter and XOR the results with the plaintext M. But now, since the nonce R never repeats, every time we compute this f of r, we get a truly random, uniform, and independent string, so that we're actually encrypting every message using the one-time pad. And as a result, all the adversary gets to see in both experiments are basically just a pair of random strings. So both in experiment 0 and in experiment 1, the adversary gets to see exactly the same distribution, namely the responses to all his chosen plaintext queries are just pairs of strings that are just uniformly distributed. And this is basically the same in experiment 0 and experiment 1, and therefore the attacker cannot distinguish the two experiments. And since he cannot win the semantic security game with a truly random function, he also cannot win the semantic security game with the secure PRF. And therefore, the scheme is secure. So now we understand what it means for a symmetric system to be secure when the key is used to encrypt multiple messages. The requirement is that it be secure under a chosen plaintext attack. And we said that basically the only way to be secure under a chosen plaintext attack is either to use randomized encryption or to use nonce-based encryption where the nonce never repeats. And then in the next two segments, we're going to build two classic encryption systems that are secure when the key is used multiple times. Now that we understand chosen plaintext security, let's build encryption schemes that are chosen plaintext secure. And the first such encryption scheme is going to be called cipher block chaining. So here's how cipher block chaining works. Cipher block chaining is a way of using a block cipher to get chosen plaintext security. In particular, we're going to look at a mode called cipher block chaining with a random IV. CBC stands for cipher block chaining. So suppose we have a block cipher, so ED is a block cipher, and let's define ECBC to be the following encryption scheme. So the encryption algorithm, when it's asked to encrypt the message M, the first thing it's going to do is it's going to choose a random IV that's exactly one block of the block cipher. So IV is one cipher block. So in the case of AES, the IV would be 16 bytes. And then we're going to run through the algorithm here. The IV basically that we chose is going to be XORed into the first plaintext block, and then the result is going to be encrypted using the block cipher, and output is the first block of the ciphertext. And now comes the chaining part, where we actually use the first block of the ciphertext to kind of mask the second block of the plaintext. So we XOR the two together, and the encryption of that becomes the second ciphertext block. And so on and so on and so forth. So this is cipher block chaining. You can see that each cipher block is chained and XORed into the next plaintext block. And the final ciphertext is going to be essentially the IV, the initial IV that we chose, along with all the ciphertext blocks. I should say that IV stands for initialization vector. And we're going to be seeing that term used quite a bit every time we need to pick something at random at the beginning of the encryption scheme. Typically, we'll call that an IV for initialization vector. So you notice that the ciphertext is a little bit longer than the plaintext because we had to include this IV in the ciphertext, which basically captures the randomness that was used during encryption. So the first question is, how do we decrypt the result of CBC encryption? And so let me remind you again that if when we encrypt the first message block, we XOR it with the IV, encrypt the result, and that becomes the first ciphertext block. So let me ask you, how would you decrypt that? So given the first ciphertext block, how would you recover the original first plaintext block? So decryption is actually very similar to encryption. Here I wrote down the decryption circuit. You can see basically it's almost the same thing, except the XOR is on the bottom instead of on the top. And again, you realize that essentially we chopped off the IV as part of the decryption process, and we only output the original message back. The IV is dropped by the decryption algorithm. Okay, so the following theorem is going to show that in fact CBC mode encryption with a random IV is in fact semantically secure under a chosen plaintext attack. And so let's state that more precisely. Basically, if we start with a PRP, in other words a pure block cipher E, that's defined over a space X, then we're going to end up with an encryption algorithm ECBC that takes messages of length L and outputs ciphertext of length L plus 1. And then suppose we have an adversary that makes Q chosen plaintext queries. Then we can state the following security fact, that for every such adversary that's attacking ECBC, there exists an adversary that's attacking the PRP, the block cipher, with the following relation between the two algorithms. In other words, the advantage of algorithm A against the encryption scheme is less than the advantage of algorithm B against the original PRP, plus some noise term. So let me interpret this theorem for you as usual. So what this means is that essentially, since E is a secure PRP, this quantity here is negligible. And our goal is to say that adversary's A's advantage is also negligible. However, here we're prevented from saying that because we got this extra error term. This is often called an error term. And to argue that CBC is secure, we have to make sure the error term is also negligible. Because if both of these terms on the right are negligible, their sum is negligible, and therefore the advantage of A against ECBC would also be negligible. So this says that in fact, for ECBC to be secure, it had better be the case that Q squared L squared is much, much, much smaller than the value X. So let me remind you what Q and L are. So L is simply the length of the messages that we're encrypting. Okay, so L could be like, say, 1,000, which would mean that we're encrypting messages that are at most 1,000 AES blocks. Q is the number of ciphertexts that the adversary gets to see under the CPA attack. But in real life, what Q is basically the number of times that we've used the key K to encrypt messages. In other words, if we use a particular AES key to encrypt 100 messages, Q would be 100. It's because the adversary would then see at most 100 messages encrypted under this key K. Okay, so let's see what this means in the real world. So here I rewrote the error bounds from the theorem. And just to remind you, Q is the number of messages encrypted with K, and L is the length of the messages. And so suppose we want the adversary's advantage to be less than 1 over 2 to the 32. This means that the error term had better be less than 1 over 2 to the 32. Okay, so let's look at AES and see what this means. For AES of course uses 128-bit blocks. So X is going to be 2 to the 128. The size of X is 2 to the 128. And if you plug this into the expression, you see that basically the product Q times L had better be less than 2 to the 48. This means that after we use a particular key to encrypt 2 to the 48 AES block, we have to change the key. Okay, essentially CBC stops being secure after the key is used to encrypt 2 to the 48 different AES blocks. So it's kind of nice that the security theorem tells you exactly how long the key can be used and then how frequently essentially you have to replace the key. Now interestingly, if you apply the same analysis to DES, DES actually has a much shorter block, namely only 64 bits. You see the key has to be changed much more frequently, namely after every 65,000 DES blocks, essentially you need to generate a new key. So this is one of the reasons why AES has a larger block size, so that in fact modes like CBC would be more secure and one can use the key for a longer period of time before having to replace it. What this means is after you encrypt 2 to the 16 blocks, each block of course is 8 bytes, so after you encrypt about half a megabyte of data, you would have to change the DES key, which is actually quite low. And you notice with AES you can encrypt quite a bit more data before you have to change the key. So I want to warn you about a very common mistake that people have made when using CBC with a random IV. And that is that the minute that the attacker can predict the IV that you're going to be using for encrypting a particular message, the cipher, this ECBC, is no longer CPA secure. So when using CBC with a random IV like we just shown, it's crucial that the IV is not predictable. But let's see an attack. So suppose it so happens that given the encryption of a particular message, the attacker can actually predict the IV that will be used for the next message. Well, let's show that in fact the resulting system is not CPA secure. So the first thing the adversary is going to do is he's going to ask for the encryption of a one block message. And in particular, that one block is going to be 0. So what the adversary gets back is the encryption of one block, which namely is the encryption of the message, namely 0, XOR the IV. Okay, and of course the adversary also gets the IV. Okay, so now the adversary by assumption can predict the IV that's going to be used for the next encryption. Okay, so let's say that IV is called, well, IV. So next the adversary is going to issue his semantic security challenge, and the message M0 is going to be the predicted IV XOR IV1, which was used in the encryption of C1. And then the message M1 is just going to be some other message. It doesn't really matter what it is. So now let's see what happens when the adversary receives the resulting semantic security challenge. Well, he's going to get the encryption of M0 or the encryption of M1. So when the adversary receives the encryption of M0, tell me what is the actual plaintext that's encrypted in the ciphertext C? Well, so the answer is that what's actually encrypted is the message, which is IV XOR IV1, XOR the IV that's used to encrypt that message, which happens to be IV, and this of course is IV1. So when the adversary receives the encryption of M0, he's actually receiving the block cipher encryption of IV1. And lo and behold, you notice that he already has that value from his chosen plaintext query. And then when he's receiving the encryption of the message M1, he just receives a normal CBC encryption of the message M1. So you realize that now he has a simple way of breaking the scheme. Namely, what he'll do is he'll say, he's going to ask, is the second block of the ciphertext C equal to the value that I received in my CPA query? If so, I'll say that I received the encryption of M0. Otherwise, I'll say that I received the encryption of M1. So really, his test is C1, he refers to the second block of C, and C11 refers to the second block of C1. If the two are equal, he says 0, and otherwise he says 1. So the advantage of this adversary is going to be 1, and as a result, he completely breaks CPA security of this CBC encryption. So the lesson here is, if the IV is predictable, then in fact there is no CPA security. And unfortunately, this is actually a very common mistake in practice. In particular, even in SSL protocol in TLS 1.1, it turns out that the IV for record number I is in fact the last ciphertext block of record number I-1. That means that exactly given the encryption of record number I-1, the adversary knows exactly what IV is going to be used for record number I. Very recently, just last summer, this was actually converted into a pretty devastating attack on SSL. We'll describe that attack when we talk about SSL in more detail, but for now I wanted to make sure you understand that when you use CBC encryption, it's absolutely crucial that the IV be random. Okay, so now I'm going to show you the nonce-based version of CBC encryption. So in this mode, the IV is replaced by a non-random but unique nonce. For example, the numbers 1, 2, 3, 4, 5 could all be used as a nonce. And now the appeal of this mode is that if the recipient actually knows what the nonce is supposed to be, then there's no reason to include the nonce in the ciphertext. In which case, the ciphertext is exactly the same length as the plaintext. Unlike CBC with a random IV, where we had to expand the ciphertext to include the IV, here, if the nonce is already known to the recipient, there's no reason to include it in the ciphertext, and the ciphertext is exactly the same length as the plaintext. So it's perfectly fine to use a non-random but unique nonce. However, it's absolutely crucial to know that if you do this, there's one more step that you have to do before you use the nonce in the CBC chain. In particular, in this mode now we're going to be using two independent keys, K and K1. The key K is, as before, going to be used to encrypt the individual message blocks. However, this key K1 is going to be used to encrypt the non-random but unique nonce, so that the output is going to be a random IV, which is then used in the CBC chain. So this extra step here of encrypting the nonce with the key K1 is absolutely crucial. Without it, CBC mode encryption would not be secure. In particular, if you just directly use the nonce, feed that into CBC encryption, in other words, you use the nonce as the IV, then we already know that a non-random nonce would not be CPA secure. We saw that on the previous slide. But in fact, even if you set K to be equal to K1, in other words, you just encrypt the nonce using the key K, that also, well, is not going to be CPA secure and can lead to significant attacks. So I want to make sure you understand that if the nonce in CBC mode encryption is not random, this extra encryption step has to take place. And so I'll make this extra step kind of dance here just to make sure you never forget to put it in. And I'll tell you that this is an extremely common mistake in practice. There are many real-world products and crypto libraries that actually forget to encrypt the non-random nonce before using it in the CBC chain, and that actually leads to practical and significant attacks. For example, this was not done in TLS. TLS, as we said, used predictable IVs, and that led to a significant attack on TLS. Moreover, the reason this is so important to know is that in fact many crypto APIs are set up to almost deliberately mislead the user into using CBC incorrectly. So let's look at how CBC is implemented inside of OpenSSL. So here are the arguments to the function. Basically, this is the plaintext. This is the place where the ciphertext will get written to. This is the length of the plaintext. This is the AES key. Finally, there's an argument here that says whether you're encrypting or decrypting. And the most important parameter that I wanted to point out here is the actual IV. And unfortunately, the user is asked to supply this IV, and the function uses the IV directly in the CBC encryption mechanism. It doesn't encrypt the IV before using it. And as a result, if you ever call this function using a non-random IV, the resulting encryption system won't be CPA secure. Okay, so it's very important to know that when calling functions like this CBC encryption in OpenSSL, either supply a truly random IV, or if you want the IV to be a counter, then you have to encrypt the counter using AES before you actually call CBC encrypt. And you have to do that yourself. So again, it's very important that the programmer knows that it needs to be done, otherwise the CBC encryption is insecure. One last technicality about CBC is what to do when the message is not a multiple of the block cipher block length. That is, what do we do if the last message block is shorter than the block length of AES, for example? So the last message block is less than 16 bytes. And the answer is that we add a pad to the last block so that it becomes as long as 16 bytes, as long as the AES block size. And this pad, of course, is going to be removed during encryption. So here's a typical pad. This is the pad that's used in TLS. Basically, if you pad with n bytes, then essentially what you do is you write the number n times. So for example, if you pad with 5 bytes, you pad with the string 55555. So 5 bytes where each byte is the value 5. And the cute thing about this pad is basically when the decryptor receives the message, what he does is he looks at the last byte of the last block. So suppose that value is 5, then he simply removes the last 5 bytes of the message. Now the question is, what do we do if in fact the message is a multiple of 16 bytes, so in fact no pad is needed? If we don't pad at all, then that's a problem, because the decryptor is going to look at the very last byte of the last block, which is now part of the actual message, and he's going to remove that many bytes from the plaintext. So that actually would be a problem. So the solution is, if in fact there is no pad that's needed, nevertheless we still have to add a dummy block. And since we add this dummy block, this would be a block that basically contains 16 bytes, each one containing the number 16. Okay, so we add essentially 16 dummy blocks. The decryptor, that when he's decrypting, he looks at the last byte of the last block. He sees that the value is 16, therefore he removes the entire block, and whatever's left is the actual plaintext. So it's a bit unfortunate that in fact, if you're encrypting short messages with CBC, and the messages happen to be, say, 32 bytes, so they are a multiple of 16 bytes, then you have to add one more block and make all these ciphertexts be 48 bytes, just to accommodate the CBC padding. I should mention that there's a variant of CBC called CBC with ciphertext stealing that actually avoids this problem, but I'm not going to describe that here. If you're interested, you can look that up online. Okay, so that's the end of our discussion of CBC, and in the next segment we'll see how to use counter mode to encrypt multiple messages using a single key. In this segment, we're going to look at another method to achieve chosen plaintext security that's actually superior to CBC. And this method is called randomized counter mode. Unlike CBC, randomized counter mode uses a secure PRF. It doesn't need a block cipher. It's enough for counter mode to just use a PRF, because we're never going to be inverting this function f. So we're going to let f be the secure PRF, and it acts on n-bit blocks. Again, if we use AES, n would be 128. And the way the encryption algorithm works in counter mode is it starts off by choosing a random IV. It's a 128-bit random IV in the case of AES. And then essentially we start counting from this random IV. So you notice the first encryption is of IV, then of IV plus 1, up to IV plus L. So we generate this random pad, We XOR the result with the message, and that gives us the ciphertext. And as usual, you notice that the IV here is included along with the ciphertext, so that in fact the ciphertext is a little longer than the original plaintext. And the point, of course, is that the encryption algorithm chooses a new IV for every message, and so even if I encrypt the same message twice, I'm going to get different resulting ciphertexts. One thing to note is that this mode is completely parallelizable, unlike CBC. CBC was sequential. In other words, you couldn't encrypt block number 5 until you've encrypted blocks number 1 to 4. So hardware companies who might have multiple AES engines working in parallel cannot actually use those AES engines when using CBC, because CBC is inherently sequential. So even though you might have 2 or 3 or 4 AES engines, you can only use one of them when doing CBC encryption. With counter mode, everything is completely parallelizable. If you have 3 AES engines, encryption basically will work 3 times as fast. So that's the beauty of counter mode. And counter mode also has a corresponding nonce-based counter mode, where the IV is not truly random, but rather is just a nonce, which could be a counter. And the way you would implement nonce-based counter mode is you would take the 128 bits block that's used in AES, and then you would split it in two. You would use the left 64 bits as the nonce, so the counter, say, would count from 0 to 2 to the 64, and then that will be the nonce part of it. And then once you specify the nonce, the lower order 64 bits would be doing the counting inside of the counter mode encryption. Okay, so nonce goes on the left, and the counter mode encryption counter goes on the right. And it's perfectly fine if this nonce is unpredictable. The only restriction is that you encrypt at most 2 to the 64 blocks using one particular nonce. The danger is that you don't want this counter to reset to 0, so that then you will have 2 blocks, say this guy and this guy, that are encrypted using the same one-time pad, namely this one and this one. So let's quickly state the security theorem for randomized counter mode. By now you should be used to these kind of theorems. Basically, we are given a secure PRF. What we end up with is an encryption scheme. We'll call it E sub CTR, E sub counter mode, which is semantically secure under a chosen plaintext attack. It encrypts messages that are L blocks long and produces ciphertexts that are L plus 1 blocks long, because the IV has to be included in the ciphertext. This is for randomized counter mode. And then the error bounds are stated over here. It's basically the same bounds as in the case of CBC encryption. As usual, we argue that this term is negligible because the PRF is secure, and we would like to deduce from that that this term is negligible so that ECTR is secure. Unfortunately, we have this error term here, and so we have to make sure this error term is negligible, and for that we have to make sure that Q squared L is less than the size of the block. We remember Q is the number of messages encrypted under a particular key, and L is the maximum length of those messages. Now, interestingly, in the case of CBC, we had Q squared L squared had to be less than X, which is actually worse than we have for counter modes. In other words, counter modes can actually be used for more blocks than CBC could. And let's see a quick example of that. So here's again the error term for counter mode. Remember, Q is again the number of messages encrypted with the key, and L is the length of those messages. And as before, just as in the case of CBC, suppose we want the adversary's advantage to be at most 1 or 2 to the 32. That basically requires that this Q squared L over X be less than 1 over 2 to the 32. And so for AES, what happens is if you plug in the values, X is 2 to the 128, 128-bit blocks. So Q times square root of L should be less than 2 to the 48. This is basically the bound you get from plugging in 2 to the 128 into this bound here. And as a result, you can see if you're encrypting messages that are each 2 to the 32 blocks, then after 2 to the 32 such messages, you have to replace your secret key. Otherwise, randomized counter mode is no longer CPA secure. So this means we could encrypt a total of 2 to the 64 AES blocks using a single secret key. Remember, for CBC, corresponding value was 2 to the 48 blocks. So in fact, because counter mode has a better security parameterization, in fact, we can use the same key to encrypt more blocks with counter mode than we could with CBC. So I wanted to do a quick comparison of counter mode and CBC and argue that in every single aspect, counter mode is superior to CBC, and that's actually why most modern encryption schemes actually are starting to migrate to counter mode and abandon CBC, even though CBC is still quite widely used. So let's look at the comparison. First of all, recall that CBC actually had to use a block cipher, because if you look at the decryption circuit, the decryption circuit actually ran the block cipher in reverse. It was actually using the decryption capabilities of the block cipher. Whereas counter mode, we only need a PRF. We never ever use the decryption capabilities of the block cipher. We only use it in the forward direction, only encrypt with it. Because of this, counter mode is actually more general, and it can use primitives like salsa, for example. Salsa 20, if you remember, is a PRF, but is not a PRP. So counter mode can use salsa, but CBC cannot. And in that sense, counter mode is more general than CBC. Counter mode, as we said, is actually parallel, whereas CBC is a very sequential process. We said that counter mode is more secure. The security bounds, the error terms are better for counter modes than they are for CBC, and as a result, you can use a key to encrypt more blocks in counter mode than you could with CBC. The other issue is, remember in CBC we talked about the dummy padding block. If you have a message that's a multiple of the block length, in CBC we said that we had to add a dummy block, whereas in counter mode this wasn't necessary. Although I did want to mention that there is a variation of CBC called CBC with ciphertext stealing that actually avoids the dummy block issue. So for standardized CBC, we actually need a dummy block, but in fact there is a modification to CBC that doesn't need a dummy block, just like counter mode. Finally, suppose you're encrypting just a stream of 1-byte messages and using nonce-based encryption with an implicit nonce. So the nonce is not included in the ciphertext. In this case, every single 1-byte message would have to be expanded into a 16-byte block and then encrypted, and the result would be a 16-byte block. So if you have like a stream of 100 1-byte messages, each one separately would have to become a 16-byte block, and you'll end up with a stream of 100 16-byte ciphertexts. So you get a 16x expansion on the length of the ciphertext compared to the length of the plaintext. In counter mode, of course, this is not a problem. You would just encrypt each 1-byte message by XORing it with the first byte of the stream that's generated in counter mode. So every ciphertext would just be 1 byte, just like the corresponding plaintext. And so no expansion at all using counter mode. So you see that essentially in every single aspect, counter mode dominates CBC, and that's why it's actually the recommended mode to be using today. Okay, so this concludes our discussion of chosen plaintext security. I wanted to just quickly summarize and remind you that we're going to be using these PRP and PRF abstractions of block ciphers throughout. This is actually the correct way of thinking of block ciphers, and so we'll always think of them as either pseudo-random permutations or pseudo-random functions. And then I wanted to remind you again that so far we saw two notions of security. Both only provide security against eavesdropping. They don't provide security against tampering with the ciphertext. One was used when the key is only used to encrypt a single message. The other one was used when the key was used to encrypt multiple messages. And as we said, because neither one is designed to defend against tampering, neither one provides data integrity. And we're going to see that this is a real problem. And as a result, in fact, I'm going to say in the next segment that these modes actually should never ever be used. You should only be using these modes in addition to an integrity mechanism, which is our next topic. Okay, so far we've seen basically if you're using the key once, you can use stream ciphers or you can use deterministic counter mode. If you're going to use the key many times, you could use randomized CBC or randomized counter mode. And we're going to talk about how to provide integrity and confidentiality once we cover the topic of integrity, which is our next module. In this module, we're going to stop talking about encryption and instead discuss message integrity. Next, we will come back to encryption and show how to provide both encryption and integrity. So as I said, our goal here is to provide integrity without any confidentiality. And there are, in fact, many cases in the real world where this comes up. For example, you can think of operating system files on your disk. Say if you're using Windows, all the Windows operating system files on disk are not confidential. They're public and known to the world, but it is quite important to make sure that they're not modified by a virus or some malware. That's an example where you want to provide integrity, but you don't care about confidentiality. Another example is banner ads on web pages. The provider of the ads doesn't care at all if someone copies them and shows them to other people, so there's no confidentiality issue at all, but they do care about modifying those ads. So for example, they do want to prevent people from changing the ads into different types of ads. So that's another example where integrity matters, but confidentiality is not important at all. So how do we provide message integrity? The basic mechanism is what's called a MAC, a Message Authentication Code, MAC. And the way we do it is as follows. So here we have our friends Alice and Bob. They have a shared key K, which is not known to the attacker, but known to both of them. And there's a public message M that Alice wants to send to Bob, such that an attacker along the way cannot modify this message on its way to Bob. The way Alice does it is by using what's called a MAC signing algorithm, well denoted by S, where the MAC signing algorithm takes as input the key and the message and produces a very short tag. The tag could be like 90 bits or 100 bits or so on. Even though the message is gigabytes long, the tag is actually very, very short. And then she appends the tag to the message and sends the combination of the two to Bob. Bob receives the message and the tag, and then he runs what's called the MAC verification algorithm on this tag. So the MAC verification algorithm takes as input the key, the message, and the tag, and it says basically yes or no, depending on whether the message is valid or whether it's been tampered with. Okay, so more precisely, what is a MAC? Well, we said the MAC basically consists of two algorithms, a signing algorithm and a verification algorithm. As usual, they're defined over a key space, a message space, and a tag space. And as we said, it's a pair of algorithms. So the signing algorithm will output a tag in the tag space, and the verification algorithm, basically given the key, the message, and the tag, will output yes or no. And I want to remind you, as usual, there are these consistency requirements such that for every k in the key space and for every message in the message space, it so happens that if I sign the message using a particular key and then I verify the tag using the same key, I should get yes in response. So this is the standard consistency requirement, which is the analog of the one that we saw for encryption. Now, one thing I'd like to point out is that integrity really does require a shared key between Alice and Bob. And in fact, there's a common mistake that people make where they try to provide integrity without actually a shared key. So here's an example. So consider CRC. CRC stands for cyclic redundancy check. This is a classic checksum algorithm that's designed to detect random errors in messages. So imagine instead of using a key to generate the tag, Alice basically uses a CRC algorithm, which is keyless, doesn't take any key to generate a tag, and then she appends this tag to the message. She sends it over to Bob. Bob will basically verify that the CRC is still correct. In other words, Bob will still verify the tag is equal to CRCM, and if so, the verification algorithm would say yes, and otherwise the verification algorithm will say no. So the problem with this is very easy for an attacker to defeat. In other words, an attacker can very easily modify the message and route and fool Bob into thinking that the new message is a valid one. The way the attacker will do it is he'll cancel the message and the tag, he'll simply block them, and then he'll produce his own message M prime and compute his own CRC on this message M prime, and then send the concatenation of the two over to Bob. Bob will run the verification algorithm. Verification will work properly because in fact the right hand side is in fact a valid CRC for the left hand side, and as a result Bob would think that this message came from Alice, but in fact has been completely modified by the attacker and has nothing to do with the original message that Alice sent. Okay, so the problem is because CRC doesn't have a key, there's no difference between Alice and the attacker, and as a result Bob doesn't know where the message came from. Once we introduce a key, now Alice can do something that the attacker can't do, and as a result she might be able to compute a tag that the attacker can't modify. So the point to remember is that CRC, as we said, is designed to detect random errors, not malicious errors. And here our goal is to make sure that even a malicious attacker cannot modify messages en route. So next we want to define what it means for a MAC system to be secure. So as usual, we define security in terms of the attacker's power, what can the attacker do, and the attacker's goal, what is he trying to do. So in the case of MACs, the attacker's power is what's called a chosen message attack. In other words, the attacker can give Alice arbitrary messages of his choice, M1 to MQ, and Alice will compute the tag for him on those messages and give him those tags. So again, you might wonder, why would Alice ever do that? Why would Alice ever compute the tag on a message that the attacker gave her? So just like in the case of chosen plaintext attack, it's very common in the real world that the attacker can give Alice a message, Alice will compute the tag on that message, and then the attacker will obtain the resulting tag. For example, the attacker might send Alice an email. Alice might want to save the email to disk in a way that will prevent someone from tampering with the disk, so she'll compute a tag on the message and save the message and the tag to disk. Later on, the attacker might steal Alice's disk, and now he's recovered Alice's tag on the message that he sent to Alice. So this is an example of a chosen message attack in the real world where the attacker actually obtained a tag on a message that he gave Alice. Okay, so that's what the attacker can do, basically this chosen message attack. And what is his goal? Well, his goal is to do something called an existential forgery. In other words, what he's trying to do is to produce some new valid message tag pair. Okay, so some message tag pair that's different from one of the pairs that were given to him during the chosen message attack. And if he can do that, then we say that the system is insecure, and if he can't, then we'll say the system is secure. So I want to emphasize that existential forgery means that the attacker cannot produce a new message tag pair, even for a message that's completely gibberish. And again, you might wonder, well, why do we care if the attacker computes a tag on a message that's gibberish? That's not of any value to the attacker. But we want to build Macs that are secure under any usage settings. And there are in fact cases where, for example, you might want to compute an integrity tag on a random secret key. In which case, even if the attacker is able to compute a tag on a completely random message, he might be able to fool a user into using the wrong secret key. And as a result, we want to make sure that if the Mac is secure, the attacker can't produce a valid tag for any message, whether it's gibberish or sensical. Another property that's implied by the security definition is if the attacker is given some message tag pair, he shouldn't be able to produce a new tag for the same message. In other words, even though there might be another tag T prime for the same message M, the attacker given M and T shouldn't be able to find this new T prime. And again, you might wonder, well, why do we care? If the attacker already has a tag on the message M, why does it matter if he can produce another tag for the message M? He already has one tag. But as we'll see, there are actually applications where it's really important that the attacker not be able to produce a new tag for a previously signed message. In particular, this will come up when we combine encryption and integrity. So that we're going to demand that given one tag in the message, it's impossible to find another tag for the same message. Okay, so now that we understand the intuition of what we're trying to achieve, let's define it as usual using a more precise game. So here we have two algorithms, S and V, and we have an adversary A, and the game proceeds as follows. The challenger, as usual, just chooses a random key for the Mac, and then the adversary basically does his chosen message attack. So he submits an M1 to the challenger and receives the tag on that message M1. Then he submits an M2 to the challenger and receives the tag on that M2, and so on and so forth until he submits Q messages to the adversary and receives Q tags on all those messages. So that's the chosen message attack part. And then the adversary goes ahead and tries to do an existential forgery, namely he outputs a message tag pair, a new message tag pair, and we say that he wins the game. In other words, B is equal to 1 means that he wins the game if, first of all, the message tag pair that he outputs is a valid message tag pair, so the verification algorithm says yes, and second of all, it's a fresh message tag pair. In other words, it's not one of the message tag pairs that we gave him before. In other words, we say that the attacker lost the game, namely B is equal to 0. And as usual, we define the advantage of an adversary as the probability that the challenger outputs 1 in this game, and we say that a Mac system is secure if for all efficient adversaries the advantage is negligible. Okay, in other words, no efficient adversary can win this game with non-negligible probability. Alright, that's our definition of secure Macs, and our goal is to build a secure Macs like this. Before we do that, I want to ask you two questions. So the first question is, suppose we have a Mac, and it so happens that the attacker can find two messages, M0 and M1, that happen to have the same tag for about half of the keys. In other words, if you choose a key at random with probability 1/2, the tag on the message M0 will be the same on the tag on the message M1. And my question to you is, can this be a secure Mac? So I want to emphasize the attacker doesn't know what the tag on M0 and M1 is. All he knows is that the two messages happen to have the same tag with probability 1/2. So the question is whether this is a secure Mac. So the answer is no, this is not a secure Mac, and the reason is because of the chosen message attack. Essentially, the attacker can ask for the tag on the message M0, and then he'll receive M0, T from the challenger, and in fact T would be a valid tag for the message M0, and then what he would output as his existential forgery is M1, T. And you notice M1, T is different from M0, T, so this is a valid existential forgery. And as a result, the attacker wins the game with advantage 1/2. So we conclude that this Mac is not secure. The second question I'd like to ask you is, suppose we have a Mac that happens to always output a 5-bit tag. In other words, the tag space for this Mac happens to be 0, 1 to the 5. So for every key and for every message, the signing algorithm will just output a 5-bit tag. And the question is, can this Mac be secure? course, the answer is no, because the attacker can simply guess the tag. So what he would do is he wouldn't ask any chosen message attacks. All he would do is he would output an existential forgery as follows. He would just choose a random tag, so choose a random tag T at random in 0, 1 to the 5, and then he would just output his existential forgery as, say, the message 0 and the tag T. And now with probability 1 over 2 to the 5, this tag will be a valid tag for the message 0, and so the adversary's advantage is 1 over 32, which is non-negligible. So this basically says that tags can't be too short. They have to have some length to them. And in fact, a typical tag length would be, say, 64 bits, or 96 bits, or 128 bits. TLS, for example, uses tags that are 96 bits long. If you try to guess the tag for a message when the tag is 96 bits, the probability of guessing it correctly is 1 over 2 to the 96, so the adversary's advantage would just be 1 over 2 to the 96, which is negligible. So now that we understand what MACs are, I want to show you a simple application. In particular, let's see how MACs can be used to protect system files on disk. So imagine that when you install an operating system, say when you install Windows on your machine, one of the things that Windows does is it asks the user for a password and then derives a key K from this password, and then for every file that it writes to disk, in this case the files would be F1, F2 up to Fn, what the operating system would do is it would compute a tag for that file and then store the tag along with the file. So here it concatenates the tag to each one of the files. And then it erases the key K, so it no longer stores the key K on disk or in memory or anywhere. Okay, so now later imagine that the machine gets infected with a virus, and the virus tries to modify some of the system files. The question is whether the user can detect which files were modified. So here's one way to do it. Basically, the user would reboot the machine into some clean OS, say you reboot from a USB disk or something, and then once the machine boots from this clean OS, the user would supply his password to this clean running operating system, and then this new clean running operating system would go ahead and check the Mac for each one of the system files. Now the fact that the Mac is secure means that the poor virus couldn't actually create a new file, let's call it F prime, with a valid tag. So it couldn't actually create an F prime T prime, because if it could, then that would be an existential forgery on this Mac. And because, well, the Mac is existentially unforgeable, the virus couldn't create any F prime, no matter what the F prime is. And consequently, because of the security of the Mac, the user will detect all the files that were modified by the virus. Now there's one caveat to that. One thing that the virus can do is actually swap two files. So for example, he can swap this file F1, with the file F2 here, just literally swap them. So when the system or when the user tries to run file F1, instead they'll be running file F2. And of course that could cause all sorts of damage. And so the way to defend against that is essentially by placing the file name inside of the MAC'd area, so that in fact we're computing an integrity check on the file name as well as on the contents of the file. And as a result, if the virus tries to swap two files, the system will say, hey, the file that's located in position F1 doesn't have the right name, and therefore it will detect that the virus did the swap, even though the Mac actually verifies. So it is important to remember that Macs can help you defend against file tampering or data tampering in general, but they won't help you defend against swapping of authenticated data, and that has to be done by some other means. Okay, so that concludes our introduction to Macs, and in the next segment we'll go ahead and construct our first examples of secure Macs. Now that we know what Macs are, let's go ahead and build our first secure Macs. First, I want to remind you that a Mac is a pair of algorithms. The first is a signing algorithm that's given a message and a key will generate a corresponding tag. And the second is a verification algorithm that given a key, a message, and a tag will output 0 or 1 depending on whether the tag is valid or not. And we said that a Mac is secure if it is existentially unforgeable under a chosen message attack. In other words, the attacker is allowed to mount a chosen message attack where he can submit arbitrary messages of his choice and obtain the corresponding tags for those messages. And then despite the ability to generate arbitrary tags, the attacker cannot create a new message tag pair that was not given to him during the chosen message attack. Okay, so we've already seen this definition in the last segment, and now the question is, how do we build secure Macs? So the first example I want to give you is basically showing that any secure PRF directly gives us a secure Mac as well. So let's see how we do it. So suppose we have a pseudo-random function. So the pseudo-random function takes inputs in x and outputs in y. And let's define the following MAC. So the way we sign a message m is basically by simply evaluating the function at the point m. So the tag for the message m is simply the value of the function at the point m. And then the way we verify a message tag pair is by recomputing the value of the function at the message m and checking whether that's equal to the tag that was given to us. We say yes if so, and we reject otherwise. So here you have it in pictures. Basically, when Alice wants to send a message to Bob, she computes a tag by evaluating the PRF, and then she appends this tag to the message. Bob receives the corresponding message tag pair. He recomputes the value of the function and tests whether the given tag is actually equal to the value of the function at the point m. So let's look at a bad example of this instruction. And so suppose that we have a pseudo-random function that happens to output only 10 bits. Okay, so this is a fine pseudo-random function. It just so happens that for any message m, it only outputs 10-bit value. My question to you is, if we use this function f to construct a MAC, is that going to be a secure MAC? So the answer is no, this MAC is insecure, in particular because the tags are too short. So consider the following simple adversary. What the adversary will do is simply choose an arbitrary message m and just guess the value of the MAC for that particular message. Now, because the tag is only 10 bits long, the adversary has a chance of 1 in 2 to the 10 in guessing the MAC correctly. In other words, the advantage of this guessing adversary, one that simply guesses a random tag for a given message, that adversary is going to have advantage against the MAC that's basically 1 over 2 to the 10, which is 1 over 1024, and that's definitely non-negligible. So the adversary basically will successfully forge the MAC on a given message with probability 1 in 1000, which is insecure. However, it turns out this is the only example where things can go wrong. Only when the output of the function is small can things go wrong. If the output of the PRF is large, then we get a secure MAC out of this function. And let's state the security theorem here. So suppose we have a function f that takes messages in x and outputs tags in y. Then the MAC that's derived from this PRF, in fact, is a secure MAC. And in particular, if you look at the security theorem here, you'll see very clearly the error bounds. In other words, since the PRF is secure, we know that this quantity here is negligible. And so if we want this quantity to be negligible, this is what we want. We want to say that no adversary can defeat the MAC I sub f. That implies that we want this quantity to be negligible. In other words, we want the output space to be large. And so, for example, taking a PRF that outputs 80 bits is perfectly fine. That will generate an 80-bit MAC. And therefore, the advantage of any adversary will be at most 1 over 2 to the 80. So now the proof of this theorem is really simple. So let's just go ahead and do it. So in fact, let's start by saying that suppose instead of a PRF, we have a truly random function from the message space to the tag space. So this is just a random function from x to y that's chosen at random from the set of all such functions. Now let's see if that function can give us a secure MAC. So what the adversary says is, I want a tag on the message m1. What he gets back is the tag, which just happens to be the function evaluated at the point m1. Notice there's no key here because f is just a truly random function from x to y. And then the adversary gets to choose a message m2, and he obtains the tag on m2. He chooses m3, m4 up to mq, and he obtains all the corresponding tags. Now his goal is to produce a message tag pair, and we say that he wins, remember, if this is an existential forgery. In other words, first of all, t has to be equal to f of m. This means that t is a valid tag for the message m. And second of all, the message m has to be new. So the message m had better not be one of m1 to mq. But let's just think about this for a minute. What does this mean? So the adversary got to see the value of a truly random function at the points m1 to mq. And now he's supposed to predict the value of this function at some new point m. However, for a truly random function, the value of the function at the point m is independent of its value at the points m1 to mq. So the best the adversary can do at predicting the value of the function at the point m is just guess the value, because he has no information about f of m. And as a result, his advantage, if he guesses the value of the function at the point m, he'll guess it right with probability exactly 1 over y. And then this tag that he produced will be correct with probability exactly 1 over y. Okay, again, he had no information about the value of the function at m, and so the best he can do is guess, and if he guesses, he'll get it right with probability 1 over y. And now, of course, because the function capital F is a pseudo-random function, the adversary is going to behave the same whether we give him the truly random function or the pseudo-random function. The adversary can't tell the difference, and as a result, even if we use a pseudo-random function, the adversary is going to have advantage at most 1 over y in winning the game. Okay, so you can see exactly in the security theorem. Let's go back there for just a second. Essentially, this is basically why we got an error term of 1 over y because of the guessing attack, and that's the only way that the attacker can win the game. So now that we know that any secure PRF is also a secure MAC, we already know that we have our first example MAC. In particular, we know that AES, or at least we believe that AES is a secure PRF. Therefore, AES, since it takes 16-byte inputs, right, the message space for AES is 128 bits, which is 16 bytes. Therefore, the AES cipher essentially gives us a MAC that can MAC messages that are exactly 16 bytes. Okay, so that's our first example of a MAC. But now the question is, if we have a PRF for small inputs like AES that only acts on 16 bytes, can we build a MAC for big messages that can act on gigabytes of data? Sometimes I call this the McDonald's problem. Basically, given a small MAC, can we build a big MAC out of it? In other words, given a MAC for small messages, can we build a MAC for large messages? So we're going to look at two constructions for doing so. The first example is called a CBC MAC that again takes a PRF for small messages as input and produces a PRF for very large messages as output. And the second one we'll see is HMAC, which does the same thing, again takes a PRF for small inputs and generates a PRF for very large inputs. Now the two are used in very different contexts. CBC MAC is actually very commonly used in the banking industry. For example, there's a system called the Automatic Clearinghouse, ACH, which banks use to clear checks with one another. And in that system, CBC MAC is used to ensure integrity of the checks as they're transferred from bank to bank. On the internet, protocols like SSL and IPsec and SSH, those all use HMAC for integrity. Okay, so these are two different MACs and we're going to discuss them in the next couple of segments. And as I said, both of them start from a PRF for small messages and produce a PRF for messages that are gigabytes long. And in particular, they can both be instantiated with AES as the underlying cipher. So the last comment I want to make about these PRF-based MACs is that in fact their output can be truncated. So suppose we have a PRF that outputs n-bit outputs. So again, for AES, this would be a PRF that outputs 128 bits as output. It's an easy lemma to show that in fact if you have an n-bit PRF, if you truncate it, in other words, if you only output first t bits, the result is also a secure PRF. And just the intuition here is if the big PRF outputs n bits of randomness for any inputs that you give to the PRF, then certainly chopping it off and truncating it to t bits is still going to look random. The attacker now gets less information, so his job in distinguishing the outputs from random just became harder. In other words, if the n-bit PRF is secure, then the t less than n-bit PRF, the truncated PRF, would also be secure. So this is an easy lemma. Since any secure PRF also gives us a secure MAC, what this means is if you give me a MAC that's based on a PRF, what I can do is I can truncate it to W bits. However, because of the error term in the MAC-based PRF theorem, we know that truncating to W bits will only be secure as long as 1 over 2 to the W is negligible. So if you truncate the PRF to only 3 bits, the resulting MAC is not going to be secure. However, if you truncate it to say 80 bits or maybe even 64 bits, then a resulting MAC is still going to be a secure MAC. Okay, so the thing to remember here is that even though we use AES to construct larger PRFs and the output of these PRFs is going to be 128 bits, it doesn't mean that the MAC itself has to produce 128-bit tags. We can always truncate the output to 90 bits or 80 bits, and as a result, we would get still secure MACs, but now the output tag is going to be more reasonable size and doesn't have to be the full 128 bits. Okay, so in the next segment, we're going to look at how the CBC MAC works. In this segment, we're going to construct two classic MACs, the CBC MAC and the NMAC. Recall that in the last segment, we said that if you give me a secure PRF, then that secure PRF can actually be used to construct a secure MAC simply by defining the signature on a message M as the value of the function at the point M. The only caveat was that the output of the PRF F had to be large. For example, it could be 80 bits or 128 bits, and that would generate a secure MAC. Now, we also said that because AES is a secure PRF, essentially AES already gives us a secure MAC, except that it can only process 16-byte messages. And the question now is, given a PRF for short messages, like AES for 16-byte messages, can we construct a PRF for long messages that are potentially gigabytes long? It's just shorthand for what's coming. I'm going to denote by X the sets 0, 1 to the N, where n is the block size for the underlying PRF. So since we're always going to be thinking of AES as the underlying PRF, you can think of n as essentially 128 bits. So our first construction is called the encrypted CBC MAC, or ECBC for short, encrypted CBC MAC. So ECBC uses a PRF that takes messages in the set X, 0, 1 to the n, and outputs messages in the same set X. And what we're going to be building is a PRF that basically takes pairs of keys. It takes very long messages, in fact, arbitrarily long messages, and I'll explain this in just a second. And it outputs also tags in 0, 1 to the n. So that's our goal. Now, what is this x to the less than or equal to L? The point here is that, in fact, CBC MAC can take very long messages up to L blocks. L could be 1,000,000 or 1,000,000,000. But it can also take variable length messages as input. In other words, x less than or equal to L means that we allow the input to be messages that contain an arbitrary number of blocks between 1 and L. So ECBC can process messages that are 1 block long, 2 blocks long, 10 blocks long, 100 blocks long. It's perfectly fine to give it variable size inputs, but just to keep the discussion simple, we upper bound the maximum length by capital L. So let's see how ECBC works. Well, we start by taking our message and breaking it into blocks. Each block is as long as a block of the underlying function f. And then essentially we run through the CBC chain, except that we don't output intermediate values. So you notice we basically encrypt the first block and then feed the results into the XOR with the second block and then feed that into f again. And we do that again and again and again. And finally, we get a value out here, which is called the CBC output of this long chain. And then I would like to point your attention to the fact that we do one more encryption step, and this step is actually done using an independent key, K1, that's different and chosen independently of the key K, and finally the output gives us a tag. So in this case the tag would be n bits long, but we also mentioned in the previous segment that it's fine to truncate the tag to less than n bits long as 1 over 2 to the n is negligible. So now you can see that FECBC takes a pair of keys as inputs, it can process variable length messages, and it produces an output in the set X. So you might be wondering what this last encryption step is for, and I'll tell you that the function that's defined without this last encryption step is called a raw CBC function. In other words, if we simply stop processing over here and we take that as the output, that's called raw CBC. And as we'll see in a minute, raw CBC is actually not a secure MAC. So this last step is actually critical for making the MAC secure. So another classic construction for converting a small PRF into a large PRF is called NMAC for nested MAC. Now the NMAC starts from a PRF that, as before, takes inputs in X, but outputs element in the key space. Remember that for CBC, the output has to be in the set X. Here, the output needs to be in the key space K. And again, we basically obtain the PRF F NMAC, which takes pairs of keys as input, again, can process variable length messages up until L blocks, and the output is an element in the key space. And the way NMAC works is kind of starts as before. We take our message and we break it into blocks. Each block is, again, as big as the block length of the underlying PRF. And now we take our key and we feed our key as the key input into the function f, and the message block is given as the data input into the function f. What comes out is the key for the next block of NMAC. So now we have a new key for the next evaluation of the PRF, and the data for the next evaluation is the next message block. And so on and so forth until we reach the final output. The final output is going to be an element in K. Okay, and just as before, in fact, if we stop here, the function that we obtain is called a cascade function, and we're going to look at cascade in more detail in just a minute. So cascade will output an element in K. However, that, as we'll see again, is not a secure MAC. To get a secure MAC, what we do is we need to map this element T, which is in K, into the set X. And so typically, as we'll see, NMAC is used with PRFs where the block length X is much bigger than the key length. And so what we do is we simply append fixed pad. FPAD is called a fixed pad that gets appended to this tag T. And then this becomes, this input here, this block here becomes an element of X. We feed this into the function. And again, notice here that there's an independent key that's being used for the last encryption step. And then finally, the last tag is an element of K, which we output as the output of NMAC. So remember, without the last encryption step, the function is called a cascade. With the last encryption step, as we'll see, which is necessary for security, we actually get a PRF which outputs elements in K and can process variable length messages that are up to L blocks long. All right, so that's the nMac construction. So now we have two Macs that we can use to build a large PRF from AES, basically. So before we analyze the security of these Mac constructions, I'd like you to understand better what the last encryption step is for. So let's start with nMac. So I claim that it's actually very easy to see that if we omitted the last encryption step, in other words, if we just used the cascade function, then the Mac would be completely insecure. Okay, so suppose we look at this Mac defined over here. In other words, all we do is we output directly the cascade applied to M without the last encryption step. Then let me ask you, how would you forge tags for this Mac? And I guess I've kind of given it away that this answer is incorrect. So I hope everybody sees that the answer is that, in fact, given one chosen message query, you can mount an existential forgery. And the reason is, I'll show you in a second in the diagram, but let me write it out in symbols first. The reason is, if you give me the output of the cascade function applied to a message M, I can derive from it, me being the adversary, I can derive from it the cascade applied to the message M concatenated W for any message W, for any W. So first of all, it should be clear that this is enough to mount an existential forgery, because essentially by asking for a tag on this message, I obtain the tag on this longer message, which I can then output as my forgery. Okay, so the Mac is insecure because I'm given a Mac on one message, I can produce the Mac on another message. But let's go back to the diagram describing cascade and see why this is true. And so let's see what happens if this last step isn't there. As an attacker, what I can do, I can add one more block here, which we called W. And then basically I can take the output of cascade, which is this value t, and I can simply apply the function f to it again. So here I'll take this t value, I'll plug it into f, and plug my last block w into it. And what I'll get is t prime, which is, well, the evaluation of cascade on the message m concatenated w. And now I've calculated t prime, which I can use for my existential forgery. Okay, so this kind of shows you why this property of cascade holds. This is called an extension attack. We're given the tag of the message m, I can deduce the tag for an extension of m, and in fact for any extension of my choice. So basically, cascade is completely insecure if we don't do this last encryption step, and the last encryption step here basically prevents this type of extension attack. I can tell you, by the way, that in fact extension attacks are the only attacks on cascade, and that can be made precise, but I'm not going to do that here. The next question is, why did we have the extra encryption block in the ECBC construction? So again, let me show you that without this extra encryption block, ECBC is insecure. So let's define a Mac that uses raw CBC. In other words, it's the same as CBC Mac, but without the last encryption step. And let's see that that Mac is also insecure, except now the attack is a little bit more difficult than a simple extension attack. So suppose the attacker is given this value, the raw CBC value for a particular message M, and now the attacker wants to extend and compute the Mac on some message M concatenated with some word W. So here's our W. Well, the poor attacker can take this value and try to XOR the two together, but now you realize he has to evaluate the function at this point. But he doesn't know what this key K is, and as a result, he doesn't know what the output of the function is. So he simply can't just append a block W and compute the value of raw CBC on M concatenated W. However, it turns out that he can actually evaluate this function by using the chosen message attack. And I want to show you how to do that. Okay, so we said that basically, so our goal is to show that raw CBC is insecure. So let's look at a particular attack. So in the attack, the adversary is going to start by requesting the tag on a particular message M that's a one block message. So what does it mean to apply CBC to a one block message? Well, basically all you do is you just apply the function f directly. So what you get is the tag, which is just the application of f, directly to the one block message M. Good. So now the adversary has this value t. And now I claim that he can define this message M prime, which contains two blocks. The first block is M, the second block is T XOR M, and I claim that the value t that he just received is a valid tag for this two block message M prime. So let's see why that's true. Well, so suppose we apply the raw CBC construction to this message M prime. So if you plug it in directly, let's see. So the way it would work is, first of all, the first message M is processed by encrypting it directly using the function f. Then we XOR the result with the second block, which is T XOR M. And then we apply f to the result of that. That is the definition of raw CBC. Now what do we know about FKM? FKM is simply this value t by definition. So the next step we get is essentially t XOR t XOR m. But this t XOR t simply goes away, and what we get is fk of m, which is of course t, and as a result, t is a valid MAC for the 2-block message m, t XOR m. So the adversary was able to produce this valid tag t for this 2-block message that he never queried. And therefore, he was able to break the MAC. So let's look at the ECBC diagram for just one more second. And let me point out that if you don't include this last encryption step in the computation of the MAC, essentially the MAC would be insecure because of the attack that we just saw. And I'll tell you that there are many products that do this incorrectly. And in fact, there are even standards that do this incorrectly so that the resulting MAC is insecure. You now know that this needs to be done, and you won't make this mistake yourself. So let's state the ECBC and NMAC security theorems. And so the statement is as usual for any message length that we'd like to apply the MAC to. Essentially, for every PRF adversary A, there's an efficient adversary B, and these are kind of the usual statements, where the facts that you need to know are the error terms, which are kind of similar in both cases. By the way, I'd like to point out that the analysis for CBC actually uses the fact that F is a PRP. Even though we never had to invert F during the computation of ECBC, the analysis is better if you assume that F is actually a PRP. In other words, it's invertible, not just a function. For NMAC, the PRF need not be invertible. So what these error terms basically say is that these MACs are secure as long as key is not used to MAC more than square root of x or square root of k messages. So for AS, of course, this would be 2 to the 64. But I want to show you an example of how you would use these bounds. And so here I stated the security theorem again for the CBC MAC. And Q here, again, is the number of messages that are MAC'd with a particular key. So suppose we want to ensure that for all adversaries, the adversary has an advantage less than 1 over 2 to the 32 in distinguishing the PRF from a truly random function. Suppose that's our goal. Well, by the security theorem, what that means is we need to ensure that Q squared over x is less than 1 over 2 to the 32. Right? We want this term to be, well, I'm going to ignore this 2 here just for simplicity. We want to ensure this term is less than 1 over 2 to the 32. And this term, of course, is negligible, so we can just ignore it. And this would imply that this term is also less than 1 over 2 to the 32. Okay, so if we want to ensure that the advantage is less than 1 over 2 to the 32, we need to ensure that Q squared over x is less than 1 over 2 to the 32. For AES, basically, this means that after macking 2 to the 48 messages, you have to change your key. Otherwise, you won't achieve the security level. So you can mac at most 2 to the 48 messages. You notice that if I plug in triple des, which has a much shorter block, only 64 bits, the same result says you now have to change your key every 65,000 messages. So this basically is quite problematic, whereas this is fine. This is actually a fairly large number. For AES, this means you have to change your key only every 16 billion messages, which is perfectly reasonable. And so this is one of the reasons why AES has a larger block than triple des. These modes remain secure, and you don't have to change your key as often as you would with triple des. Okay, so I want to show you that in fact these attacks are not just in the statements in the security theorem. In fact, there really are real attacks that correspond to these values. The MACs really do become insecure after you assign, square root of x or square root of k messages. So I'm going to show you an attack on both PRFs, so either ECBC or NMAC, assuming that the underlying function is a PRP, is actually a block cipher, like AES. Let's call it fbig. Let's say that fbig is either FECBC or FNMAC. Fbig means it's a PRF for large messages. Now, it turns out both constructions have the following extension property. Namely, if you give me a collision on messages x and y, then in fact that also implies a collision on an extension of x and y. In other words, if I append w to both x and y, I'll also get a collision on the resulting words. So it's fairly easy to convince yourself that this extension property holds, and you do it just by staring at the diagram for a second. And so imagine I give you two messages that happen to collide at this point. Now remember, I assumed that f is a PRP, so once you fix k1, it's a one-to-one function. So if the two messages happen to map to the same value at the output, this means they also happen to map to the same value at the output of the raw CBC function. But if they map to the same value at the output of the raw CBC function, that means that if I add another block, let's call it W, and I take this output here, then I'm computing the same value for both messages, and for both messages I'll get the same value at this point too. And when I encrypt, again, with K1, I'll also get, so there's one more F here. I'll also get the same output, final output, after I've appended the block W. Okay, so if the two values happen to be the same for two distinct messages, if I append the block W to both messages, I'm still going to get the same value out. It's easy to convince yourself that the same is true for NMAC as well. Okay, so both of these PRFs have this extension property. So based on this, we can define an attack. So here's the extension property stated again, and the attack would work as follows. Suppose I issue square root of y chosen message queries. So for AES, remember the value of y is basically 0, 1 to the 128. So this would mean that I would be asking 2 to the 64 chosen message queries for just arbitrary messages in the input space. Well, what will happen is I'll obtain 2 to the 64 message MAC pairs. Now we're going to see in the next module actually that there's something called the birthday paradox. Some of you may have heard of it already. That basically says that if I have 2 to the 64 random elements of a space of size 2 to the 128, there's a good chance that two of them are the same. So I'm going to look for two distinct messages, MU and MV, for which the corresponding MACs are the same. Okay, and as I said, by the birthday paradox, these are very likely to exist. Once I have that, now I've basically found MU and MV that have the same MAC, and as a result, what I can do is I can extend MU with an arbitrary word W and ask for the tag for the word MU concatenated W. But because MU and MV happen to have the same output, I know that MU concatenated W has the same output as MV concatenated W. So now that I've obtained the output for MU concatenated W, I also have the output for MV concatenated W. And therefore I've obtained my forgery. Okay, so now T is also a forgery for the message MV concatenated W, which I've never asked before, and therefore this is a valid existential forgery. Okay, so this is kind of a cute attack. And the bottom line here is that, in fact, after square root of y queries, I am able to forge a MAC with fairly good probability. Okay, so what does square root of y mean? If we go back to the security theorems, this means that basically for ECBC after square root of x, or for NMAC after square root of k messages have been MAC'd, the MAC becomes insecure and the attacker can actually find new MACs for messages for which he was never given a MAC for. So again, this is a cute attack that shows that the bounds of the theorem really are real, and as a result, these bounds that we derived in this example are real, and you should never use a single key to MAC more than, say, 2 to the 48 messages with AES-based CBC. So to conclude, I'll just mention that we've seen two examples. We saw ECBC and NMAC. ECBC is in fact a very commonly used MAC that's built from AES. 802.11i, for example, uses ECBC with AES for integrity. There's also a NIST standard called CMAC that we'll talk about in the next segment that also is based on CBC MAC. NMAC, in contrast, is not typically used with a block cipher, and the main reason is you notice that in the NMAC construction, the key changes from block to block. That means that the whole AES key expansion has to be computed and recomputed on every block, and AES is not designed to perform well when you change its key very rapidly. And so typically when you use NMAC, you use block ciphers that are better at changing their keys on every block. And as a result, NMAC typically is not used with AES. But in fact, NMAC is a basis of a very popular MAC called HMAC, which we're also going to look at next. And you'll see very clearly the NMAC underlying the HMAC construction. Okay, so that's the end of this segment, and we'll talk about more MACs in the next segment. In the last segment, we talked about the CBC MAC and the NMAC, but throughout the segment, we always assumed that the message length was a multiple of the block size. In this segment, we're going to see what to do when the message length is not a multiple of the block size. So recall that the encrypted CBC MAC, or ECBC MAC for short, uses pseudo-random permutation F to actually compute the CBC function, as we discussed in the last segment. But in the last segment, we always assumed that the message itself could be broken into an integer number of blocks for the block cipher. And the question is what to do when the message length is not a multiple of the block size. So here we have a message where the last block actually is shorter than the full block, and the question is how to compute the ECBC MAC in that case. So the solution, of course, is to pad the message, and the first pad that comes to mind is to simply pad the message with all zeros. In other words, we take the last block and just add zeros to it until the last block becomes as long as one full block size. And so my question to you is whether the resulting MAC is secure. So the answer is no, the MAC is not secure, and let me explain why. Basically, the problem is that it's possible now to come up with messages so that the message M and the message M concatenated 0 happen to have exactly the same pad. And as a result, once we plug in both M and M0 into ECBC, we'll get the same tag out, which means that both M and M concatenated 0 have the same tag, and therefore the attacker can mount an existential forgery. He would ask for the tag on the message M, and then he would output as his forgery the tag on the message M concatenated 0. And it's easy to see why that's the case. Basically, to be absolutely clear, here we have our message M, which after padding becomes M000. Say we had to add 3 zeros to it. And here we have the message M0, M that ends with 0, and after padding, we basically now only have to add 2 zeros to it. And lo and behold, they become the same pad, so that they're going to have exactly the same tag, which allows the adversary to mount the existential forgery attack. So this is not a good idea. In fact, appending all zeros is a terrible idea. And if you think about a concrete case where this comes up, imagine in the automatic clearinghouse system used for clearing checks, I might have a check for $100 and a tag on that check. Well, now the attacker basically could append a 0 to my check and make it a check for $1,000, and that wouldn't actually change the tag. So this ability to extend the message without changing the tag actually could have pretty disastrous consequences. So I hope this example convinces you that the padding function itself must be a one-to-one function. In other words, it should be the case that two distinct messages always map to two distinct padded messages. We shouldn't actually have a collision on the padding function. Another way of saying it is that the padding function must be invertible. That guarantees that the padding function is one-to-one. So a standard way to do this was proposed by the International Standards Organization, ISO. What they suggested is basically let's append the string 10000 to the end of the message to make the message be a multiple of the block length. Now, to see that this padding is invertible, all we do is describe the inversion algorithm, which simply is going to scan the message from right to left until it hits the first 1, and then it's going to remove all the bits to the right of this 1, including the 1. And you see that once we remove the pad in this way, we obtain the original message. So here's an example. So here we have a message where the last block happens to be shorter than the block length, and then we append the 100 string to it. It's very easy to see what the pad is. Simply look for the first 1 from the right. We can remove this pad and recover the original message back. Now there's one corner case that's actually quite important, and that is, what do we do if the original message length is already a multiple of the block size? In that case, it's really very, very important that we add an extra dummy block that contains the pad 1000. And again, I can't tell you how many products and standards have actually made this mistake where they didn't add a dummy block, and as a result, the MAC is insecure because there's an easy existential forgery attack. And let me show you why. So suppose, in case the message is a multiple of the block length, suppose we didn't add a dummy block and we literally MAC'd this message here. Well, the result now is that if you look at the message which is a multiple of the block size, and a message which is not a multiple of the block size but is padded to the block size, and imagine it so happens that this message M'1 happens to end with 100. At this point, you realize that here, the original message here, let me draw it this way, you realize that the original message, after padding, would become identical to the second message that was not padded at all. And as a result, if I ask for the tag on this message over here, I would obtain also the tag on the second message that happened to end in 100. Okay, so if we didn't add the dummy block, basically again the pad would be not invertible because two distinct messages happen to map to the same padded result. Again, as a result, the MAC becomes insecure. So to summarize, this ISO standard is a perfectly fine way to pad, except you have to remember to also add a dummy block in case the message is a multiple of the block length to begin with. Now some of you might be wondering if there's a padding scheme that never needs to add a dummy block. And the answer is that if you look at the deterministic padding function, then it's pretty easy to argue that there will always be cases where we need to pad. And the reason is just literally the number of messages that are a multiple of the block length is much smaller than the total number of messages that need not be a multiple of the block length. And as a result, we can't have a one-to-one function from this bigger set of all messages to the smaller set of messages which are a multiple of the block length. There will always be cases where we have to extend the original message, and in this case that would correspond to adding this dummy padding block. However, there is a very clever idea called CMAC, which shows that using a randomized padding function, we can avoid having to ever add a dummy block. And so let me explain how CMAC works. So CMAC actually uses 3 keys, and in fact sometimes this is called a 3-key construction. So the first key K is used in the CBC, the standard CBC MAC algorithm. And then the keys K1 and K2 are used just for the padding scheme at the very, very last block. And in fact, in the CMAC standard, the keys K1, K2 are derived from the key K by some sort of a pseudorandom generator. So the way CMAC works is as follows. Well, if the message happens to not be a multiple of the block length, then we append the ISO padding to it, but then we also XOR this last block with a secret key K1 that the adversary doesn't know. However, if the message is a multiple of the block length, then of course we don't append anything to it, but we XOR it with a different key K2 that, again, the adversary doesn't actually know. So it turns out, just by doing that, it's now impossible to apply the extension attacks that we could do on the cascade function and on raw CBC, because the poor adversary actually doesn't know what is the last block that went into the function. He doesn't know K1, and therefore he doesn't know the value at this particular point, and as a result he can't do an extension attack. In fact, this is a provable statement. So that this construction here, simply by XORing K1 or XORing K2, is really a PRF, despite not having to do a final encryption step after the raw CBC function is computed. So that's one benefit, that there's no final encryption step. And the second benefit is that we resolve this ambiguity between whether padding did happen or padding didn't happen by using 2 different keys to distinguish the case that the message is a multiple of the block length versus the case where it's not, but we have a pad appended to the message. So the 2 distinct keys resolve this ambiguity between the 2 cases, and as a result, this padding actually is sufficiently secure. And as I said, there's actually a nice security theorem that goes with CMAC that shows that the CMAC construction really is a pseudorandom function with the same security properties as CBCMAC. So I wanted to mention that CMAC is a federal standard, standardized by NIST, and if you now these days wanted to use a CBCMAC for anything, you would be actually using CMAC as the standard way to do it. Particularly in CMAC, the underlying block cipher is AES, and that gives us a secure CBCMAC derived from AES. So that's the end of the segment, and in the next segment we'll talk about a parallel MAC. In the last 2 segments, we talked about the CBCMAC and NMAC to convert a PRF for small messages into a PRF for much larger messages. Those 2 constructions were sequential in the sense that if you had multiple processors, you couldn't make the construction work any faster. In this segment, we're going to look at a parallel MAC that also converts a small PRF into a large PRF, but does it in a very parallelizable fashion. In particular, we're going to look at a parallel MAC construction called PMAC that uses an underlying PRF to construct a PRF for much larger messages. In particular, the PRF can process much longer messages that can have variable length and have as many as L blocks in them. Now the construction works as follows. We take our message and we break it into blocks, and then we process each block independently of the other. So the first thing we do is we evaluate some function P and we XOR the result into the first message block, and then we apply our function F using a key K1. We do the same for each one of the message blocks, and you notice that we can do it all parallel. All message blocks are processed independently of one another. And we collect all these results into some final XOR, and then we encrypt one more time to get the final tag value. Now for a technical reason, actually on the very last block, we actually don't need to apply the PRFF, but as I said, this is just for a technical reason, and I'm going to ignore that for now. Now I want to explain what the function P is for and what it does. So imagine just for a second that the function P isn't actually there. That is, imagine we actually directly feed each message block into the PRF without applying any other processing to it. Then I claim that the resulting MAC is completely insecure. And the reason is that essentially no order is enforced between the message blocks. In particular, if I swap 2 message blocks, that doesn't change the value of the final tag. Because the XOR is commutative, the tag will be the same whether we swap the blocks or not. As a result, an attacker can request the tag for a particular message, and then he obtains a tag for a message where 2 of the blocks are swapped, and that counts as an existential forgery. So what this function P tries to do is essentially enforce order on these blocks, and you notice that the function takes, first of all, it's a keyed function, so it takes a key as input. And second of all, more importantly, it takes the block number as input. In other words, the value of the function is different for each one of the blocks. And that's actually exactly what's preventing this blocks swapping attack. So the function p actually is a very easy to compute function. Essentially, given the key and the message block, all it is just a multiplication in some finite field. So it's a very, very simple function to compute. It adds very little to the running time of PMAC, and yet it's enough to ensure that the PMAC is actually secure. As we said, the key for PMAC is this pair of keys, one key for the PRF and one key for this masking function p. And finally, I'll tell you that if the message length is not a multiple of the block length, that is, imagine the last block is shorter than full block length, then PMAC actually uses a padding that's similar to CMAC so that there is no need for an additional dummy block ever. So that's the PMAC construction, and as usual we can state its security theorem. So the security theorem, by now you should be used to it. Essentially it says that if you give me an adversary attacking PMAC, I can construct an adversary attacking the underlying PRF plus an additional error term. And so, since again the PRF is secure, we know that this term is negligible. And so if we want this term to be negligible, we know that we need this error term to also be negligible. Here, as usual, Q is the number of messages that are MAC'd using a particular key. And L is the maximum length of all those messages. And PMAC is secure as long as this product is less than the square root of the block size. So for AES, this would be 2 to the 128. The square root, therefore, would be 2 to the 64. So the MAC would be secure as long as Q times L is less than 2 to the 64. And every time as it gets closer to that value, of course, you would have to change the key in order to continue macking more messages. So the main thing to remember is that PMAC also gives us a PRF, and when it processes the message blocks independently of one another. Turns out that PMAC also has a very interesting property, namely that PMAC MAC is incremental. So let me explain to you what that means. So suppose the function f that's used to construct PMAC is not just a PRF, but in fact a permutation, a PRP. So we can actually invert it when we need to. Now suppose we've already computed the MAC for a particularly long message m. And now suppose just one message block of this long message changes. So here m1 is changed into m'1, but the remaining message blocks all remain the same. For other MACs like CBC MAC, even though only one message block changed, you would have to recompute the tag on the entire message. Recomputing the tag basically would take time that's proportional to the length of the message. It turns out with PMAC, if we only change one block or a small number of blocks, actually we can recompute the value of the tag for the new message very, very quickly. And let me ask you a puzzle to see if you can figure out how to do that yourself. And remember, the function f is a PRP and therefore is invertible. So let's see if you can figure out how to compute the MAC and the new message by yourself. So it turns out this can be done, and you can quickly recompute the tag and the new message using this third line here. So just to make sure we all see the solution, let's quickly go back to the original diagram for PMAC, and I can show you what I mean. So imagine this one message block changed into some other block, say changed into m'1. Then what we could do is we can take the tag on the original message before the change was made. So we can invert the function f and determine the value before the function f was applied. Now, well, since we now have an XOR of a bunch of blocks, what we can do is we can cancel out the XOR that came from the original message block, basically by XORing this value that came from the original message block into this XORed accumulator, and then XORing again the value that would come from the new message block back into the XOR accumulator, and then apply the function f again. And that would give us the tag for the new message where just one block was changed. So in symbols, basically, I wrote the formula over here. You can see basically we decrypt the tag, and then we XOR with the block that comes from the original message block. We XOR again with the block that comes from the new message block, and then we re-encrypt the final XOR accumulator to get the new tag for the message with the one block changed. So that's kind of a neat property. It kind of shows that if you have very large messages, you can very quickly update the tag. Of course, you would need a secret key to do the update, but you can quickly update the tag if just a small number of message blocks changed. Okay, so that concludes our discussion of PMAC, and now I want to switch topics a little bit and talk about the concept of a one-time MAC, which is basically the analog of the one-time pad, but in the world of integrity. So let me explain what I mean by that. So imagine we want to build a MAC that is only used for integrity of a single message. In other words, every time we compute the integrity of a particular message, we also change the key so that any particular key is used only for integrity of one message. Then we can define the security game as basically saying the attacker is going to see one message, therefore we only allow him to do one chosen message attack. So he gets to submit one message query, and he is given the tag corresponding to that one message query, and now his goal is to forge a message tag pair. Okay, so you can see his goal is to produce one message tag pair that verifies correctly and is different from the pair that he was actually given. As we'll see, just like the one-time pad and stream ciphers were quite useful, it turns out one-time acts are also quite useful for the same applications where we only want to use a key to encrypt or to provide integrity for just a single message. So as usual, we would say that a one-time ACK is secure if basically no adversary can win this game. Now the interesting thing is that one-time ACKs, just like the one-time pad, can be secure against infinitely powerful adversaries. And not only that, because they're only designed to be secure for one-time use, they can actually be faster than MACs that are based on PRFs. And so I just wanted to give you a quick example of one-time MAC. This is a classic construction for a one-time MAC, and let me show you how it works. The first step is to pick a prime that's slightly larger than our block size. In this case, we're going to use 128-bit blocks, so let's pick the first prime that's bigger than 2 to the 128. This happens to be 2 to the 128 plus 51. And now the key is going to be a pair of random numbers in the range 1 to r prime, so 1 to q. So we choose two random integers in the range 1 to q. Now we're given a message, so we're going to take our message and break it into blocks where each block is 128 bits. And we're going to regard each number as an integer in the range 0 to 2 to the 128 minus 1. Now the MAC is defined as follows. The first thing we do is we take our message blocks and we kind of construct a polynomial out of them. So if there are L blocks in our message, we're going to construct a polynomial of degree L, and you notice that the constant term of this polynomial is set to 0. And then we define the MAC very simply. Basically what we do is we take the polynomial that corresponds to the message, we evaluate it at the point k, that's one half of our secret key, and then we add the value a, which is the second half of our secret key. And that's it. That's the whole MAC. So just basically construct the polynomial that corresponds to our message, evaluate that polynomial at a half of the secret key, and add the other half of the secret key to the result, and of course reduce the final result modulo q. Okay, so that's it. So that's the whole MAC. It's a one-time secure MAC. And the way we argue that this MAC is one-time secure, essentially is by arguing that if I tell you the value of the MAC for one particular message, that tells you nothing at all about the value of the MAC at another message. And as a result, even though you've seen the value of the MAC on a particular message, you have no way of forging this MAC on some other message. Now I should emphasize that this is a one-time MAC, but it's not two-time secure. In other words, if you get to see the value of the MAC on two different messages, that actually completely compromises the secret key, and you can actually predict the MAC for a third or fourth message of your choice. So then the MAC becomes forgeable. But for one-time use, it is a perfectly secure MAC, and I'll tell you that in fact this is a very fast MAC to evaluate. So now that we've constructed one-time MACs, it turns out there's actually a general technique that will convert one-time MACs into many-time MACs. And I just wanted to briefly show you how that works. So suppose we have our one-time MAC, let's call it S and V for signing and verification algorithms. And let's just assume that the tags themselves are n-bit strings. In addition, let's also look at a PRF, a secure PRF that also happens to output n-bit strings, but also takes as inputs n-bit strings. Let's now define a general construction for a MAC. These MACs are called Carter-Wegman MACs. That works as follows. Basically what we would do is we would apply the one-time MAC to the message M, and then we're going to encrypt the result using the PRF. So how do we encrypt the result? Well, we choose a random R, and then we compute kind of a one-time pad from this R by applying the PRF to it, and then we XOR the result with the actual one-time MAC. So the neat thing about this construction is that the fast one-time MAC is applied to the long message, which could be gigabytes long, and the slower PRF is only applied to this nonce R, which is then used to encrypt the final result of the MAC. And you can argue that if the MAC that was given to us as a building block is a one-time secure MAC, and the PRF is secure, then in fact we get a many-time secure MAC that happens to output two n-bit tags. So we're going to see Carter-Wegman MACs later on when we talk about authenticated encryption. And in fact, one of the NIST standard methods for doing encryption with integrity uses a Carter-Wegman MAC for providing integrity. I wanted to mention that this Carter-Wegman MAC is a good example of a randomized MAC where this nonce R is chosen afresh every time the tag is computed. And so if, for example, if you try to compute tag for the same message twice, each time you'll choose a different R, and as a result, you'll get different tags both times. And so this is a nice example of a MAC that's actually not a pseudo-random function, not a PRF, because a single message could actually be mapped to many different tags, all of which are valid for that one message. To conclude our discussion of the Carter-Wagman MAC, let me ask you the following question. Here we have the equation for the Carter-Wagman MAC. As usual, you see the nonce R as part of the MAC. And the second part of the MAC I'm going to denote by T. This is basically the one-time MAC applied to the message M, and then encrypted using the pseudo-random function applied to the nonce R. So we'll denote the result of this XOR by T. So my question to you is, given the Carter-Wagman MAC pair R, T for a particular message M, how would you verify that this MAC is valid? And recall that this algorithm V here is the verification algorithm for the underlying one-time MAC. So this is the right answer, and to see why, just observe that this XOR here decrypts the quantity T to its plaintext value, which is basically the original underlying one-time MAC, and so we can directly feed that into the verification algorithm for the one-time MAC. The last type of MAC I wanted to tell you about is one that's very popular in internet protocols. It's called the HMAC. But before we talk about HMAC, we have to talk about hash functions, and in particular collision-resistant hash functions, and we're going to do that in the next module. So this is the end of our first module on MACs, and I wanted to point out that there's really beautiful theory that went into constructing all the MACs that we saw. I kind of gave you the highlights and showed you the main constructions, but there's really quite a bit of theory that goes into constructing these MACs, and if you'd like to learn more about that, I kind of listed a couple of key papers that you might want to look at. Let me quickly tell you what they are. The first one is what's called the three-key construction, which is the basis of CMAC, a very elegant paper that gives a very efficient construction out of CBCMAC. The second paper is a more technical paper, but basically shows how to prove the bounds of CBCMAC as a PRF. The third paper talks about PMAC and its construction, again, a very cute paper. The fourth paper talks about security of NMAC and HMAC as well. HMAC we're going to cover in the next module. The last paper I listed asks an intriguing question. Recall that all of our constructions, we always assumed that AES is a pseudo-random function for 16-byte messages, and then we built a pseudo-random function and therefore a MAC for much longer messages. This paper says, well, what do we do if AES is not a pseudo-random function, but still satisfies some weaker security property called an unpredictable function? And then they ask, if AES is only an unpredictable function, but not a pseudo-random function, can we still build MACs for long messages? And so they succeed in actually giving constructions just based on the weaker assumption that AES is an unpredictable function, but their constructions are far less efficient than CBCMAC or NMAC or PMAC that we discussed in these segments. And so if you're interested in a different perspective on how to build MACs from block ciphers like AES, please take a look at this paper, and there are actually some nice open questions to work on in this area. So this concludes our first segment on integrity, and in the next segment we're going to talk about collision resistance. In this module we're going to talk about a new concept called collision resistance, which plays an important role in providing message integrity. Our end goal is to describe a very popular MAC algorithm called HMAC that's widely used in internet protocols. HMAC itself is built from collision-resistant hash functions. Before we do that, let's do a quick recap of where we are. In the last module, we talked about message integrity, where we said that a MAC system is secure if it is existentially unforgeable under a chosen message attack. This means that even an attacker who is given the tag on arbitrary messages of his choice cannot construct a tag for some new message. And then we showed that in fact any secure PRF immediately gives us a secure MAC. And so then we turned around and said, well, can we build secure PRFs that take large messages as inputs? And so we looked at four constructions. The first construction was based on CBC. When we looked at two variants of it, one called encrypted CBC and one called CMAC. And we said that these are commonly used with AES. In fact, in the 802.11i standard, CBCMAC is used for message integrity, in particular with the AES algorithm. We looked at another mode called NMAC, which also converts a PRF for short inputs into a PRF that's capable of taking very large messages as input. And these two were both sequential MACs. We then looked at a parallelizable MAC called PMAC, which again was able to convert a PRF for small inputs into a PRF for very large inputs, but it did so in a parallel fashion, so a multiprocessor system would be more efficient with PMAC than, say, with CBCMAC. All three of these built a MAC for large messages by constructing a PRF for large messages. And then we looked at the Carter-Wagman MAC, which actually is not a PRF, it's a randomized MAC. So a single message could actually have many, many different valid tags, and therefore the Carter-Wagman MAC is actually not a PRF. And if you remember, the Carter-Wagman MAC was built by, first of all, taking the bulk message and hashing it down to a small tag using a fast one-time MAC, and then encrypting that tag using a PRF. The benefit of the Carter-Wagman MAC was that, as we said, the hashing of the bulk message is done using a fast one-time MAC. And then in this module, we're going to construct MACs from this new concept called collision resistance. And so the first thing we're going to do is construct collision-resistant hash functions. So let's first of all start by defining what does it mean for a hash function to be collision-resistant. So think of a hash function from some message space to a tag space t, and you should be thinking of the message space as much, much bigger than the tag space. So the messages could be gigabytes long, but the tags would only be like 160 bits. Now, a collision for the function h is a pair of messages m0, m1 that happen to be distinct. However, when you apply the function h to them, you end up with the same output. So the image you should have in your mind is essentially there are two inputs, m0 and m1. They belong to this gigantic message space. However, when we apply the hash function to them, they happen to collide, and they both map to the same output in the tag space. Now, we say that the function h is collision resistant if it's hard to find collisions for this function. Now, this should seem a little bit counterintuitive because we know that the output space is tiny compared to the input space. So by the pigeonhole principle, there must be lots and lots and lots of messages that map to the same output, just because there isn't enough space in the output space to accommodate all the messages without collisions. And so we know that there are lots of collisions, and the question is there an efficient algorithm that finds any such collisions explicitly? So we say that the function is collision resistant if for all explicit efficient algorithms A, and these algorithms are not able to print a collision for the function h. Okay, and as usual, we'll define the advantage as the probability that the algorithm A is able to output a collision. Now, I'm not going to formalize the term explicit here. All I'll say is that it's not enough to just say that an algorithm exists, an algorithm that simply prints a collision, because we know many collisions exist. What we actually want is an explicit algorithm that we can actually write down and run on a computer to generate these collisions. There are ways to formalize that, but I'm not going to do that here. Now, a classic example of a collision-resistant hash function is SHA-256, which happens to output 256 bits, but can take arbitrarily large inputs. For example, it can take gigabytes and gigabytes of data, and it'll map it all to 256 bits, and yet nobody knows how to find collisions for this particular function. So just to show you that this concept of collision resistance is very useful, let's see a very quick application for it. In particular, let's see how we can trivially build a MAC given a collision-resistant hash function. So suppose we have a MAC for short messages. So you should be thinking something like AES, which can MAC 16-byte messages. And then suppose we have a hash function, a collision-resistant hash function, from large message space that contains gigabyte messages into our small message space, say into 16-byte outputs. Then basically we can define a new MAC, let's call it IBIG, which happens to be MACing large messages, and we'll define it simply by applying the small MAC to the output of the hash function. And how do we verify a MAC? Well, basically, given a tag, we verify it by rehashing the given message and then checking that a small MAC actually verifies under the given tag. Okay, so this is a very simple way to show you how collision resistance can take a primitive that's built for small inputs and expand it into a primitive that's built for very large inputs. And in fact, we're going to see this not just for MACs. Later on, when we talk about digital signatures, we're going to do the same thing. We're going to build a digital signature scheme for small inputs, and then we're going to use collision resistance to expand the input space and make it as large as we want. So the security theorem basically is in some sense trivial here. Basically, it says if the underlying MAC is secure and H is collision resistant, then the combination, which can actually MAC large messages, is also a secure MAC. And as a quick example, let's apply this to AES. So let's use the one example that we mentioned, SHA-256. So in this case, SHA-256 outputs 256-bit outputs, which is 32 bytes. So we have to build a MAC that can MAC 32-byte messages. And the way we could do that is basically by applying the 16-byte AES, plugging it into a 2-block CBC. A 2-block CBC would expand AES from a PRF on 16 bytes to a PRF on 32 bytes. And then take the output of SHA-256 and plug it into this 2-block CBC, based on AES. And then we get a very, very simple MAC, which is secure, assuming AES is a PRF and SHA-256 is collision resistant. So one thing I wanted to point out is that in fact collision resistance is necessary for this construction to work. So in fact, collision resistance is not just a made-up term. Collision resistance really is kind of the essence of why this combined MAC is secure. And so let's just assume for a minute that the function h, the hash function we're using, is not collision resistant. In other words, there is an algorithm that can find two distinct messages that happen to map to the same output. In this case, the combined MAC is not going to be secure because what the adversary can do is simply use the chosen message attack to get a tag for M0 and then output M1, comma, that tag as a forgery. And indeed, T is a valid MAC for M1 because H of M1 happens to be equal to H of M0. And so in doing so, just with a one chosen message attack, the attacker was able to break this combined MAC simply because the hash function was not collision resistant. So it should be, again, I want to emphasize that if someone advertised even one collision for SHA-256, two messages, just one pair of messages that happen to have the same output under SHA-256, that would already make this construction insecure, because an attacker could then ask for the tag on one message, and in doing so he would obtain the tag on the other message as well. And that would count as an existential forgery. Okay, so already we see that collision resistance is a very useful primitive in that it lets us expand the input space of cryptographic primitives. I want to show you one more application where collision resistance is directly used for message integrity. Imagine again we have files that we want to protect. Let's imagine these files are actually software packages that we want to install on our system. So here are three different software packages. Maybe one is GCC, one is Emacs, and another one is, VI. Now the user wants to download the software package, and he wants to make sure that he really did get a version of the package that he downloaded, and it's not some version that the attacker tampered with and modified its contents. So what he could do is basically refer to a read-only public space that's relatively small. All it has to do is hold small hashes of these software packages. So there isn't a lot of space needed here. The only requirement is that this space is read-only. In other words, the attacker cannot modify the hashes stored in the space. And then once he consults this public space, he can very easily compute the hash of a package that he downloaded, compare it to the value in the public space, and if the two match, then he knows that the version of the package he downloaded is in fact a correct one. Why is that true? Well, because the function h is collision resistant, the attacker cannot find an F1 hat that would have the same hash as F1. And as a result, the attacker cannot modify F1 without being detected, because there's no way that the hash of his F1 hat would map to the value that's stored in the public space. So the reason I brought up this example is I wanted to contrast this with the MAC example. We kind of saw a similar situation with MACs. In the MAC example, we needed a secret key to verify the individual file tags, but we didn't need a resource that was a read-only public space. With collision-resistant hashes, we kind of get the exact complement, where in fact we don't need a key to verify. Anyone can verify. You don't need a secret key for it. However, now all of a sudden we need this extra resource, which is some space that the attacker cannot modify. And in fact, later on, we're going to see that with digital signatures, we can kind of get the best of both worlds, where we have both public verifiability and we don't need a read-only space. But so far, with either MAX or collision resistance, we can have one, but not the other. So I'll tell you that in fact this kind of scheme is very popular. In fact, Linux distributions often use public spaces where they advertise hashes of their software packages, and anyone can make sure that they downloaded the right software package before installing it on their computer. So this is in fact something that's used quite extensively in the real world. Okay, so in the next segment we'll talk about generic attack on collision resistance, and then we'll go ahead and build collision resistant hash functions. The next thing I want to do is show you a general attack on collision resistant hash functions. If you remember when we talked about block ciphers, we saw a general attack on block ciphers which we called exhaustive search, and that attack forced the key size for a block cipher to be 128 bits or more. Similarly, on collision resistance, there's a general attack called the birthday attack, which forces the output of a collision-resistant hash functions to be more than a certain bound. And so let me show you the attack, and then we'll see what those bounds come out to be. So here's a general attack that can work on arbitrary collision-resistant hash functions. So here we have our collision-resistant hash function, supposedly. Let's suppose that it outputs n bit values. In other words, the output space is roughly of size 2 to the n. Now the message space is going to be much, much larger than n bits. Let's just say that the messages that are being hashed are, say, 100 times n bits. I want to show you an algorithm that can find a collision for this hash function h in time roughly 2 to the n over 2. Okay, so roughly the square root of the size of the output space. So here's how the algorithm is going to work. What we'll do is we'll choose random 2 to the n over 2 messages in our message space. Let's call them m1 to m2 to the n over 2. Now, because the messages themselves are much bigger than n bits, they're 100 times n bits, it's very likely that all these messages are distinct. So they'll be distinct with high probability. But for each one of these messages, we're going to apply the hash function and obtain a tag t sub I. So this is, of course, the t sub i's are n-bit long strings. And now we're going to look for a collision among the t sub i's. In other words, we're going to find an I and a j such that t sub I equals to t sub j. And once we've done that, we've basically found a collision because, as we said, with very high probability mi is not equal to mj, but the hash of mi is equal to the hash of mj, and therefore we found a collision on the function h. Now, if it so happens that we look through all 2 to the n over 2 t sub i's and we don't find the collision, we go back to step 1 and try another set of 2 to the n over 2 messages. So the question is, how well will this work? In other words, how many times do we have to iterate this process until we actually find the collision? And I want to show you that, in fact, the number of iterations is going to be very, very small, which means that this algorithm will find the collision in time that's roughly proportional to 2 to the n over 2. So to analyze this type of attack, I have to tell you a little bit about the birthday paradox. I imagine some of you have already heard of the birthday paradox. Here stated as a theorem, and I want to prove it to you because everybody should see a proof of the birthday paradox at least once in their lives. So here it is. So imagine we have n random variables, r1 to rn, in the interval 1 to b. And the only thing I'm going to assume about them is that they're actually independent of one another. That's crucial, that these n samples, r1 to n to rn, in this interval are independent of one another. And they also happen to be distributed identically. So for example, they might all be uniform in the interval 1 to b, but again, these would be independently uniform variables. Now, it so happens that if we set n to be about the square root of b, in other words, if we sample roughly square root of b samples from the interval 1 to b, to be precise, it's 1.2 times the square root of b, then the probability that 2 of those samples will be the same is at least a half. Okay, and then it turns out, in fact, the uniform distribution is the worst case for the birthday paradox. In other words, if the distribution from which the ri's are sampled from is non-uniform, then in fact fewer than 1.2 times square root of b samples are needed. The uniform distribution is the worst case. So we're going to prove this for the uniform distribution, and that basically just also proves it for all other distributions. But the proof that I want to show you here will hold just for the uniform distribution. Okay, so let's do the proof. It's actually not difficult at all. So we're asking, what is the probability that there exists an I that's not equal to j such that Ri is equal to Rj? Well, let's negate that. So that's basically 1 minus the probability that for all I not equal to j, we have that Ri is not equal to Rj. This basically means that no collision occurred among the n samples that we chose. Well, let's try to write this out more precisely. Well, we're going to write this as 1 minus. And now when we choose R1, basically it's the first one we choose, so it's not going to collide with anything. But now let's look at what happens when we choose R2. When we choose R2, let me ask you, what is the probability that R2 does not collide with R1? Well, R1 takes 1 slot, so there are b minus 1 slots that if R2 falls into, it's not going to collide with R1. So in other words, the probability that R2 does not collide with R1 is b minus 1 slots divided by all b possible slots. Similarly, when we pick R3, what is the probability that R3 does not collide with either R1 or R2? Again, R1 and R2 take up 2 slots, and so there are b minus 2 slots that remain for R3. If it falls into either one of those b minus 2 slots, it's not going to collide with either R1 or R2. So I imagine you see the pattern now. So R4, its probability of not colliding with R1, R2, or R3 is b minus 3 over b, and so on and so forth until we get to the very last Rn, and the probability that Rn does not collide with the previous Ri's, well, there are n minus 1 slots taken up by the previous Ri's, So if Rn falls into any of the remaining b minus n plus 1 slots, it's not going to collide with any of the previous R1 to Rn minus 1. Now you notice the reason I was able to multiply all these probabilities is exactly because the Ri's are all independent of one another. So it's crucial for the step that the Ri's are independent. So let me rewrite this expression a little bit. Let me write it as 1 minus the product of I goes from 1 to n minus 1 of 1 minus I over b. Okay, all I did is I just rewrote this as a big product as opposed to writing the terms individually. So now I'm going to use a standard inequality that says that for any positive x, 1 minus x is less than e to the minus x. And that's actually easy to see because e to the minus x, if you look at its Taylor expansion, is 1 minus x plus x squared over 2 minus and so on and so forth. And so you can see that we're basically ignoring this latter part of the Taylor expansion, which happens to be positive, and as a result, the left side here is going to be smaller than the right-hand side. Okay, so let's plug this inequality in, and what do we get? We get that this is greater than 1 minus the product of I goes from 1 to n minus 1 of e to the minus I over b. Okay, I simply plugged in x equals I over b for each one of those terms. Now the nice thing about exponentials is that we multiply them, the exponents add. As a result, this is simply equal to 1 minus e to the power of, here, let me take the 1 over b out of the parentheses, sum of I goes from 1 to n minus 1 of I. Okay, so all I did is I took the minus 1 over b out of the parentheses, and we're left with a simple sum of 1 to n minus 1. And so the sum of the integers from 1 to n minus 1 is simply n times n minus 1 over 2, which I can bound by n squared over 2. And so really what I get at the end here is 1 minus e to the power of minus n squared over 2b. Okay, I literally bounded this sum here by n squared over 2. Okay, very good. Now, so what do we know about n squared over 2b? Well, we can derive exactly what n squared over 2b is from the relationship here. So if you think about it, let's look at n squared over 2. Well, n squared over 2 is 1.2 squared over 2. 1.2 squared is 1.44. Divided by 2 is 0.72 times the square root of b squared, which is b. Okay, so n squared over 2 is 0.72b, and as a result, n squared over 2b is just 0.72. So we get 1 minus e to the power of minus 0.72. Well, so now you just plug this into